Data science and machine learning is the hardest job of the 21st century with an average salary of $120,000 per year. According to LinkedIn, the data science job profile is among the top 5 jobs in the entire world. Now, if you want to foray into the world of data science, you need to have good command over statistics, as it forms the base of all the data science concepts. So, with the help of statistics, you can make predictions such as New York will be hit with multiple tornadoes at the end of this month, or the stock market is going to crash by this weekend. Now, all of this sounds magical, doesn't it? Well, to be honest, it's just statistics and not magic, and you don't really need a crystal ball to see into the future. So, keeping the importance of statistics in mind, we have come up with this comprehensive course by Dr. Abhinanda Sarkar. Dr. Abhinanda Sarkar has his Ph.D. in statistics from Stanford University. He has taught applied mathematics at the Massachusetts Institute of Technology, been on the research staff at IBM, led quality, engineering development, and analytics functions at General Electric, and has co-founded Omics Labs. We are uploading this high-quality classroom session by Dr. Abhinanda Sarkar from Great Learning's Business Analytics and Business Intelligence course, which has been ranked #1 analytics program consecutively for the past 4 years. This tutorial will be on YouTube for only a limited period of time, so that learners across the world can have access to high-quality content. So, please do subscribe to Great Learning's YouTube channel and share the video with your peers so that everyone can learn from the best. Now, without further delay, let's have a quick glance at the agenda. We'll start off by understanding the difference between statistics and machine learning. Then we'll go through different types of statistics, which are descriptive, predictive, and prescriptive. After that, we'll understand the different types of data available. Going ahead, we'll understand the concept of correlation and covariance comprehensively. Following which, we'll head on to probability and learn how to implement conditional probability with Bayes' theorem. And finally, we'll look at 2 types of probability distribution, binomial distribution and Poisson distribution. So let's start off with the session.
What you now need to do is you now need to be able to get the data to solve this problem. So therefore, the statistical way of thinking typically says you formulate a problem and then you get the data to solve that problem. The machine learning way of looking at things typically says, here is the data, tell me what that data is telling you. Many of my colleagues and I myself have run into this problem when going for interviews, etc., etc. And so sort of statisticians say that we're not getting jobs out there, and so I go to people who are hiring and saying that why don't you hire statisticians? And I reach an interesting conclusion to this entire discussion, that sometimes around the way the interviewer who's interviewing the statisticians for a data scientist job asks the question, here is my data, what can you say? And the statistician answers with something like, what do you want to know? And the business guy says, but that's why I want to hire you. And the statistician says, but if you don't tell me what you want to know, how do I know what to tell you? And this goes round and round, right? No one's happy about this entire process. So there's a difference in the way these two communities approach things. My job is not to resolve that, because in the world that you will face, you'll see a lot more of this kind of thinking than you'll see in this kind of thinking. Because in this world, the data is cheap and the question is expensive. And you're paid for asking the right question. In this world, the question is cheap and the data is expensive. You're paid for collecting the data. So sometimes you will be in a situation where this is going to be important. For example, let's suppose you're trying to understand who's going to buy my product. You're asking the question, let's say that my products aren't selling, and you want to find out why. What will you do? Get what data? So let's say that you're selling, I don't know, what do you want to sell? You want to sell watches, say? So let's suppose people aren't buying watches anymore, which is a reality, correct? So you're a watch company. Who buys watches these days? The entire business model of a watch is disappearing. Do you have watches? Some of you have. He has. Actually, a surprising number of you have. Maybe they do different things these days, right? That seems like a very... That's a fitness device. It's not really a watch at all. So something like this was actually with my daughter at lunch today. So she got something like this. I'm not sure. My wife, who's an entrepreneur, runs her own company. She came back from Delhi. She came back with 2 of these. I don't know where she picked them up. So my daughter, the first thing she did, she took one of this and she took this thing out. Because she thought of the whole wristband as an unnecessary idea. I mean, that didn't occur to her. I mean, that's a separate thing. That's a nice little beautiful red wristband, etc. So a watch is a different thing. But let's say that you're a watch company, nobody's buying your watches. Or fewer people are buying your watches. Now, how are you going to solve this problem? Or how are you going to process this information? What do you want to do? What do you want to know?
Check the models, testing, not say.
Okay. But remember, I'm asking this question also from an analytical perspective. So when you say that, to check the model and see what is not sold, that assumes the whole data question. So first order, you'll see sales. For whom and when and how? How do you structure your data? How will you arrange the problem?
Let's say what are your competitors selling?
Okay, that makes problems even harder because now you're going to look for data that isn't with you. No, he's right. Maybe people are not buying watches because they're buying something else. That's a reasonable thing. But let's keep this problem simple. Let's consider only data that is within you. We'll go outside, not to worry. But let's say that I'm looking at my data. What data do I want to see and what questions do I want to ask of it? So sales year by year, types, and then what comparisons do I want to do?
Year on year.
Year on year?
Region wise.
Region wise, age. With what purpose? What question am I asking the data?
What section of customers are buying my product or
what section of customers are buying my product compared to what?
What has changed in terms of the
what are my biggest set of customers?
So that's one thing. Who are my biggest customers? Okay. That's a very interesting question to ask, except that question implies that I needed to know who my biggest set of customers sort of could have been. But it's a good point. Where is the bulk of my sales coming from? Then someone else says something about time. Is it going down? So you can look at things like saying that for which group of customers are my sales going down the most? For example, you could ask that. I'm not saying that's the right question, but that's a possible question to ask. So let's suppose you follow that approach, that I'm trying to understand. I know that my sales are going down. That's an obvious thing. My CEO is telling me, my CFO is telling me, and if I don't stop this, we're all going to be out of a job. Correct? The HMT factories in Bangalore are not in good shape. One of them, I think, has become the income tax office. Right, somewhere in the Malleshwaram area. So that's going to happen to me if I don't do this well. So I know my sales are going down. But I don't know by how much and particularly for whom. So are there segments for which the sales are going down? Which segments are sales going down the most? In which segments are they going down a little bit? How fast are they going down? I can ask questions of that sort. Now, what conclusions at the end of this do I want to be able to do? How do I want to use this information? Now, for this, you usually follow something like a 3-step process, and you may have seen this, and this covers both these sides. And these words should be familiar to you to some extent. The first is called descriptive. The second is called predictive. And the third is called prescriptive. Have these words been introduced to you, at least in this you've read it, I'm sure. You all cruise the web and look at blogs and things like that. Nothing new in this, I'm sure. But I just want to set a context because it's going to talk a little bit about what we're descriptive. There's a C here. So descriptive, predictive, and prescriptive. Now, what is a descriptive problem? The descriptive problem is a problem that says that describe for me where I'm losing my sales and when I'm losing my sales. It just describes the problem for me. It tells me where the problem is. It locates it. It isolates it. The predictive problem says, look at this data and give me an idea as to what might happen or what would happen if I change this, that or the other. So let's suppose I do the following kind of idea. I say that let me relate my sales to my prices. Let me try and understand that if I reduce my prices of my watches, will more people buy them? Conversely, if I make my watches luxury items, increase the price of a watch, remove a low-end brand and make a watch an aspirational thing, a decorative item, a luxury item, a brand item, so that people wear a watch not to see the time but also as a prestige statement, as a fashion statement. Whatever it is, if I do this, then what will happen? That's predictive. I'm trying to predict something based on it. I'm trying to say if something happens to, let's say, one part of my data, what will happen to the other part of my data? And then based on that, the doctor carries out a predictive analysis of you. Because I see this, I now think you have this issue. You have this thing going on. Let's say I'm diagnosing you as being pre-diabetic. You're not yet diabetic, but you're happily on the way to becoming a diabetic. Now, because of this, I now have to issue you a prescription. I now should tell you what to do. So there's the data that comes from you. That data in some way is modeled using the domain knowledge that the doctor has. And that model has translated into an action. That action is designed to do something. Typically, it's designed to do something actually fairly complicated. The first action that the doctor tries to do is, number one, let's say, do no harm, the Hippocratic Oath. First, let me make sure that I don't do any unnecessary harm to the patient. Then let me, shall I say, optimize his or her welfare by making sure that I control the blood sugar the best and that I postpone the onset of diabetes as best as I can. It's a complex optimization problem of some sort. In a business also, it's a complex optimization problem. Right? I need to be able to sell more watches. But I also need to be able to make money doing so. I can increase my sales, but if I increase my sales and my profits go down, or my earnings go down based on the cost, then that's a problem. But at the same time, if I try to run a profitable business and nobody buys my product, that also is not a particularly good idea. Then there are other issues maybe in running the company. I've got employees that I want to keep on the boards. How do I run the company in such a way so that it needs that particular labor force? I have finances to take care of. I have loans to repay. How do I get the cash flow in order to repay the bank loans that I have? So the prescription has to meet lots and lots of requirements. If you are building an autonomous vehicle, you'll have situations saying the car has to do this. But it also has to follow certain other rules. For example, if it sees someone crossing the road, it should stop. But it shouldn't stop very suddenly. Because if it stops very suddenly, it's going to hurt the car, it's also probably going to hurt the driver. So it needs to stop, but it shouldn't stop too suddenly. It has to follow the rules of the road. Because otherwise the computer will simply say, oh, you want me to avoid the person crossing the road? I'm just going to go behind the person. And you're going to tell the car to please don't do that because there's a house next to it. You can't just sort of do that. Oh, you didn't tell me that. You just told me to avoid the person. You didn't tell me about the house. Okay, we'll put that as a constraint in our program and see how well it goes. So prescription is problematic. Another simple way of doing it might be to say that description is how many centuries has Virat Kohli scored. Look up Cricinfo and it will give you the answer. Prediction might be try to guess how many centuries Virat Kohli will score in the World Cup. Prescription might be how do we get Virat Kohli to score more centuries in the World Cup. And as you can figure out, you're going from a purely data-based version of the problem into something that's only notionally about the data. Data will help you, but there's a lot more than the data when it gets to that. What we'll do today, what we'll do now, once I've finished talking to you, is we'll take a look at what the descriptive part of analytics is. So the descriptive part of analytics is talking about simply describing the data without necessarily trying to build any prediction or any models into it. Simply telling you the way it is. This is hard. This is in itself not necessarily an easy thing to do, because you need to know very well how to do that and what are the ways in which one looks at data. This is skillful in itself. So, for example, let's suppose that you're a doctor. You go to the doctor, and the doctor is looking at your symptoms, and the doctor recommends a blood test. Now, how does a doctor know what blood test to recommend? Based on the symptoms. But remember that potentially there's an enormous amount of information in you. All of us as biological things carry an enormous amount of information in our blood, in our neurons, in our genes, or wherever. You know, if you're talking about big data, as I said, there's 2 meters inside every cell, and there are a few billion neurons in your head. You don't need to go far to see big data. You are big data. You are one walking example of big data. We all are. Right? Now, in that big data, what little data does the doctor know to see? That's the descriptive analytics problem. The doctor is not doing any inference on it. The doctor is not building a conclusion on it. The doctor is not building an AI system on it. But it's still a hard problem. Because given the vast amount of data that the doctor could potentially see, the doctor needs to know that this is interesting to me, and this is interesting to me, and this is interesting to me. And this is interesting to me in this particular way. For example, a blood test. Let's suppose that I draw blood from you for a particular purpose. Let's say for blood sugar. Correct? Leaving aside the biology of how much blood, etc., to draw. None of you, I guess, are a doctor. Any of you are doctors here? Any doctors in the room? No doctor, so I can say whatever I want to. You won't understand what I'm saying. No, but I'm old enough that this is a real problem for me. So you have a large amount of blood that's flowing through you. We all do. This blood carries nutrients. What that does is that every time there is a nutrient inflow, the blood looks a little different. So if you eat, your blood looks a little different. Because that's your blood's job. The blood's job is to carry nutrients. So if you want to run, you want to walk, if I'm walking around, my legs are getting energy from somewhere. The energy needed to my legs is being carried from the blood, and it is being generated through inputs that I get. Some of it because of the air that I breathe, from where it gets the oxygen to burn things. Some of it from the food that I've eaten, the nice lunch that I had, where it gets the calories to do that. So therefore, based on what my energy requirements are, and based on what I've eaten, my blood is not constant. My blood content is what is known as a random variable. What's random about it? Because it looks a little different all the time. Your blood at 12 o'clock is going to look a little different. 12 o'clock at midnight is going to look a little different from 12 o'clock at noon. Because it's doing something a little different. The same phenomena is there everywhere. If I were to, for example, measure the temperature of the oil in your car or in your two-wheeler, what do you think that temperature will be? It depends. First of all, it depends on whether the car is running or not. It depends on whether it has run or not. It depends on how much oil there is. It depends on how you drive. It depends on the temperature rest of the car. The answer is it depends. And the same is true for your bodily fluids. So this becomes a slight problem. Because if it is random, then from a random quantity, how do I conclude what your blood sugar is? How does a doctor reach a conclusion of any sort? Average of what? Average of particular duration. So there are multiple averages that you can get. First of all, there is a question of saying that if I take blood from you, how is the blood usually collected? So the phlebotomist comes and usually takes an injection from one point. Let's say by some strange accident, this is thoroughly inadvised, but let's say by some strange accident, two different people are drawing blood from two hands at the same time. Do not try this at home. But let's suppose they do this. Will they get the same blood?
Depends. Ideally, yes.
Ideally, yes.
It depends.
What time it is?
Two different.
Same time. Right, at the same time, as I said, do not do this at home. But at the same time, you're getting two different samples. There's not just a question of time. Your blood is not going to look the same even within your body at one period of time. Even from the left hand, even from the right hand at exactly the same period of time, it's not going to look the same. There is a slight problem that's somehow a little obvious, that you know your heart is in the middle. Right? Your heart is actually in the middle, but it beats to the left. Why? Because the heart is what? The heart is both a pump and a suction device. The pump side is on the left, the suction side is on the right. So your blood pours out from your left side and it goes back in on the right side. So there's a slight asymmetry in your body between left and right. One side tends to go out, the other side tends to come in. It's slight, it mixes up all in the middle. So one sampling idea is that I'm taking a sample of blood from you, and it's just one example. The second question is, as you were saying, it's a question of time. So you can average over time. Now if you average over time, this is a little easier. You can say I'm going to do this maybe before eating, after eating, a little after eating. So for those of you who have blood pressure tests, for example, blood sugar tests, once they ask you to do it, fasting. And then they ask you to do it some 2 hours after eating. Do they tell you what to eat? Sometimes with glucose. Okay. Sometimes they don't. They sort of say that based on what you naturally eat, let me figure out what you are processing. They expect you to eat a typical meal and not go and eat, large amounts of KFC if that is not what you normally eat. Just eat what you normally eat. If you're vegetarian, eat normal vegetarian, eat normal food, and then figure it out. Let's see how good your body is at trying it out. So it's saying, do a normal thing, and I'll take another normal sample. Then one of you said something very interesting. They average things out. Now, what does averaging do?
Neutralize.
That's an interesting word to use. Neutralizes things.
Provide a general idea.
Provide context.
Provide context. Context of what? Context. That's a good point. So what is the doctor trying to do? So let's simplify things a little bit and say that, let's suppose that the doctor has a threshold. Let's give it a number. Let's say the doctor says that if your blood sugar is above 140, I'm going to do something. If your blood sugar is, say, less than 140, I'm not going to do anything. I don't know whether this is the right number or not, but just let's make it up. Now the doctor is going to see from you a number. It may be a single reading, it may be an average, it may be a number of things. How is the doctor going to translate what they see from you and compare it to the 140? How is that comparison going to be made?
Maximum number of people.
Normalizing the value.
Maximum.
So let's suppose I have just one reading. So let's suppose that I have one reading, and that reading, is 135. I've just got one reading from you, 135. What does that tell me?
Standard, how much it is needed?
No test required.
No test required. One argument is, it's simple. Let's take a very machine learning computer science view to this. 135 is less than 140. So now he's saying, yeah, but you know what? Let's say that 135 and another guy who say 120, there should be something that says that this 135 is a little bit more trouble than 120. Closer to the threshold, as he says. So maybe, in other words, this threshold isn't quite as simple as I thought it was. So I can solve this problem in one of two ways. One way to do this is to make this 140 a little range. This is sometimes called fuzzy logic. Right? In other words, the question you're asking becomes fuzzy, not as crisp. You're not fiddling with the data, you're fiddling with the boundary, you're fiddling with the standard. The other way to do that is to create a little uncertainty or create a little plus minus around the reading itself, around 135. Saying that if this is 135, And let's suppose that I go and get another reading. And the second reading that I get is say 130. And the third reading that I get on the day after that is say 132. And I'll say, okay, seems to be fine, I might say. But let's suppose after 135, the guy goes and I do my usual thing and I measure it again. And this time it comes out as 157. And I do it again and it comes out as 128. And I do it again, it comes out to be 152. So in both cases 135 was probably a good number, but in one cases 135 was varying very little and in the other cases 135 was varying a lot. Which gives me different ideas as to how to process it. So what descriptive analytics talks about essentially is trying to understand certain things about data that helps me get to conclusions of this kind a little more rigorously. Now to be able to quantify what these plus minuses are is going to take us a little bit of time, and we will not get there this residency, we'll get there next residency. To say that in order to say it's not 135 but 135 plus minus something, that question now needs to be answered. But to do that, I need to have two particular instruments at my disposal. One instrument that I need to have at my disposal is to be able to know what to measure. I need to say, what does an error mean? I need a statement that says that maybe I'm 95% confident that something is happening. I'm 95% sure that this is below 140. I need a way to express it, and that is the language of probability. So what we will do tomorrow is we'll introduce a little bit of the language of probability. It will be sort of unrelated to what we're doing today, so there's going to be a little bit of a disconnect. But what we're going to do is we're going to create two sets of instruments. One instrument that is purely descriptive in nature, and one set of instruments which is purely mathematical in nature, so that I can put a mathematical statement on top of a description. And the reason I need to do that is because the pure description is not helping me solve the problem that I've set. So therefore what will happen is, you will see in certain medical tests, you will not see points like this, you will see intervals. Your number should be between this and this. Your cholesterol number, your HDL, whatever should be between this and this. You won't see a number, you will see a range that typifies a variation. And in certain cases you will see thresholds, and maybe it's just a lower limit or an upper limit, but you'll also see a recommendation that says, please do this again. In other words, I'm going to compare, I can't compare one number to one number. One number to one number is typically a very bad place for any kind of analyst to be in, because you've got no idea of which is error prone and where the error is. So therefore what happens is you try to improve one of those numbers. And so either by fiddling around with the range or by getting more measurements. And you'll do that and you'll see that as we go along a little later. So this is a context for what we have. In terms of data, let's see. So this is a set of files that has been loaded. It's a very standard set of files. It's not mine, to be honest. I just want to make sure that I'm doing what I'm supposed to be doing. So for reasons that are more to do with security, my understanding, the notebook will not access your drives. So keep it on your desktop and not complicate life. So, and there is this notebook. It's called Cardio Goodness of Good. The word statistics refers to the idea that this comes from the statistical way of thinking, which, as I said, opposed to the machine learning way of thinking, tends to be a little more problem first, data next, which means we worry about things like hypothesis and populations and sampling and questions like that. And the descriptive part refers to the fact that it is not doing any inference, it is not predicting anything, it's not prescribing anything, it is simply telling you what is there. with respect to certain questions that you might possibly ask of it. Now, what is the context to the case? The market research team at a company is assigned the task to identify the profile of the typical customer for each treadmill product offered by the company. The market research team decides to investigate whether there are differences across product line with respect to customer characteristics. Exactly what you guys were suggesting that I should do with respect to the watch. Understand who does what. Entirely logical. The team decides to collect data on individuals who purchase a treadmill at a particular store during the past 3 months. Like watches, they're now looking at data for treadmills. And that is in the file, in the CSV file. So what you should have is, you should have a CSV file in the same directory, and through the magic of Python you don't have to worry about things like path. Before we get there, remember, because we're looking at this statistically, before we get the data we should have a rough idea as to what we're trying to do, and so they say that here are the kinds of data that we are looking at. The kinds of products, the gender, the age in years, education years, relationship status, annual household income, average number of times a customer plans to use a treadmill each week, average number as a customer expects to run walk each week, on a self-rated fitness scale on 1 to 5, where 1 is in poor shape and 5 is in excellent shape. Some of this is data, some of this is opinion. Some of this is opinion masquerading as data. Like for example, number of times a customer plans to use a treadmill. Hopeful, wishful thinking. It's still data. You're asking someone, how many times will you use it? Her rows, daily, no problem. 7 times a week. Oh, we'll see. But it's still data. It's come from somewhere. So what has happened, the way to think about this is to say that I want to understand a certain something. And the certain something has to do with the characteristics of customer characteristics. And to do this, you can then use you can either take, let's say, a marketing point of view, who buys. You can also take a product engineering kind of view, what sells, in other words, what kind of product should I make, etc. In business, as you probably know, for those of you who are, any of you entrepreneurs? One hand up. One hand up. They're closet entrepreneurs from what I could figure out. Right. Sometimes it's unclear what that word means. In other words, you think you are, or you're not confident enough to call yourself one, or you're doing that. In IT space, if you're an entrepreneur, for example, in physical product space or even in software space, one of the things you often think about is what's called the product market fit, which is you're making something. How do you match between what you can make and what people will buy? Because if you make something that people do not buy, that doesn't make any sense. On the other hand, if you identify what people buy and you can't make it, that also doesn't make too much sense. So the conclusions that we will draw on this, we will not draw on today. But the purpose is to be able to go towards conclusions of that kind. Either isolate products, isolate customers, and try and figure out what they tell us. Pandas generally has a fair amount of statistics built into it. That's what it was originally built for. NumPy is something that was built more for mathematical problems than anything else. So some of the mathematical algorithms that are needed are there. There are other stat-sci plots in Matplotlib or Seaborn and many other things that you've seen already. Python is still figuring out how to arrange these libraries well enough. Shall we say, the programming bias sometimes shows through in the libraries. So I, for one, do not remotely know this well enough to know what to import up front. But a good session, you know what to import up front and you do all this up front. So you don't get stuck with what you want to do. The naming is up to you. If you like the names as they are, then that's fine. If you want a standard set of names. So when you wrote the data set, if this is in the right path, just this will work. .csv. It's usually smart enough to convert Excel forms into CSV. In other words, if you have this as XLS and things like that, it's usually smart enough, but if it isn't, then just go in and save an XLS file as a CSV file and operate that way, in case it doesn't do it on its own. But more often than not, what you see is that when Jupyter sees it, it will see any XLS file as a CSV file, or go and make the change yourself. Or you can have other other restatements in it as well. You can change functions inside it and you can figure out how much to head. What this tells you is there's the head and the tail of the data. This is simply to give you a visualization of what the data is. This gives a sense of what variables are available to it, what kinds of variables they are. We'll see a little bit of a summary after this, etc. So for example, some of these are numbers. Income. What is income? Income is annual household income. That's a number. Some, for example, let's say gender, male, female, this is a categorical variable. This is not entered as a number. It's entered as a text field. If you are in Excel, for example, right at the top, if you go in and you see that, it will tell you how many distinct entries there are, how many distinct settings there are. So usually what happens right at the beginning, and a data frame like this, if it is created, this is a data frame. If a data frame is created, when it gets created, the software knows as to whether it is talking about a number or whether it is talking about categories. There are certain challenges to that. You can see one particular challenge to this. What does this 180 mean? Counts. Why do you think there are so many decimal places that comes here? 14 years of experience, 16 years of experience. Why is it going 0, 0, 0, 0, 0, 0?
No, that's because mean, median, low are there in the next.
By default,
Yes, it does this because it sees other numbers where those decimal places are needed. So what it does is, what any software typically does is, when it sees data, it sort of says that at what granularity do I need to store the data. Sometimes this is driven by your computer, your 64-bit, your 32-bit and things like that. But what it does is, it means that the data is stored in the data frame to certain digits. Now, usually you don't see that, you'll see it in this way. But sometimes, for example, when you say include equal to or and you ask for a full description, the data comes out in this slightly irritating way. Because of something here, because of, let's say, the income field or any of that. Now, when it looks at the descriptions of this, what is the description that it is reporting and how does it choose to report out the description? In this particular situation, so let's take a little bit of a closer look at this. One thing here, look at the way it's done here. So count, unique, top, frequency, and then there are certain things here: mean, standard deviation, minimum, 25%, 50%, 75%, and max. When it sees a variable like gender, it reports out lots and lots of NANs. What does that tell you right off the bat? It can't do that, which means it's not a number. This is not a number. In other words, if you ask me to find the mean of something and you're giving me male and female as inputs, I don't know what to do. Which is an entirely reasonable stand to take for any reasonable algorithm, right? It requires another kind of description for it to work. But the problem with describe this syntax is that it's asking for the same description for all of them, whether it's in significant digits, whether it's in columns, etc., etc. So it's chosen this description and it says that that's all that I'm going to give you. But where it makes sense, let's say for example I look at age. Now for age I've got 180 observations and it is calculating certain descriptions for it. Correct? So what are the descriptions it is calculating? Let's look at these. It's calculating a description like, say, minimum. Minimum is what? 18. Maximum is 50. These are easy to understand. Then let's look at something a little interesting. Suppose I want to report one number, one representative age for this data set. This is like asking the question, how do I get a representative blood sugar number for you? I can give you a minimum and a maximum, but to do the minimum and maximum, I need to draw blood many times from you. But let's suppose I want one representative age for you. Somebody asks you, what is your blood sugar? You want to give them one number. Similarly, somebody is looking at this data and asks the question, give me a representative age. How old is your typical user, or what age do you want to build it for? Or you're even asking, let's say, a product question. You're a product designer, and a product designer building a treadmill. Now, how do you design a product? Those of you who are engineers, based on the weight. Now, very good. What weight? Whose weight? Who's the user? What is the weight of the user? He's got a good point. As a design engineer, I need to know what weight will be on that treadmill. Now, what is the answer to that question? Max?
Users who visit the gym.
So there's a question of saying that if I want to measure a variable by one number, how should I even frame that question? What makes sense? What is a one average? No? Max? In this particular case, you might argue the max is the right number, because I want to be able to say, if I can support him, I can support anyone. But there's also a downside to that. I've now engineered that product. You could argue that I have, shall I say, over-engineered that product. Correct? I'm sorry?
Factor of safety.
A factor of safety? Okay. Alright. So let's suppose that you are doing this for a mattress. You all sleep on mattresses. We're all relatively wealthy based on the fact that we're here. So we probably sleep on a mattress. Not everyone's fortunate enough to sleep on a mattress, but let's suppose you do sleep on a mattress. How much weight should that mattress be designed to bear? If you over-engineer it, what will happen is that, number one, for a reasonable weight, let's say weight a lot below that, that mattress is not going to sink. Let's say that you design it for 100 kilos. Now, if you're 50 kilos or 60 kilos, that mattress is not going to sink for you, because it's going to feel comfortable for someone who is 100 kilos. And for someone who's 50 kilos, you're just going to bounce on it. You're not going to feel its soft silkiness or whatever it is you want to feel from the mattress. It won't work. So what to do? So that's a hard problem. It's a description, but it's a hard problem. Who do I engineer it for? And so therefore, people have different ranges of what I mean to represent it. So here's one version of it. This is what is called a 5-point summary. I report out the minimum, the 25% point, the 50% point, the 75% point, and the maximum. Variable by variable, I report 5 numbers. I report the lowest. What does 25% mean? 25% of my data set, or the people, are younger than 24. The youngest is 18. 25% or a quarter of them are between 18 and 24. A quarter are between 24 and 26. A quarter are between 26 and 33. And a quarter are between 33 and 50. This is what is known as a distribution. This is what is known as a distribution. The statisticians love distributions. They capture the variability in the data and they do all kinds of things with it. So I'm going to draw a typical shape of a distribution. We'll make more sense of it later on. This is a theoretical distribution. A distribution, for example, let's say has a minimum, has a maximum, has say a 25% point, has a 50% point, it has a 75% point. In terms of probabilities, there's 25% here, 25% here, 25% here, 25% here. If you want to think in terms of pure description, this is not a probability, it's just a proportion. If you want to think in terms of probabilities, what this means is that out of 180 people, if I draw one person at random, there's a 25% chance that that person's weight is going to be below 24. Sorry, age 24, correct. If you want to think in terms of probabilities, we'll do that tomorrow. But this is a description. So what this description does is it gives you an idea as to what value to use in which situation. So for example, you could say that I'm going to use 26 as my representative age. If I do that, what is the logic I'm using? This 25%, this 50% point, so to speak, this is called the median. This is called the median, and we'll see it. Median means the age of the average person. First sort, take the middle person and ask, how old are you? The age of the average person. I could also ask for the average age of the person, which is what? Which is the mean, which is 1 over n x1 plus xn. Now this is algebra. What you have to do is you have to put n equal to 180. This is the first age, the second age, the third age up to 180. 1 by 180, age 1 plus age 180. This is called the mean. This value is what? 28.79. The average age is about 28 years or 28 and a half years, 28.8 years. But the age of the average person is 26. Yes?
So could you please repeat the median and the mean?
The difference between the two?
You described what is the age of the person.
So I described the median as the age of the average person, and I described the mean as the average age of a person. Now he's looking at me like saying, you have to be kidding me, right? That's confusing. I admit to it. The easy way to understand it could be this. What is the mean? Add them all up, divide by how many there are. What is the median? Sort them from the smallest to the largest, pick off the middle. If they're an even number, what do? You take the average of the two middle ones. If they're the same, it'll be the same number. If they're not, it'll be a number between them. So sometimes the median may show up with a 0.5 or something like that for that reason. If there is an integer counts, but there are an even number of counts. Now, which do you think is better? You're giving the right answer. It depends. You'll figure out that I like that answer. They both make sense. They both make sense. It depends on what context you're going to use it for. In certain cases, yes.
You said that median is basically the mean of the.
It's the age of the average person. It's a reading from the average person.
So what is the parameter we are saying? It is the average person. How we are getting that average?
Okay. So if you're talking in terms of parameters, so he used an interesting term. He's saying, what is the parameter I'm after? Parameter is an interesting word. Parameter refers to something what generally in a population. It's an unknown thing that I'm trying to get after. For example, blood sugar is a parameter. It exists, but I don't know it. I'm trying to get my handle on it. Correct? So if I'm thinking in terms of parameters, then these are different parameters. So let's look at a distribution here. I'm not sure whether this will pick up things. I hope so. So the median is a parameter such that On this side I have 50%, and on this side I have 50%. This is the median. The mean is what is called the first moment. What that means is, think of this as a plate of metal, and I want to balance it on something. Where do I put my finger so that it balances? It is the CG of the data, the center of gravity of the data. You can understand the difference between these two now. If, for example, I push the data out to the right, what happens to the median? Nothing happens to the median because the 50-50 split remains the same. But if I push the data out to the right, the mean will change. It will move to the right. Your lever, the lever principle, right? If there's more weight on one side, I have to move my finger in order to counterbalance that weight. So these are two different parameters. If the distribution, for example, is what is called symmetric, symmetric means it looks the same on the left as on the right, then these two will equal. Because the idea of going half to the left and half to the right will be the same as the idea of where do I balance, because the left is equal to the right. So when the mean is not equal to the median, that's a signal that the left is not equal to the right. And when the mean is a little more than the median, it says that there is some data that has been pushed to the right. And that should be something that you can guess here, because the mean and the median to some extent are what? 24, 26, etc. The lowest is 18. That's about 6 years, 8 years less than that. But what is the maximum? 50. That's 25 years beyond. The data is pushed to the right a little bit. Instead of saying pushed to the right technical term is right skewed. There are, shall I say, people are more not average on the older side than on the younger side. There was a hand up somewhere. Yes.
I was just confused with the statement that median would not move, but then you explained it.
Yes. So therefore, one reason that the median often doesn't move is because it is not that sensitive to outliers. So let's suppose, for example, we look at us and we ask ourselves, what is our mean income or our median income? And we have that. Each of us make a certain amount of money, we can sort that up and put that in. Now let's suppose that Mr. Mukesh Ambani walks into the room. Now what is going to happen to these numbers? Mean is going to go up, right? He alone probably makes a very large multiple of all our incomes put together. Possibly. I don't know how much you make. I know how much I make. But what's going to happen to the median? It's going to stay almost the same. The typical person may move by at most half. Because what is a typical person going to be? The typical person is going to be an actual individual in the room, or maybe an average of 2 individuals in the room. And that person is not going to change. Yes. Yes. That's one conclusion we can draw on this. There are other plots below which will also show the same thing. You're not being able to draw that conclusion. Well, good logical reason. I haven't shown you the full data. We'll see the histogram and we'll do that. So hold on to that question. The conclusion was drawn is that there are two things to do. See here. One is, if I simply look at this without seeing any more graphics, where is the middle of the data from a median perspective? At 26? Correct? Now from 26, look at the difference between 26 and the smallest. 18. Between 18 and 26, that's 8 years. This 8 years contains 90 observations because there's 180 total. Now, what is on the opposite side of this? 26 to 50. That's how many years?
24.
24 years. This 24 years now contains how many observations? Same 90. So there are 90 observations that are between 18 and 26. And there are 90 observations between 26 and 50. So if I were to draw a picture, what would that picture look like? Yes, exactly as you're drawing it, right?
What we can say is skewed on the left hand side or right?
This usually by definition is called right skewed. This is a problem that BABI has. Does this mean it's left skewed or right skewed? As a word, right, it's called right skewed. More data to the right. Sorry, more data is a dangerous word. No, it's the same number of observations. I'll say the data is pushed to the right.
More variation on the right side.
More variation on the right side is probably a safer way of putting it, yes. So skewness is often measured in various things. One measure of skewness is typically, for example, mean minus median. Mean minus median, if it is positive, it usually corresponds to right skewness. Mean minus median negative usually corresponds to left skewness. This is a statistical rule, but sometimes it is used as a definition for skewness. There are many definitions for skewness. Skewed data sometimes causes difficulties in analysis, because what happens is the idea of variation changes. Being variation on one side means something a little different than variation from the other side. By the way, what's happening to you with respect to things like books? Are you getting books? Are you not getting books? I have no idea what the books are. You got one book, which is what? Which is the statistics book? Okay, I'll take a look at that book later. So, this book, right? Okay, show me the book. Okay. Comment 1, very nice book. Comment 2, not a Python book. Right? That doesn't make it a bad book. So, if you're looking for help on how to code things up, this is not the right book. Get a book like Think Stats or something like that. But, if you want to understand the statistics side to it, it's an excellent book. So everything that I'm talking about is going to be here. I might talk about which chapters and things like that at some point. And I might talk about how to use this in the book. So for example, at the back of this book, there are tables. There are tables at the back of this book, which we'll learn how to use. And then I'll try to convince you that you shouldn't use them. But remember, many of these methods are done in ways in which either you don't have access to computers, or if you do have access to computers, you don't have them, shall we say, at runtime. In other words, when I want to run the application on it, I can build a model using a computer, but I can't run it within one. The runtime environment for statistics is often done when there are no computers around. The build environment can include computers, but the runtime environment cannot. A lot of statistics is done under that kind of situation.
Even probability is also covered here?
Yes, very much so. Very much so. Okay, so definitions of skewness and things like that. Do it in the way you usually use a book, which means you go to the index and see if the word is there. And then you go back and figure it out, and it will give you some ideas as to how that works. It's a nice book. It's one of the best books that you have in business statistics, but it's not necessarily a book that will tell you how to code things up. That is not a deficiency of the book. Not every book can do things of that sort. There are other books around that will tell you how to code things up, but will not explain what you are doing. It's important to know what you are doing. It's also important to know why you're doing it. But books can't be written with often everything in mind. Yes?
Can you suggest some book which tells us how we can think that way?
The thinking is here. I think this is good for thinking. I would absolutely recommend this book on the thinking side.
Because the problem lies that in which situation what we need to apply.
Yes, and that answer I think is very, very good here. Where you won't get is it will say do this, and it won't give you the Python syntax to do it. That will not be here. So if you can solve that problem through some other means. I used to have a colleague in corporate life who had a very big sticker on his board. It said, Google search is not research. Right? Now nobody agrees with him anymore. So I suppose that when in doubt, you do what normal Homo sapiens do today, which is you Google for an answer. So one possibility is that you understand something from a book such as this, and if you want to understand the syntax, just Google for the term. Say Python, that term, whatever, it will probably give you the code. Things are very well organized these days. There's also the question, and I should give you a very slight warning here, not to discourage you from anything. But in the next 9 months or thereabouts, the duration of your program, there's going to be a fair amount of material that will be thrown at you. Correct? The look and feel will sometimes be like what we would often call at MIT as drinking from a fire hose. You can if you want to, but you will get very wet. So therefore, pick your battle. If you want to understand the statistics side of it, please go into the depth of it. But if you try to get into equal depth on every topic that you want to learn, that will take up a lot of your professional time. Now the reason we do the statistics part first, one, it's a little easier from a computational perspective, although harder from a conceptual perspective, so we begin it this way. But hold on to that idea, and then as you keep going, see if this is something that you want to learn more on. And if you can, you're welcome. Just write to us or let us know, or let anyone know that Hoita has just come in, let her know, and we'll get the references to you. But if you want to, say for the first 2 residencies, please read the book and see what happens. If there are doubts, yes, but it's a well-written book. Its instructor is one of our colleagues here. If you want, we can also help explain things. So this is the summary. What did the summary tell you? This summary gave you what's called the 5 numbers that help you describe the data. Minimum, 25, 50, 75, max. We'll see another graphical description of this. It also described for you a mean. There is also another number here, and this number is indicated by the letters STD. STD refers to standard deviation. STD refers to standard deviation. And what is the formula for a standard deviation? STD is equal to the square root of little bit of a mess, but 2 steps. Step 1, calculate the average. Step 2, take the distance from the average for every observation. Ask the question, how far is every data point from the middle? If it is very far from the middle, say that the deviation is more. If it is not far from the middle, say that the deviation is less. Deviation being used as a synonym for variation. I'm talking about variation. Variation can be more or variation can be less. More than the average, less than the average. If someone is much older than average, there's variation. If someone is much younger than average, there is variation. So therefore, both of these are variation. So what I do is, when I take the difference from the average, I square it. So more than x bar becomes positive, less than x bar also becomes positive. Then I add it up and I average it. There's a small question as to why it is n minus 1, and that is because I'm taking a difference from an observation that is already taken from the data. Now I have squared. When I have squared, my original unit was in age. When I have squared, this has become age squared. So I take the square root in order to get my measure back into the scale of years. So the standard deviation is a measure of how spread a typical observation is from the average. It is a standard deviation, where a deviation is how far from the average you are. And because of this squaring, you need to work with a square root. In sort of modern machine learning, people sometimes use something called a mean absolute deviation, MAD, very optimistically called. So what MAD is you don't take a square, you take an absolute value, and then you do not have a square root outside it. And that is sometimes used as a measure of how much variability there is.
So why it is squared then?
Why is it?
Why we do it just?
We square it because we want to look at both positive and negative deviations. If I didn't square it, what would happen is it would cancel out. What was the word that one of you used? Neutralize, right? I love that term. Your positive deviations would neutralize your negative deviations.
So I went with this x minus x bar is there.
Yes.
So it should be like x square minus x square. And if you are seeing the positive and the negative.
This number is going to be positive if say x1. So let's look at the first number here. So if I look at the head command here, when I did the head command here, what did the head command give me? The first few observations. So now this is an 18-year-old. This is probably sorted by age. This is an 18-year-old, correct? Now I'm trying to explain the variability of this data with respect to this 18-year-old. Why is there variation? This 18 number is not the same as 28, and 18 is less than 28. So what I want to do is I want to go 18 minus 28.7. What I'm interested in is this 10. This 10-year difference between the two. Now the oldest person in this data set is how old? 50. When I get to that row, this 50 will also differ from this 28 by 22 years. So I'm interested in that 10 and I'm interested in the 22. I'm not interested in a minus 10 or a minus 22. I can do that. I can do that. In other words, what I can do is I can represent 18 minus 28 as 10, and I can represent 28 minus 50 as 22. And that is this. As I said, 1 over n minus 1, absolute x1 minus x bar plus absolute xn minus x bar. That is this. With n minus 1. And this is done, as I'm saying. This is what is called mean absolute deviation. And many machine learning algorithms use this. You are correct. In today's world, this is simpler. Now, when standard deviations came up first, this was actually a little harder. But people did argue about this. I think, well, 150, maybe more about, I forget my history that much. There were two famous mathematicians, one named Gauss and one named Laplace, who argued as to whether to use this or whether to use this. Laplace said you should use this, and Gauss said you should use. Now the reason Gauss won was simply because Gauss found it easier to do calculations. Why is this easier to calculate with? Because Newton had come up with calculus a century or so before that. And so, for example, let's suppose that you want to minimize variability, which is something that we often need to do in analytics. Which means you need to minimize things with standard deviation, which means you need to differentiate. This function, the square function is differentiable, you can minimize it using calculus. This is not. So therefore what happened was, Gauss could do calculations, but Laplace could not, and Laplace lost. And Gauss won the definition of the standard deviation.
We haven't much used 25% or 75, so
okay. Why do we not do that? So, today, this entire argument makes no sense. Because today, how do we minimize anything? Our computer program. You don't use any calculus. You run fmin or something of that sort, you basically run a program to do it. So therefore this argument you can both do calculations equally well with this as in that. So today what is happening is that Laplace's way of thinking is being used more and more. This one is a lot less sensitive to outliers. This one, what it does is, if it is far away, the 22 squares to 484 or something like that, which is a large number. So the standard deviation is often driven by very large deviances. Larger the deviance, the more it blows up. And so therefore this is often very criticized. If you read, for example, the finance literature, there's a guy called Taleb, Nassim Taleb, he writes this book called The Black Swan and Fooled by Randomness, where he left and right criticizes the standard deviation as a measure of anything. So today this argument doesn't make a great deal of sense, and when in practice something like this makes sense, it's often used. So a lot of this is done historically. It looks this way because of a certain historical definition, and then it's hard to change. So today in centuries after Gauss, sad people like me are trying to explain it and having trouble doing it. because there's a logic to it, right? I mean, and that logic doesn't hold at all anymore now. Yes.
Standard deviation in simple terms is that 18. How far generally is that from the median?
How far on the average is an observation from the average? Confusing statement again. He's again going to go unhappy. But how far on the average is an observation from the average? If that answer is 0, that means everything is at the average. But you're asking the question, how far from the average is an observation on the average? If I take your blood pressure, how far from your average blood pressure is this reading? If this is exactly equal, then I don't need to worry about variability. Every time I measure blood pressure, I'll see the same thing. What is your average bank balance? Don't tell me that, but you know what I mean, right? You have an average bank balance. Your bank account manager or your bank actually tracks this, what your average bank balance is. But you're not actually, your balance is almost never or very, very rarely equal to your actual average bank balance. It's more and it's less. How much more, how much less is something that the bank is also interested in order to try and figure out, how much of your money, so to speak, to get out there. Because the bank is going to make money by lending it out, correct? But when it lends it out, it can't give it to you. So it makes an assessment as to how much money, I don't want to get into finance now, but you get the drift. So therefore, it is a measure of that. It is not the only measure of that. So for example, here's another measure. So you remember this 25 number and the 75 number that you're asking about? Let's say that I calculate a number that looks like this. Let's say 33 minus, let's say 33 is a 75% point, minus 24. So 33 minus 24, let's say this is my 24 and this is my 33. Between this, how much data lies? 50%. Why? Because this is 25% and this is 25%. This now contains 50%. This is sometimes called the interquartile range. Interquartile range. Big word. Right? Now, why is it called an interquartile range? The reason is because sometimes this is called Q3 and this is called Q1. Q3 stands for upper quartile. You can understand quartile, quarter. So upper quarter, and this is the lower quartile. And the difference between the upper quartile and the lower quartile is sometimes called the interquartile. Why is it called the range? Because what is the actual range of the data? The range of the data in this particular case is 50 minus 18. And 50 minus 18, which is your max minus your min, this is sometimes simply called the range. Range is maximum minus minimum. Interquartile range is upper quartile minus lower quartile. And these measures are used. They do see certain uses based on certain applications. You can see certain advantages to this. For example, let's suppose that I calculate my 5-point summary. With my 5-point summary, I can now give you a measure of location, which is my median, and I can give you 2 measures of dispersion, which is my interquartile range and my range. So those 5 numbers have now been twisted to give me a summary number, which is the median, and a range number. Interestingly, I can also draw mental conclusions from that. For example, I can draw conclusions from these 5 numbers in the following way. 24 and 33. Half my customers are between 22 and 24 and 33. So if I want to deal with half my customers, I need to be able to deal with a range of about 9 years. Within this 9 years is all that I'm interested to get this right. So if I'm building my machine, I'm going to make sure, let's say, that the 33-year-old is okay with this and the 24-year-old is okay with this. Will the 50-year-old be okay with this? Yeah, may not be. But if I want to make the 50-year-old okay with this, I'll have trouble with the 18-year-old. So I can do a lot with even these 5 numbers. We'll see more descriptive statistics as we go along. By the way, this is only for age. I can do this for usage, I can do this for fitness, I can do this for income, I can do this for miles. Income is interesting. Here's the median income, $50,000, and the mean income about $53,000. If you see income, in almost all real cases, the mean income is going to be more than the median income. The per capita income of India is more than the income of the typical Indian. Say, what does this command do? If I say mydata.info, what this is doing is, my data first of all is a data frame that I created. Just to review, I read the PDF file this way. Now this is a describe, and this here is info. Now describe and info in the English language are similar things, description and information. This is interpreted in the software as 2 completely different things. Information is like your variable setting. It's like your integer field, your real field is setting like that. It's giving you information on the data as data. The word data means different things to different people. To a statistician, data means what? To a statistician, data means a number. To an IT professional, what does data mean? Bytes, information. I've lost my data. I don't particularly care what the data is. I've lost my data. So this is that information. It tells you about the data. It's an object. This is description. It's a 64-bit stored integer. It's an object. So it tells you about numeric, categorical. It tells you about the kind of data that's available. Non-null fields. In other words, there are objects in the field, etc. There are so many integer types which are stored at 64 because this computer is probably capable at 64. And there are 3 categorical variables. This is, shall we say, a data object summary of what is there in that data frame, not a statistical summary. Useful in its own way, particularly if you are processing it and storing it. For those of you who are going to go into data sort of curation-like careers, this kind of a database is a nightmare. Because typically what happens is, when you store real data, in addition to data, you often store what's called a data dictionary. Sometimes that's referred to as metadata, data about the data. Because simply storing a bunch of numbers is not enough. You have to say what the numbers are about. This adds a layer of complexity to the metadata. You now have to store not only what the variable is about, but what kind of a variable it is. So many professional organizations say is that archival data should never be a mixture of both numerical and categorical objects. And they pay a price for that. Numerical things should become categorical or categorical things become numerical. But what happens is, if you are storing large volumes of it and archiving it and making it available for people who have not seen it before, it sometimes gets convenient. So therefore, fields like this are often useful to see how big a problem you have. Right? Now I want to plot a few things. To plot, you can plot anything. Seaborn, I think, is coming a little later. But this plot, this is from Matplotlib library, and it is plotting through a command called hist. Hist means histogram, which you've already seen. You've covered histograms, right? I think you've seen histograms. So this is a histogram. Now histogram as a syntax has bin sizes and figure sizes. So what you can do is you can play around with these and see the differences in what this histogram does. But there's a certain default that shows up, and that default is quite good. And here is a histogram distribution of the age. This is not a set of numbers, this is a picture. This is a picture. What does this picture have? This picture has a set of bins, and it has a set of counts within each bins. Between these two numbers, between say 10 and whatever this is, let's say 22 or thereabouts, I have a count of, let's say 17. So it gives a count, and it does this by getting a sense of how many bins there are and plotting this shape. It's a little bit of an art to write a histogram program. There's a Python book out there, I think ThinkStat is one of it, in which sort of the first 1/3 of the book is basically how to write a histogram code. It's a wonderful book, but because it treats this example, it got terrible reviews. Reviewers said, why do I want to learn how to code a histogram? And the book's author is, I'm teaching you how to write a code. A histogram is an example of how to do that. And I tend to agree. If you want to test yourself of your understanding of data and your understanding of any programming language and any visualization language, code a histogram in it. And have fun. So it's a nice challenge from many perspectives. The data challenge, the language challenge, the visualization challenge, all of that. Yes?
So you said archival data should not be numerical plus category.
Many companies do that. That they want archival data to be of only one data form, only one format. Why is that so? Because, as I said, when you store data, how do you store it? Let's say that you've generated an analysis. The analysis is done, correct? And you've decided not to destroy the data. You're going to keep the data in your company's databases or in your own database. How will you keep it? You can take a technology. Let's pick an example. Let's say pick an example. SQL, Excel, whatever. Let's say Excel. Let's say I keep it in Excel. Now, if I keep it in Excel, what will I now do? So let's say I have an Excel spreadsheet. Let's say my cardio data set. Let's say this data set. Now, in addition to the data, what do I need to store with it?
Metadata.
Yes, metadata. How do I store that metadata? Yes, so one possibility is I can have a text file like that, like I had at the top of this, describing all of this, which is typically what happens in Excel storage. It describes this and it describes, there's one file called .dat and another file called .disc or something of that sort, which basically describes the variables, and the idea is that they have the same name, and one extension gives you the data, the other extension gives you the description of the variables that are in this data. Correct? Now this is good. Now what's going to happen? On that data, certain code has been run. That code is going to assume certain things about the data. What do you want that code to assume about that data? Whatever you want that code to assume about that data should be available in the data dictionary. Now, if that code is stable enough to realize that whatever fields you give me, I will run on, that's cool. But if that code requires you to know what kind of data is being used, let's say discrete data, let's say continuous data, in the future you'll be doing things like linear regression, logistic regression. Linear regression will make sense if the variable is a number. Logistic regression will make sense if the variable is a 0 or a 1. If you have that problem, now in the metadata you need to be able to tell not only what business information this variable contains, but also what kind of a computational object it is, so the code can run. So therefore what people often say is that I'm going to make it very simple and I'm going to assume that my entire data frame consists of only one kind of variable, so that when I run any algorithm on it, I know exactly what kind of data input that algorithm is going to get. But I'm saying it's a practical answer that many companies often have. And I've worked in a couple of companies, at least one company where this was very seriously done. So we had to when we put data back in, we had to convert it. And in the situation that I was in, it wanted everything in categories. So what we would do is we'd take continuous data and we would do what's called fine classing, which means that we would divide not into 4 pieces but into 10 pieces. Decile 1, decile 2, decile 3, decile 4 up to decile 1. And every variable was stored now not in its original numbers but as 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So let's suppose that I tell his income is 9. What that means is I know he's in the 9th decile. 10% of the people or more have income more than him, 80% have less than him. He's in that bracket. And all variables were stored that way. Now what happens is every algorithm knows that every variable is going to be stored that way. And you can keep writing algorithms that way. Otherwise what would have to happen is every algorithm would need to be differently. And let's say you're doing credit scoring. Let's say you're doing CRM models. You're doing something of this sort, and you've built a very sophisticated CRM model that tracks your customers, and it works. Now suddenly you've got a new variable coming in, the Twitter feed, and suddenly nothing works. What to do? Go back and rebuild that entire model. That's going to set you back 3-4 months. That's going to set you back a few $1,000s. So you say, no, any variable that has to go in this form. And if it goes into this form, my algorithm can deal with it.
So well, in such case, it might not affect the efficiency of the model that we generate.
Yes, yes. And in practice, I'm going far away from topic now. In practice, a professional analyst has to struggle between doing the right thing badly and the wrong thing well. You want to do the right thing well. But the right thing well is going to cost you time, money, data, and everything. So you struggle between saying that I'm going to get a flawed model quickly built on a new data set, or I'm going to get an inefficient answer on a model that's already been built. And let's see how far it goes. And so these are more cultural issues with how an analytical solution is often deployed in companies. They vary very much from industry to industry. They vary very much from company to company, from the culture of a company to a culture of a company. They depend on regulatory environments. In certain environments, an auditor-like entity comes in and insists on seeing your data. Show me your data. Let's say in finance, this is sometimes happening. Regulatory agency, let's say Reserve Bank of India, goes into a bank and says, show me your data. All this NPAs, etc. Show me your order book, show me your loan book. Correct? And now that has to be done, and the decisions you made have to be done in a way that is patently clear why you have done this. So very often people say, I don't want to make the best risk decision. I want to make the most obvious risk decision. Which may not be the same thing at all. But I'm being audited. So that's a practical question. And I don't have a clean answer to that. But I do know what happens. Is it right? No, it's not. But we live in a world that has that kind of imperfection. One of my teachers, his name was Jerry Friedman. You'll see some of his work later on. He came up with algorithms like projection pursuit, CART, Mars, gradient boosting. He created many of the algorithms that you'll be studying. One of my teachers at Stanford. When he ran our consulting classes, he would say this: solve the problem assuming you had an infinitely smart client and an infinitely fast computer. After you've done that, solve the real problem, where you do not have an infinitely smart client and you do not have an infinitely fast computer. This was in the early 1990s, where computer speeds were a lot slower. And we didn't have powerful machines like this around. So a lot of this is done in that kind of situation, where you are struggling for continuity, when you're figuring it out. Imagine yourself as an analytics manager, and I hope many of you will be. And you have an analytics team sitting in front of you, correct? You're looking at them and you're looking at them in the eye, and you know how much you're paying them. And you know that half of them are going to leave at the end of the year. What are you going to do with regard to the modeling and things like that? Your first order of business is going to be to ensure continuity in some form. Keep it simple, right? Keep it simple. Keep it obvious for the next bunch of people who are going to come in. And for that, you'd be willing to trade a little bit of make it right. So now the new person coming in will now not want to solve a very complicated kind of situation. This is not where you want to be, and I do not want to depress you on day one. But it's also the fun part of the profession, right? It's also what makes it interesting and interesting and exciting. Right? So it's not all bad. Okay, so the histogram command summaries of what these histograms are, and each gives you a sense of what the distribution is. And as you can see from most of these pictures, most of these variables, when they do have a skew, tend to have a right skew. Maybe education has a little bit of a left skew. Maybe education has a little bit of a left skew, that a few people are educated and most people are here, but even so. Right? Now here's an interesting plot. Matplotlib has this as well, but Seaborn has a better version of it, This is what's called a box plot. You've seen a box plot? This is a box plot. People are unsure as to where this box came from because there's a statistician called Box who's used this before, but this box came from, it used to be called a box and whisker plot. These are the whiskers. This whisker will go, this is the median, this is the upper quartile, the top edge of the box, the bottom edge of the box is the lower quartile, the end of the whisker is 1.5 times the interquartile range above the box. Right? If you want a formula, sort of the whisker, the length of the whisker is 1.5 times IQR. Should I have a break now? A little bit maybe, huh? So we'll, okay, 3:45 or whatever, we'll go up to there at least. Yeah, I haven't stopped, I just got distracted. So 1.5 times the, so it goes up to that. If a point lies outside it, the point is shown outside it. If the data ends before it, the whisker also ends. Correct? What is the whisker? Okay, what is the whisker? Alright, let me explain another way. The whisker is the maximum, the top of the whisker is the maximum, the bottom of the whisker is the minimum. Okay? Not okay. Okay. Some of the points are outside. So, this point here, now what is this plot here? Age for males. So what this means is this is the minimum, 18 or whatever it is, and this is the maximum, 48 or whatever it is. Minimum and the maximum. So if you see nothing else on the box plot, no other points other than just the box and the whisker, then your 5-point summary is sitting there. That's it. Right. Now, what happens if you see points like this? Outliers. What is an outlier? An outlier is a point that lies more than 1.5 times the interquartile range above the box. So this whisker will not extend indefinitely. It will go up to 1.5 times this box and then it will stop. And if any points are still left outside it, it will show them as dots. You can treat this as a definition for what an outlier is.
What about the lower whisker?
Same thing.
1.5
Same thing in the other direction. The logic is symmetric.
1.5 times content.
No. That means this it hasn't. The data is ended here.
The data is ended.
The data is ended here.
Was there any other number tried instead of 1.5?
I suppose so, and you can change it. You can. I won't try it now, but you can go to the box plot syntax and change that. So you can go to box plot syntax and you can change that 1.5. It's not hard coded into the algorithm. I think 95% sure. As a statistician, I'm never sure about anything. But it's a parameter in the you should be able to pass the parameter in the box plot function. Default is 1.5. You should be able to change it.
And what's the color part? That's the median, is it?
Which one?
The color.
Color?
Blue color or orange color?
Oh no, these two colors. These two colors are because I've asked for two things. I've asked for male and female. If I had 3 of them,
That's okay. But how the range of the color? The box.
oh this one here. Oh, this is Q3. The lower is Q3 and the upper is lower is Q1 and the upper is Q3.
So this is the quartile range.
Quartile range. So for males, between the bottom whisker to the end of the box is a quarter of your data. The box is half your data, and the top of the box to the end of the whisker is quarter of your data.
So the middle line is
The middle line is the median.
This is the IQ.
The middle line is the median. There is also a function in box plot you can play with, where it will give you a dot. And that dot is the mean. I mean, you can ask boxplot to do that. But a mean is not a general standard component in the 5-point summary. It's a different calculation, not a sort. But if you want to, you can make boxplot to give a dot on the mean as well, by definition. Yes. So mean median. So half the data is between 24 and 34 or whatever that is. Half of all the men in my sample are between those two numbers. I think boxplot doesn't allow you to change the shape of the box. I think that is set. That's sort of central to the idea of a boxplot. It does allow you to fiddle with the size of the whisker, but I don't think it allows you to fiddle with the size of a box. In other words, if you change that to something else, let's say the 20% point to the 80% point, 80-20 rule, that's no longer a box plot. It's another interesting plot. The significance of it is exactly this, as we had seen before. The significance of it is that the data looks like this. It's right skewed. Think of the picture. So if this is your Q1 and this is your Q3, this is your Q2 or the median, then the median is going to be closer to Q1 than it is to Q3. In the same way that the minimum will be closer to the median than the maximum, same idea. This is a summarization for numbers. If you want to summarize for categorical data, what's called a cross-tab or a cross-tabulation, this is simply how many products are there? Product category 195, 498 and 798. They've got three kinds of treadmills and they're trying to understand who was using what kind of treadmill. Our business problem is to understand who was using what products. This is a cross-tab. What is this? This is something that will be used for categorical variables. No box plot will make sense here. There are no numbers. So now you can ask interesting questions here if you want to, and you can think about how to answer it. Is that, for example, you can ask a question, is there a difference between the preferences of men and women? Possibly. Is there a difference in the products that irrespective of gender, is there a product that they prefer? You can ask all kinds of interesting questions and you can find ways to answer it, which we will do, not in this residency, but next time around.
For those we can categorize it also?
Categorize?
For those preferences?
So this is simply, once again, this is descriptive. All this has done is it has simply told you the data as it is. What I'm saying is that if you want to do a little more analysis on it, you now have to reach a conclusion based on it. So for example, one conclusion to ask is that do men and women have the same preferences when it comes to the fitness product they use? Now that's a question. To answer that question, it's enough to look at the data. But just looking at it will not give me the answer. I need to be able to find a statistic to figure that out. A statistic that does what? That in some way measures that difference. Let's say measures the difference between men and women, or what we will do is not measure that. What we'll do is we'll measure that if there was no difference between men and women, what should this table have looked like? And then we'll compare the difference between these counts and that table. But that's the interesting part of a statistical statistic, which we'll do. That's called a chi-square test. It's coming up in the next residency. But that's the prediction part or the inference part of this description. This is just the description. You can do a similar thing here. This, for example, is for marital status and product. What product you use? Are you not very dependent on whether you're partnered or single? What is marital product versus product? Maybe it has to do with age, or maybe they're correlated. Should you use one as opposed to the other? Okay. You can use counts as well. If you say instead of doing it this way, instead of seeing it as a table, if you want to see it as a plot, you can ask for counts. So there are things like count plots and bar plots, which allow you to do counts. In the lab, you'll do probably a few more of these. This is simply another visualization of the same thing. For those of you who like things like pivot tables in Excel, Microsoft has made, wonders of us all. In corporate life, I was told that, you can have a master's in bachelor's and master's in anything, engineering is good, etc. And it's nice if you have PhDs in a few areas, but what you really need is a PhD in PowerPoint engineering. I mean, that's a necessary qualification for success. So certain tools have been used. So therefore, those tools have been implemented in many of these softwares as well. This is the pivot table version of the same data set. This is the last, not last, but still this is a plot. Let me show you this plot and then we'll end or we'll take a break. This is a plot that is a very popular plot because it is a very lazy plot. This plot requires extremely little thinking. Pair plot of a data frame, right? You don't care what the variables are. You're telling it nothing about the plots. You're simply saying, figure out a way to plot them pair by pair. And it does that. So for example, how would you read this plot? On this side, so it creates a matrix. The rows are a variable and the columns are variables. What is this? This is age versus age. Age versus age makes no sense. So what it plots there is a histogram of age. Doesn't like the gap. Nature abhors a vacuum. I suppose Python does as well. So it'll now plot what it should have plotted is age versus age. You're right, it should have been a 45-degree line. But a 45-degree line is a useless graphic, particularly if the same 45-degree line shows up in all the diagonals. So to make a more interesting graphic, it plots the histogram there. This analysis, this kind of analysis sometimes has a name associated with it. The name is univariate. Univariate means I'm looking at it variable by variable, one variable at a time. When I'm looking at age, I'm only looking at age. It's called univariate analysis. It's just a word. Uni as in uniform, same form, unicycle, cycle with one wheel, things like that. Univariate. Unit.
But for the other set of data also, will it replicate the same kind of pattern? If I'm going to give the other set of data.
Another set of data, it'll replicate the same nature of the data. There'll be histogram here again.
Age and education versus education, this time.
So yes, so what it will do is, remember that this graph, the nature of the graph, so let's see this. Right? So where is gender here? Where is gender here? Is it there? Is gender in my data? It is there. So when I did pairs plot my data, what did it do with gender? Yes, remember in info, when we did info here, remember how it had stored the data? No, not NaN, here. So it had product, gender and marital status, it had identified as objects in the data frame when it had formed the data frame. So now what does it tell you about the command, the pair plot command? Yes, it will ignore those objects. So in answer to your question, if the data frame has been stored, has been captured with integer 64, basically integers or numerics in it, it will plot. If it's only objects, it will probably give a null plot. Yeah.
So how come age is not a
Say again, age is not?
line, right? It's not a linear line.
Why like that? This is the histogram. This is the same plot. This plot is the same as which plot? This one. It's the same as this one here. No, this is not age versus age. This is just age. Age versus age would have been a 45-degree line, but it's not plotting that. It's not plotting that. In the diagonal, it is not plotting age versus age. In the diagonal, it is simply plotting age's own distribution.
With count. Age with count.
Yes, with the count. So what it is doing is, it is essentially running hist on age, on each observation, and putting it on the diagonal. Yes.
What can we infer from the histogram of like 20 to 25 bins?
20, say again?
There is a bin, right?
There is a bin.
So what can we infer from that? From each bin?
From each bin, it's a count.
Count of people in that age.
It's a count of the number of people who are in that age group. Here, this is age. No, this is miles. This is age. This is age. So let's say between here, let's say 40.5 and 43.5 or whatever these numbers are, there are 3 people. Remember, the histogram is a visual thing. You can data mine a histogram if you want to, which means you can find out what those are, and you can see it inside histogram. Just ask for a summary of that, it will give you what the features are of that histogram. But the histogram is not meant to be used that way. It's meant to be used as an optical device, to see the shape, to see the count. It's an art to do a histogram. If you change the bins a little bit, the histogram will look a little different. So I would suggest that unless you've got a lot of experience in this, or you really enjoy the programming, do not fiddle with the histogram. Its shape will change. I'll show you a little later after the break. Not change the histogram, but what shape is. No, not in default. You can go in and change it on size. But the bin width, etc., the bin width of histogram takes a little more to change. Right? So there is stuff out here. You can find other things in which you can play this. So there are ways to do it. Okay? So quickly ending, we're losing our food. So these different plots, and we'll continue after the break. The rest of it is simply an X versus Y. So for example, this is age versus education. This is age versus education.
So the second graph from the first one is just rotated.
Yes, he's right. If this is education on the y-axis and age on the x-axis, or vice versa, then these two plots, 1 and 2 and 2 and 1, are just mirror images of each other.
It's not a mirror image. No, it's just rotated.
You're right. Depends on where you look, where you put the mirror. But yes. Mirrors. So I remember when I was a kid, mirrors would confuse me. So I would ask a question like this: that when I see a mirror, left and right get switched, but top and bottom don't. And I never understood why. Due to gravity? You can think, left and right get switched, but top and bottom don't. I thought it was something to do with the mirror. And then I thought it was something to do with my eyes, maybe because they're left hand. So I looked at it this way, and that didn't help. So yes, it's an important point. When you do symmetry, it's a good catch. It's a good catch to realize that there aren't so many plots. there are actually only half as many plots, because the plot on this side of the histograms and the plot on the opposite side of the histograms are the same. There was another question that one of you asked, is that many of these seem to look like rows and columns. In the sense that, what are these rows? Now what does this row look, what does this mean? It means that this variable fitness actually has very few numbers in it. It has a number 1, 2, 3, 4 and 5. Now why is that? Because remember how I defined fitness is my perception of whether I was fit or not in my original definition of the variables. Here you go. Self-rated and fitness on 1 to 5 scale, where 1 is in poor shape and 5 is in excellent shape. This was the created data. So in this data set, I now have this variable in it. These kinds of variables sometimes cause difficulty in the sense that there's a word for it. These are sometimes called ordinal variables. So sometimes data is looked at sort of, numerical and categorical. And categorical is sometimes called nominal and ordinal. Nominal means it's a name of a person, north, south, east and west, gender, male, female, place, etc. It's a variable. Essentially it's a name. Ordinal it's also categorical, but there is a sense of order. There is a sense of order. Dissatisfied, very dissatisfied. So there's an order, therefore ordinal. This variable, the fitness variable, can, if you wish, be treated as an ordinal categorical variable. So for example, the Likert scale is that, so the 7-point scale. Not satisfied, very dissatisfied, dissatisfied, moderately dissatisfied, neutral, moderately satisfied, satisfied, very satisfied. Mark 1. This generates a data from a scale of say 1 to 7 or 0 to 6. So it will show up in your database as a number. Like for example, here you can say instead of 1 to 5, very unfit, moderately unfit, okay, relatively fit, very fit. Instead of giving 1 to 5, give it that way. And you code it up this way, your choice. So sometimes when you have data that looks like this, the Python or any database will recognize it as a number because you've entered it as a number, but you analyze it as if it is a category. So the opposite problem also sometimes exists in that sometimes you get to see a categorical variable show up as a number, but you know it's a categorical variable. A zip code is an example. A zip code shows up as a number, but it's obviously not. You can't add up zip codes, right? You take two places in Bangalore and you want to find a place between them, that's not the average of the zip codes. It might be close, but you can't do arithmetic with zip codes. The other difficulty with zip codes is that there can be many of them, which means that as your data set grows, the number of zip codes also grows. So the number of values that a variable can take grows with the data. And this sometimes causes a difficulty. Because what happens is that in the statement of the definition of the variable, you now cannot state how many categories there will be present. So you know that there will be more zip codes coming, you just don't know how many more zip codes will be coming. But you also know it's a categorical variable, so you can't treat it like a number. And so there are some special types of problems like zip codes that require special types of solutions. So the plot itself is a very computational plot. If it recognizes it as a number, it plots it. If you don't want to make it plot as a number, change it to a character. Most softwares, including Python, will allow you to do that. Now, this is in some way a graphical representation of it. For the end of this session, we can talk a little bit about the numbers associated with it. So here, for example, my data age, you can also go, dot age if you want to and things like that. This is the mean. 27.7888 is the mean. So you can extract it. There are functionalities of the mean that can be recovered, like trimming, etc., that if you want to. You can calculate the standard deviation. You remember the standard deviation formula? That strange formula that I wrote on the board? This is the standard deviation formula if you want to calculate the standard deviation. You can do this for other variables as well. This is an interesting plot. So I don't want to go too far into this plot, but it's an interesting plot. Right. In Seaborn, there's a warning on the code. This is called, or what they're referring to, is a distribution plot. So, this is a plot that tries to look at not what the data is, but what the distribution is. So, remember I was drawing these odd pictures like this, and drawing lines on it. Those were distributions. So, what it's trying to do is it's trying to go after the distribution of the data. Now, what does this mean? It means that it says this. It says that there is an underlying distribution of the age variable. This distribution is a distribution you do not know. However, you have a sample from that distribution. How big a sample? About 180 observations. From that sample of 180, can you guess at what that distribution is? In other words, can you give me a curve? It's an answer to that problem. And it gives a curve. Why is the raw data not enough? So the raw data is not enough, then this goes to the heart of what the statistical problem is because I am interested not in the age of this particular group of people. I am interested in the corresponding age of another very similar group of people. Why? What is the problem I'm trying to solve? I'm trying to solve the problem of who is buying my cardiac equipment. Now, when are these people going to buy my cardiac equipment? At some point in time? Okay. Now, what is my data? But for whom is this data? Who have I got the data for? Right, people have already bought. So I have a problem. My problem is, I want to reach a conclusion about my future customers based on my old customers. How to do this? What mathematical logic allows me to say something about the future based on the past? Yes. In short, the way to do this is to assume that there is what is called a population. We'll talk more later. At this stage, to assume a distribution. To assume that there is a distribution. From this distribution, I have seen a sample today. From this distribution, I'll see a sample tomorrow. The people are not the same. Because the people who are going to use my cardiac equipment yesterday are not what are going to use it next year. If it was the same, I'd never have a growing business. There's no point analyzing data of customers unless I want them to buy more things or I have new customers coming in. So what is common between my observed set of data and the data for my new customers? That commonality is what you can think of as a distribution. So he says that from this, can you give me a sense of what this distribution is? And from this distribution, I can think of other people coming. So what we'll do tomorrow is we'll talk about a few distributions, few specific distributions and how to do calculations in the distributions. For now, what this graphic does is it simply calculates that distribution for you. I'll explain very, very briefly how it does that. Won't go into too many details. What it does is, it takes the averages of points. Yes?
So you mean that for a sample, distribution cannot be done?
I'm saying that for a sample, Why so why is not the sample the distribution itself? Why am I not saying, it's a good question, why am I not saying, ignore the curve, why am I not saying that the original histogram, which I've seen 3 or 4 times before, why is that itself not the distribution? That's similar to the following question. Let's suppose that you have done a blood pressure test and you've gotten a few measurements. You've been tested twice today, let's say pre-prandial, before breakfast, after breakfast. Next week also you have done this. Let's say you have done this for whatever be a reason. You have done this, say, once a week for a month. So now you've got 4 readings. No 4 readings, 8 readings. Now these 8 readings, is that the distribution?
No.
You need to have a range.
Yes, so there's something that says, yes, if I want to understand what my blood sugar is and what it will be going forward if I do not get treated, then certainly there's a relationship between this and what will happen in the future. For example, if I behave exactly the same way, if I eat exactly the same way, or I exercise and not exercise exactly the same way, if I smoke, if my lifestyle is exactly the same as it is, I would expect my readings to be the same. But what about it is going to be the same and what about it is different, I don't quite know. Yes, it is true that those 8 numbers are a representation of the distribution, but they're not the distribution itself. If they were the distribution itself, I would be forced to say that in the next month, I would have exactly these 8 readings. But I know that's not true. But I also know that from these 8 readings, I can say something about what will happen next month. It's not that there's useless information there. So if my readings this month, for example, are, let's say 110, 120, 115, 125, let's say in good health, 130, etc. I know these are my 8 readings. I know with some idea perhaps that if things remain the same, next month they will not start becoming 220, 210, 215, 230. They will not become that. How do I know that? Because I have this readings this month. So the idea of a distribution is to be able to abstract away from the data the random part and the systematic part. And the systematic part is what remains as the distribution. Around it there's going to be a random variation. And that random variation is going to exist from data set to data set, like this month and next month, like this bunch of customers and another set of customers who buy cardio equipment, maybe from another branch of my store. If I am, for example, running, let's say, a chain of stores, let's say that I'm, I don't know, not to pick names, but let's say, I don't know, Reliance Fresh or something of that sort. And I want to understand how my stores are doing. Let's say I take 5 or 6 stores and I study them extensively. How do I know that those results are going to apply to the remainder of my 500, 600 stores? What is common between these 5 and the remainder? How are they representative of it? What part of it applies to the rest and what part of it does not? How do I extend it? How do I extend your blood pressure readings to the next blood pressure readings? How do I figure this out? That is the heart of statistics. That's called statistical inference. To abstract away from the data certain things that remain the same and certain things that do not. So a distribution is an estimate of that underlying true distribution of age. And so it's not as rough. It's smoother. How smooth is something that the plot changes, that the plot figures out on its own, like histogram. But you are free to change it. You are free to change it. There are functions within it, functions within this plot, and it's a fairly sophisticated function, which you can do many things with. I mean, it's a fairly sophisticated thing. There are many functions available within it. So, for example, this bin of histogram, this allows you to say where should the boundaries of those the histogram part of it be. Whether you want to plot it or not, whether you want to plot that what I was calling a distribution, the Gaussian kernel density estimate, it's a sophisticated way of saying the same thing. And there are functions available to put into that. So you can change this. It's one of the most sophisticated plotting functionals that you'll be able to see. I wouldn't suggest doing it now. Get a little more experience in doing this, but yes.
Slightly different ways you use Gaussian.
Gaussian will not make too much of a difference. What will happen is if there is no smoothing out here, it will look like a normal distribution. These little wiggles will go away.
I mean, it's better, gives you a smoother curve.
We will discuss that a little later as to when, maybe tomorrow, as to when it's a good idea to do that and when it is not. Just hold on to that question a little bit. We haven't talked about the Gaussian distribution yet. I'll deal with that when the Gaussian distribution comes. For now, what this is it gives you a visual representation, simply a descriptive representation of the underlying distribution. Hence a distribution plot.
So the distribution you always want to compare with the samples, 8 samples if you take an example.
Yes.
You've distributed them, then you're taking a current sample.
Yes, so if my distribution is correct, let's suppose in an ideal world, if my distribution thinking is correct, then here's what would happen. If I take my old 8 data and I do a histogram, I do a dist. In the new data, I do a dist again. These two should be very similar. The histograms may be different, but the distributions should be similar, if I've done my analysis correctly.
Does that mean the variance is?
I wouldn't use the word variance, I'd say variability. It means that there is a sum, this is called sampling variability. In other words, there's a variability that is due to the fact that you've taken a sample. There is an underlying truth, but you're not seeing that truth because you're taking a sample. There is an underlying level of your blood sugar, but you're not seeing that because you've taken only a very small sample of your blood, a few milliliters, where there are liters flowing around, and at only at a few seconds in time. There are many hours in the day. There are so many other things that your reading could have been. But if it is a good sample, then what would happen is that I'll be able to cover this variability. So if I want to get a sense of what your blood sample actually is and I want to sample this well, what I will do is I'll take samples in different kinds of situations. One thing they cover, for example, before eating and after eating, that they cover. Maybe I want to cover other things as well. For example, in certain kinds of diseases, they're very conscious as to where to take the blood from. Because the metabolism in the blood changes based on what? Certain diseases, and I won't mention what. For example, you draw the blood near the liver. The liver is the body's filtration system. So essentially you want to figure out the nature of the blood when it flows into the liver. And then after it flows out of the liver in order to understand whether the liver is filtering your blood correctly or not. Now to do that, you need to draw the blood in very specific places. So in order to do that, therefore your experimentation should cover all of that. What does that mean, for example, in business terms? Let's say that you're looking at sales data and you want to understand your sales distribution. Well, don't focus on certain salespeople. Look at your bad salespeople, look at your good salespeople. Look at your high selling products, look at your low selling products. Cover the range of possibilities. If you do not cover the range of possibilities, you will not see the distribution. And if you do not see the distribution, you will not know where the future data will come from. And if you don't know that, you will not be able to do any prediction or prescription for that. The histogram is just a summary. This is also just a summary. But the histogram summary applies to just this data set. This distribution is pretending to apply to a little bit more.
What is the definition of it?
Definition of?
Distribution.
The definition of a distribution doesn't apply to the data. So a distribution function, so to speak, is just this. So for example, it's sometimes defined this way. F of x is equal to the probability that x is less than or equal to x. This is sometimes called a distribution function. F of x is equal to the chance that age is less than or equal to say 15. Age is less than or equal to 16. Age is less than or equal to 17. And now let me confuse you even more. F of x, this is the derivative of x, the differential of x, is the density function, which is the area under the curve. This is called the density function, which is what this plot is plotting. This is sometimes called the density function. The density function, so the distribution function is the integral of the density function, and the density function is the derivative of the distribution function, if you're very mathy in all of this. So what they're plotting is they're plotting the density function. I showed the code. So this is actually called the density function. The reason I'm calling it a distribution function is because it says distribution here. I was hoping not to confuse you. Clearly I failed. Go ahead.
Given that solving this is 8 by 8.
Yes. That's the idea. Yes. Now you've hit the problem of statistics bang on the head. How do I get an idea of a distribution that applies to everyone based on only one sample sitting in front of me?
Lake, frozen lake. And then
That is the $1 million question, and that is why people like me exist. Right? That is the whole point of the subject. And it is a hard problem. It is a hard problem because you are trying to draw a conclusion outside your data. Nobody is interested in your data. Nobody is interested in your data. Right? Everybody is interested in their data or in their problem. Aapka मामला आपका ही है. Nobody is interested in your data. Now, but you still have to analyze the data that is in front of you and reach a conclusion that makes sense to them. The bank has to look at its portfolio and figure out what its risk strategy should be. The clothing store needs to look at its sales and figure out what clothes it should make. Great Learning has to figure out its course reviews and figure out which faculty members to keep. You have to look at your expenditures and figure out how much salary to negotiate for. How will you do all of this? How do you do all of this, by the way? Based on some sense of distribution, right? So when you go and you negotiate for a salary, now you're not going to negotiate for 100 crores. You might, but you'll say no one's going to give me that anyway. So maybe you're good enough, I don't know. But what you do is you essentially say, you do roughly something like the following. You figure out how much money you need and how much money you are expecting. And that to some extent is based on your expenditure and what you want to do. Your expenditure is also based on that. You have a certain income and you're spending based on this. You're doing all of this on a regular basis. You're standing on the road. Correct? You're standing on the road and you're trying to decide whether to cross it. How do you decide? Experience. You got past data and that data is telling you, please cross the road. How? That data has not seen that car. K533619 with his driver has not been seen by your data set. How are you crossing? Because you're making the assumption that while I have not seen him, I've seen many others like him. So there's this story, right? So a taxi driver is going at night on the road, etc., and he's just running left, right, etc. So red light, cross, no issues, etc. It just keeps going. The passenger is getting very scared. Stop karo ye. The driver, he says in Hindi, apologize for the language. Hum raaste ka sher hai. And I'm the lion of the road. Who will stop me? He goes through all the red lights. And then there's a green light. And then he stops. And then he says, why have you stopped? Now the guy says, raaste mein bahut sher hai. So the guy on the other side. So he's logical, right? So his data is saying that there are people who cross the red light. So therefore, if I'm standing at a green light, there's red light on the other side, cars are going to cross that red light, right? Very logical. So therefore, and we do this all the time. So while we are not trained as statisticians, at least normal people are not, they behave like one based on the experience. Now your objective and the objective of an analytics professional is to translate this logic into an algorithm, into a procedure that the company and the computer understands. And that is not easy. For starters, let's say that you are here and you say that this is an average, right? This is the mean age. This is 28.7888. And you could say that this is an estimate of the mean of the distribution. This is the mean of the data. But you are not interested in the mean of the data. Why are you not interested in the mean of the data? Because you're not interested in this particular set of 180 people. But you are interested in the average age of my customers. So now the question becomes, what does the age of my new customers have to do with the number 28? Are they related? Yes. you would say that they're like a copy of what I have. Now that's interesting. So if they're like a copy of what I have, then will I see 28.78 again? And now you will say probably not. They're a copy, but not that much of a copy. Most likely, now we are talking. So now, how likely is most likely? And what about it is going to be the same, and what about it is going to be different?
The y-axis of the distribution.
So the y-axis of the distribution you will say is the same. So for example, you could say that this 78.8 is an estimate of the population distribution, which means that yes, it comes from the histogram. It comes from the same data histogram comes from, but it also comes from this distribution. But there's also this nagging feeling that I do not know for sure. I do not know. I don't know what this new data is going to be. So what will happen is we will not give the answer 28, we'll not give the answer 28.7. We'll give an answer that is like 28.7 plus minus something. We'll say, I do not know what the population mean is, but I'm going to guess it's around 28. I know it is not going to be exactly 28, but 28 isn't useless for me either. It's going to be around around 28. How much around 28? Now certain criteria come in. What will this depend on? It will depend on the variation of the data. If the data is standard deviation, if the data is very variable, this plus minus will be large.
And the nature of the data, right?
Same, yes, the nature of it will depend upon how many things I'm averaging over. If this was 180, I'm so sure. If this was 18,000, I'll be even more sure. If this was 18, I'll be less sure. So it depends on how much data is being averaged over. The more data I have, the surer I am about the repeatability of it. The surer I am that I will see something similar again. It depends upon how sure I want to be. If I want to be 95% sure, if I want to be 99% sure, if I want to be 99%, the more sure I want to be, the bigger the tolerance I must have on my interval. And those are things we'll get to. So those are also descriptions, but those descriptions are heading towards being able to predict. So now if I give you this 28.78, I've given you a description of the data, but I've not given you a prediction. If I've now given you 28.78 plus minus something, I've now begun to give you a prediction. Today is about descriptive analytics. We're not predicting anything. We'll get there. But this plot is in some way a first measure of looking at this idea of a population and of a distribution associated with the population. Right? This is, yeah.
Variation is less.
If the variation less, this curve will be sharp. Flat means variation is more. If the curve goes this way, it means that there is a lot of variation. I'm unsure about the middle.
In that case, you can't give the proper prediction.
It's harder. You need more data.
No, if data is more, definitely the variation will be more.
Not necessarily. The variation of the average would go less. So let's suppose that you have no control over your diet. I'm not accusing you of anything. It happens to humans. But let's suppose that you are doing a job in which your lifestyle is very varied. You travel from place to place, you eat in different hotels, sometimes you don't eat at all, sometimes you stress out a lot, sometimes you're naturally going after trains, and sometimes you're sleeping for 12 hours in a row. Your life is highly variable. Now let's suppose, and there's nothing wrong with that, many people have very varied lives. But let's suppose I'm now trying to measure the blood sugar of such a person. What must I do? Now, try to other variables, or at the very least what I need to do is, if I simply want to get a good blood pressure measurement, is I have to measure it under many different circumstances. Or I could argue, I don't control your circumstances. I can control your circumstances. So I can say, for example, that go and measure it at this time, or go and measure it. Take a glucometer, and before going to bed, do this. Or after you've just had a very hard day, do this. I can give certain instructions to cover all the corners. Or I can simply say, I don't know, but what you need to do is you need to measure your blood pressure, or sorry, your blood sugar, say every 6 hours. And then tell me what happens. But you need to do this often, because I expect your blood sugar to be highly variable. Simply because your body is being put through an enormous amount of variation. In a business situation, let's suppose that you've introduced a new product. You do not know if this new product is going to sell or not. What will you do? I mean, how will you measure it? You've just introduced it. Based on past data, you'll do that, but you've just released it. You can measure current data. No. Different situation. I've just released the product. All that is over. All that is over. I now have just released this watch in the market. What typically happens is people track the market very, very closely. Number of hits to the ads, the number of sales made, everything. The reason is because they're not sure how much this will sell. See, the question is what changed? What changed was your product release. Now the competitor could be reacting immediately. My point is not that there are many things to look at, which you should. My point is that when there is a change in the distribution, when there is an unknown distribution coming in front of you, whose variation you do not know, you tend to get more data. You sample more frequently, or you get more data. You figure this out. We do this all the time. For example, let's suppose for those of you who have kids, let's suppose your kid is going to a new school. What will you do? You'll ask more questions to them. You'll get more data. You'll find out what is happening in school. What are the teachers like, etc. Because there's too much variability standing in front of you. Now with those answers, and then you do a few trips to the school, you're now a little more, you know. You may like it, you may not like it. But you're at least more informed. That distribution is now known to you. So you get more and more data. That's why you get the experience. That's why you start getting that experience. If you have that experience already, in other words, if you know the distribution very, very well and you're comfortable with it, it'll take time to get there. And that's why this big data world is becoming so interesting, that by the time you have understood a problem, the problem is not important anymore. There's a new problem. Now this is good, right? That's why you guys have jobs. But it also means that the answer to that also means that when you have new data, you solve a different problem. You don't solve the older problem better. Which is what a statistician to some extent is trained to do. That as you get more and more data, get the distribution better. Get a better idea of the unknown. Make a better product. But the alternative view is, make another product. Solve a different problem. If you have more data, so the CEO is now saying, I have more data, give me more. More of what? Solve another problem for me. Give me new customers that I can go after and things like that. So therefore, that problem is a problem that statisticians, big data people often, and it's not an easy problem to go after. That as you have more and more data coming in, how do you utilize it? How do you make efficient use of this information? Do you get tighter estimates of what you're going after? You're doing sentiment analysis of text. Many of you will do text analysis. You'll write, Twitter code in Excel, and you'll do latent semantic analysis. You'll look at positive net sentiment scores and things of that sort. And now the question will be that you know that this is going to change. People's opinions are going to change. Correct? So, over what granularity do you expect people's opinions to stay the same? Do they change every day? If they change every day, there is no point looking at a person over an average of days, because that average is nothing. Every day is a different opinion. On the other hand, if their opinions change, let's say on a monthly basis, then you can look at daily averages and average them. You'll get a better estimate of that monthly rating. So you have to make a guess as to whether I'm estimating a changing thing or whether I'm estimating a solid thing better. And that's not an easy thing to do. I know it's happened to me, I don't know whether it's happened to you or not, but there are times in my life where I have simply not had haircuts. What that means is, I've gone 6 months, 8 months, a haircut has been like a weight loss program. Right? I've not cared what I look like, I'm not sure I do now, but when things become very unhygienic, I go and get a haircut. There have also been times in my life when I've been a lot more conscious of what others think about me. You can imagine what points in my life. So now I groom, I'm very careful, I get my hair done and I'm all correct and I'm getting my hair cut much more regularly. Now what am I doing? So in the second case what I'm doing is I'm trying to make sure that I'm reaching a certain distributional standard. There's a certain target distribution that I have and I'm interested in getting there. I'm intolerant of variability. I'm saying that I'm going to estimate this distribution and I'm going to stay close to it. In the first case I was not. I was perfectly okay with the variability. And in certain cases you will be okay with the variability and you will not want to estimate a distribution of this type. And in certain cases you will. You will want to estimate it very, very well. You'll want your hair to be done very correctly. You'll want your product to be targeted to a very specific age group. You'll want to know that when I am targeting to this particular age group, what advertisements do I want to show? You'll want to advertise it on television. And you'll want to know who is watching the program on which you're advertising this. Are they college people? Are they professionals? Are they old people sitting at home? Who will use this? And therefore, where will I advertise my cardio product? There are times when you'll want to know this very, very precisely. Or as precisely as you can. So therefore, this number, this mean number, and this number from a description perspective, is perfectly okay. It is just the average. But from an inferential perspective, it's just the beginning of the journey. It's just one number. And we're going to have to put a little more bells and whistles around this. Go ahead, you have lots of questions clearly.
Usually what we read is that a variable with not normal distribution should not be taken further in the study.
Okay, so we haven't talked about normal distributions, we will do tomorrow. But, so statisticians need to make assumptions about their data. One of the assumptions is what he's talking about. It assumes a certain distribution. It says that I'm going to assume that the data has a normal distribution. It's an assumption. Now why do statisticians make assumptions like that? One reason they make assumptions like that is because they make it, the calculation becomes easier. Now just because the calculation becomes easier doesn't mean the calculation is correct. Because if the assumption is wrong, the calculation is also going to be wrong. But because of the assumption, you can do many of these calculations. And if you don't make those assumptions, these calculations now become difficult or even impossible given the data at hand. So a lot of the tests and a lot of the procedures that we'll be talking about are going to make certain assumptions. We'll see one in about an hour or so. And if that assumption is correct, I will have a strong model. But if that assumption is wrong, I will still have a model that is indicative. So there was an economist, I think Paul Samuelson, I'm not entirely sure who, but someone who said, no, George Box, I think, the Box. He said that all models are wrong, but some models are useful. Right? So the question is, it may still be useful. If, in many cases, the distribution is expressly allowed to be not normal, the domain tells you that. Let's say that you are in an engineering domain, you know the data has a certain shape. And the engineering domain tells you that it's a shape, and the shape is sometimes called a Weibull distribution. What that means is that if you are reporting out, let's say, the failures of something, you're reporting out the failures of gas turbine blades. I've spent a number of years doing that. We had to report out a Weibull distribution. We didn't report out a normal distribution, we had to report out a Weibull distribution. In the finance industry, you report out a log normal distribution, means and variances of it. Every industry has its own favorite distribution, because every industry has its own generic data form. Now, even within the industry, a particular data set could violate that rule. And then it becomes interesting that as a statistician, do you now use a higher power tool set, a more powerful tool set to solve that? This leads to certain complexities. The first complexity that often runs into is which one, and do I do it differently from someone else? Is literally like a doctor who looks at a patient and says that, you know what, the textbook says that I should do it this way. But I like this guy. He looks different. I've never seen anyone like him before. So let me ignore the textbook and treat him this way. I think he'll get better. Now, could I be right? I could. But I'm taking a risk. So every time you're making an assumption on your own and following through on it, you're taking a very similar risk. You could be right for that particular case, but the precedence, you have far fewer precedences to go on. And as a result of which, later on when you extend it beyond to someone else, you're going to find it hard to do so. So therefore, people often make assumptions on distributions in a sort of historical sense, that they've known that this has worked moderately well over a period of time. And they're very hesitant to change it for particular cases. Sometimes they're not allowed to. In regulatory terms, they're not allowed to. Any accountants here? Accountants, right? So accountants, so you know this. So if you're an accountant, you have to do your books in a certain way. Right? Let's say that you're measuring cash flow. There is a certain way in which you will measure cash flow. Right? Now, you may say that in this particular month, your business was done a little differently, so I'm going to show better cash flow this way. If you can, you know you're running into trouble. Now, you may be right. You may be right in the sense that that may actually be a better way of doing it. But as soon as you go out of CFA, as soon as you go out of a very standard way of doing things, things will be a problem. And the same kind of logic applies to often statistical analysis as well. So as a result of which, like an accountant, you are doing the right thing approximately most of the time. In machine learning, there's a term that you might see. There's a term that's often called, like supervised, unsupervised, etc. It's called pack learning. Pack learning. It's a deeply technical field, and PAC stands for probably, approximately, correct. Probably, approximately, correct. I'm not telling you anything. If I'm wrong, don't blame me. But I'm probably, approximately correct. And the probabilistic part comes from statistical thinking. The approximately part comes from machine learning thinking. And it's a deep field. It's a serious field. But it puts a probabilistic statement or an approximation. So therefore, at the end of the day, whatever method you use, there has to be a sense of how generalizable it is. You will do that. You'll do that fairly soon. In a couple of months, you'll do your first hackathon. In your first hackathon, all your hackathons will have a certain field to them. A common field for a hackathon is, I'm going to give you a data set. You build your model on the data set, and I am going to have a data set that I'm not going to show you, and I'm going to tell you how well your model has done on my data set. And you have a day or 6 hours or whatever to fiddle around with your data set and show improvement on my data set. This is what you'll do. You'll do it twice, I think, in your schedule. What does that mean? It means that by being very good on your data set doesn't necessarily mean you are successful. You have to be good on my data set, but I'm not going to give you my data set. This is not as impossible as it sounds. This is a very standard problem, and this is a typical problem. You will not find this hard. You'll find this very easy by the time you get there. No, not a problem. You all will. Your predecessors will. You will. You'll get 90, 96, 99, whatever % accuracy. Not to worry. Technically, this is not hard. Right. So there are two answers to that. One is, if the mean is different from the median, then you ask no. Mean being equal to the median from a distribution sense means that these are the two numbers. Okay. If the distribution looks like this, and I have a parameter mu, we're going to do this later. When statisticians use a Greek letter, they're referring to something that they do not know. Right? It's all Greek to them. So mu is a population parameter. It exists, but it is unknown. It exists, but it is unknown. Now, if the distribution is nice and symmetric like this, then this unknown thing in the middle can be estimated using a mean, or it can be estimated using a median. Now, the question becomes, which is better? And the answer to that, roughly speaking, is this, that if there are many outliers, if this distribution tends to sort of spread out to the tails, then use a median. Because of the reason that I said, the median becomes stable to outliers. If this distribution has a more bell-shaped curve of this particular kind, the mean is more efficient at this. A better answer is, what if the nature of the distribution is not that, but it is like this, then the median may be here and the mean may be here. Now you're asking different question. Now it's not a statistics question, it's a common sense or a science-like question. Which one are you interested in? Are you interested in per capita income, or are you interested in the income of the typical Indian? Correct? For example, let me ask you this. How much time, or give me one number, one representation of the amount of time that you spend on a website? I'm asking for one number. Don't tell me the number, but think in your head as to how you would answer this. How much time do you spend on a website? By a website, what I mean is this. Yes, but what does average mean? So how would I do this? So here's what I'm asking. You're cruising the web every day, let's say. So what I'm asking for is a number like this, and the amount of time that you spend on a website, you go to different websites. And you spend a variable amount of time on each of these websites for whatever be your purpose. Sometimes you're just passing through, sometimes you're seeing a video, sometimes you're sending an email, blah, 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 whatever. And every session I'm thinking of as a different website. And if you go to Google twice, then I'm thinking of that as two websites. So session wise, so to speak. Now I'm asking for a representative number. So how would you come up with that number? What's a fair answer to that? A mean. So if I do the mean, here is how I would do it. On a given day, so the first website I've gone to, I'll find out how much time I spend there. Second, how much time I spend there. Third, how much time I spend there. Fourth, how much time I spend there. And then add this up and I divide. That's the mean. Right? What would be the median? The median would be, I'd look at all those times and I sort it and I'd put this in. Which is going to be larger? It depends, is correct. But in this particular case, so think of your typical browsing habits. Now everyone's browsing habit is different. But just think of it. And people who deal with network traffic deal with this problem on a regular basis. So here is what usually happens. Most of your sessions are actually quite short. For example, a query. You go to a website and you post a query, or you go to your Gmail and you check whether there's been a new email, or you go to a favorite website, news site, and see whether something new is there or not. Most of the actual pages you visit, you don't spend a lot of time on. But sometimes you go to a website and you spend a lot of time on it. Let's say you write an email, let's say you see a video. So what does your data look like? Many small numbers and a few big numbers. This is what is called a heavy tail distribution. The histogram sometimes looks like this. Heavy tailed. This is the right tail. This is called a tail of a distribution. A tail to a statistician is not an animal thing. A tail usually refers to the end of a distribution. Some called a heavy tail distribution. And network traffic is an example of, a typical example of heavy tail. So now here is what happens. People in this particular case, the mean and the median are carrying very different kinds of information. The median is essentially saying that for a typical website that you go to, how much time do you spend on a typical website? Now, if that number is low, that is an indication that most of the time you are, shall we say, cruising or browsing. On the other hand, if you're looking at the mean and that number is high, then you know that you're spending a lot of time on certain very specific websites. And this points to two very different kinds of people. So the mean and the median are carrying different kinds of information with them, both useful. So in answer to your question, it depends on what you're going after. And in certain things you will see one of them being naturally used as opposed to the other. There's also a third one called the mode, which is actually harder. When we were statistics students, we would study mean median mode. And the mode is the peak of the distribution, what is most likely. And the reason the mode isn't talked about much is because the mode actually algorithmically is very hard to get at. The mean is a very simple algorithm. The median is a very simple algorithm. The mode is a harder algorithm. You can think about how to write a program for the mode if you want to. It's a much harder algorithm. So the mode essentially, what is the mode of this distribution, for example? So let's take a look at one of them. This is what? This is income for men. What is the modal income? The modal income is here. It's somewhere around 55,000, where this maximum is. Correct? For women, it's here, maybe just less than 50,000. So you understand what the mode is. It is the highest frequency or the most common value. But in practice, that's actually a little difficult to do. If I give you a set of numbers, how will you calculate the mode? But will you see a spike? What is a spike? So I'll give you all your ages. How will you calculate the mode? So one possibility is you will look at the age and ask which age is the commonest.
Where the count of the age is.
Where the count of the age is more. But that almost means that your data is not numerical. You're almost thinking of the data as being categorical because you're counting how many observations there are at a value. The idea of a numeric is that it is sort of continuous. It's not chunked that way. So for data that is chunked up or categorical, you can easily calculate the mode. For something that is not. And so the mode therefore has become less fashionable because it's not a very easy thing to go after. When we were in college, the mode was something actually quite easy to calculate. Here's the way we would calculate the mode. Here is the histogram. And the way we would calculate the mode is this. We draw a line from here to here. We draw a line from here to here. Left to left. Take the highest class. Draw this cross line, and here is the mode. This is the way we would do the mode in the pre-computer era. Right? I went to college where we didn't have any laptops and things like that. Running a program meant running to the computer center with pieces of paper. So many of these things were done by hand, and this is something very easy to do by manually. This is not that easy to do on a computer. The logic is twisted. You have to figure out what the bin width is. Therefore, you have to make, therefore his estimation of mode and his estimation of mode will be different from the same data set. That is not going to be true for the mean or for the median. And as soon as two different people find the same answer to the same, different answers to the same question, you know there's a problem with the statistic. So therefore, this is, so the mode isn't done as much these days. These are the histograms, sort of my data histogram. This is a way of separating out the histograms. In other words, looking at the histograms by different column equal to income essentially means that which variable, the by says which gender, so it's, and they go side by side because they essentially tell you as to what the difference in the distributions is. So what does this tell you? I could have plotted a disk plot here as well, or the code could have, but this says that there is a little bit of a difference between the male and the female distributions in shape as well as in the actual values, so to speak. And so from a descriptive perspective, you can keep doing analysis of this kind to see whether there is a difference, not just in gender variable, but in other variables as well. Do people travel the same amount of miles on different devices? A plot like this will tell you. To compare these two, what we can do in next residency, or you can do as an assignment after that, is you can say, is there a statistical difference between the miles of products that are traveled or that are used for between the different products? In other words, is there a difference between these three products in terms of how much usage they see? And you can compare three distributions, and we will compare three distributions in time. Okay. Now the last idea I want to talk about today is we've talked mostly about univariate, which is one variable. We saw a little bit of a plot, but I want to talk about, shall we say, bivariate. Bivariate means two variables at a time. If you want to talk about many variables at a time, that's called multivariate. But before we get to many, let's get to two. So we've looked at one notion, or we've looked at two notions. We've looked at the notion of location. Location means that if there is a distribution, what is its middle? And that can be mean or median. We've looked at variation, like standard deviation range and interquartile range. But when I look at distributions of two variables, there's a little bit more to it. There is a relationship between the two variables that I want to be able to capture. A sense of relation or a sense of correlation. That how do I measure whether one variable is related to the other variable or not? Remember, I'm still describing. I'm still trying to find a number. Like a mean, like a standard deviation, I'm trying to simply describe a number. If that number is this, correlation is high. If that number is this, correlation is low. What should that number be? There are many, many ways of defining such a number. Here is one, and is there in the book. Let's suppose, so I'm going to do this slightly abstractly. So I've got numbers that look like this, x1, these are my points. So for example, if I look at, say, a plot here, let's take one of these. This is, say, miles and income. The amount of exercise done and income. Each of these points has an x coordinate and a y coordinate. These coordinates I'm calling x1, y1, x2, y2, x3, y3, x4, y4, x180, y180. You understand? They're pairs of observations. This is, say, x1, y1. This is, say, x2, y2. This is, say, x3, y3. They're pairs of observations this way. Right? Now, x bar is what? 1 over n, x1 plus xn. And I'm going to write this simply because I'm going to have to write something a little more complicated now. Summation I is equal to 1 to n xi. If you don't like the sigma notation, that's fine. You can write it with dots. Why add a little complexity here? Y bar, which is the average, is similarly summation I is equal to 1 to n yi. Okay? Now I'm going to write something here. I'm going to write summation xi minus x bar yi minus y bar. I'm going to write that down. I'll tell you why I'm writing that down. But look at that. What is xi minus x bar? It's sort of like a variation or a spread of xi from its average. Similarly, yi minus y bar. Okay. Now, when is this term xi minus x bar, yi minus y bar, when is it positive? When both of these are positive or both of them are negative? Right? Now, both of them are positive means what? Both of them are positive means xi is above average and yi is above average. right? Both negative means xi is below average or yi is below average. So, imagine a data set that looks like this. Where is x bar and y bar? Somewhere in the middle here. Here is one line, or here is a line, and here is another line. For all the points here, xi is above its average and yi is above its average. For all the points here, xi is below its average and yi is below its average. Which means all these terms or most of these terms are going to be positive. I may still have a point, for example, say this point where it is negative. But when my data looks like this number will be positive. What happens when my data looks like this? When my data looks like this, then xi is above its average, yi is above its average and xi is below its average. That means one of these is positive and one of these is negative. That means this guy is negative. So when the data looks like this becomes negative. What happens if the data looks like this? The positives and the negatives will, this number being negative means when one is high, the other is low. For example, let's say height and weight. Height and weight means what? The taller you are, the heavier you are, the relationship between the two. My doctor says that I'm about 4 or 5 kilos overweight. I say, no doctor, I'm about 2 inches too short. I don't have a weight problem, I have a height problem. Your interpretation. So therefore, if you want to therefore get a statistic that captures whether your data, whether your variables are moving together or in opposite directions for example might be something like say weight of a car and mileage of a car. Bigger cars have lesser mileage, which means that if you have an above average weight car, that probably has a lower than average mileage. So this particular measure this is an addition. When I divide it by 1 over n minus 1 to take an average effect, this thing is called the covariance of x and y. This is called the covariance of x and y. Covariance are very heavily used in certain areas. They're heavily used, for example, in dimension reduction, in principal components. You'll see that in time. They're used in finance, in portfolio management and things of that sort. This is called the covariance of x and y. What is the covariance of x and x? The covariance of x and x, which means instead of y I'll just put x. This becomes 1 over n minus 1 summation I is equal to 1 to n xi minus x bar into xi minus x bar, which means xi minus x bar squared, which is the square of the standard deviation. This is sometimes called the variance of x, which is the same as the standard deviation of x squared. So that thing that before I took the square root, that's called the variance. With the square root is called the standard deviation. Without the square root it's called the variance. By the way, it's all there in the book. So in case you didn't get it, you can see the video or you can read the book, or these are very standard definitions. So the covariance is a measure of the nature of the relationship between x and y. If the covariance is positive, they're moving in the same direction. If the covariance is negative, they're moving in opposite directions. If the covariance is 0, then many things can happen. Either the data looks like this, there's no relation, or maybe the data looks like this. Not a normal distribution. This is not a distribution. This is, say, price and profit. For example, what is the relationship between price and profit, by the way?
Price increase, sales down.
So this is the theoretical relationship between price and profit. On this side, as price goes up, your profit increases because you're getting more money per product. And on this side, with even higher price, fewer people buy your product. So your profit goes down. Now for such a thing, the average is somewhere here. So the correlation also becomes 0. Another way to think of it is positive on this side and negative on this side. So if this is 0, it doesn't mean that there is no relationship. It could mean that there is a complicated relationship. Something that is positive on one side and negative on the other side, and not that simple. I once remember doing an analysis in which we were trying to find out, it was about attrition, why people leave companies. And inside it there was a model where we were trying to, for some reason, trying to find out the relationship between, or trying to understand where people stay. Do they stay close to the office or do they stay far away from office? And now what do you think is the relationship between, say, experience and distance to home?
Higher the experience, closer the distance. Higher the experience, further is the home. No, because if I have home very far.
Tenure or experience? Okay. We had normalized for that. In other words, think of it as just experience, but we were looking at populations in which experience loosely translates to age. But you're right. There could be people who join the company very old. I agree with that. But let's simplify life and say that you have a data set in which you experience. And here's what we found. That early on in their careers, people live close by. In the middle, they moved away. And towards the end, they again became closer. Now, this was an observation. There's no science to this. This was just simply seen. In that particular company, this particular thing would happen. But remember, the point is not to describe. The point is also to predict, to understand and things like that. So we had to build a story around this when we went to the CMD and said that, here's what we had done. So you can make up a story around this. And the story we made up, correctly or incorrectly, I don't know, is that in the beginning, to some extent, people have low dependencies. You typically coming, you're unmarried, bachelor, etc. You're also ready to work a lot harder. So staying close by is convenient. You get a PG or you get an apartment, you stay close to work. Because staying further away from work gets you no particular benefit. It's just inconvenient. But as you reach in some way middle age, so to speak, things become very complicated. There is a spouse here, she may have a job, there are kids, there are schools, there's kinds of houses that you can afford. And so this solves a more complicated optimization problem, and you may not be able to find a solution to that problem close to work. But people who survive even longer in the company earn enough to solve this problem through other means. And then what happens is they move back to work again. Buy a villa close to, etc. And now there are multiple cars to take people elsewhere. Kids are often grown up. So the number of dependencies are a lot less. You may agree with the story, you may disagree with the story. But the point is that there's a complicated relationship you're trying to explain based on what the data is. Now the use of it, I won't talk about much. So this number is a number whose sign, positive or negative, tells you about the nature of the relationship. But only the sign tells you. The value is much harder to interpret. The reason is because I can measure these things in whatever units I want. Suppose I'm measuring, so height, say height and weight. And I measure height in centimeters and weight in kilograms. That's one answer. But I can measure height in feet and weight in pounds and get a different answer. I can even make this number much higher by measuring height in millimeters and weight in milligrams. I don't know why I do that, but I get. So this as a value is entirely dependent upon the units of measurement, which makes it a problem. So what statisticians do when they reach this situation is that they normalize things. They make the unit go away. So the way the unit goes away is you divide this by the standard deviation of x, and you divide this by the standard deviation of y. Now I can do this on the board without writing anything again, but I would suggest you write the whole formula again. When I divide this by the standard deviation of x and the standard deviation of y, now the units cancel out. Now this value becoming 1 means xi is 1 standard deviation above average in whatever be its units. And yi is say 2 standard deviations above average in whatever its units. The unit has gone away. This number is called the correlation between x and y. And the correlation between x and y is a number between is a number between -1 and 1. The correlation is between -1 and 1. If the data looks like this, then it is 1. If the data looks like this, then it is -1. This is the correlation. It is a measure of the relationship between two variables, measured in this very peculiar way. It is not just a measure of the relationship, it is a measure of what I would say the linear relationship between x and y. A non-linear relationship or a strange relationship could cancel out positive and negative and end up with 0 or a low number. So if the correlation is close to +1, there is a strong positive relationship between the two. Strong positive relation means what? If one of the variables is above average, then the other is also very likely to be above average, and vice versa. So what I can do is this is the, when I do my data and I do .cor as a function, right? This gives what is called the correlation matrix. Again, it will calculate it only for the things with numbers. If it doesn't, in other words, if you give it a data frame and this doesn't happen, then just make sure that you only take the subset of it which has only the numbers. Do not calculate correlations for things that aren't numbers. If they're not numbers, there are other ways to calculate association. We'll see that later as well. Now, based on this, what do you see? First of all, the correlation between age and age is 1. Why? Well, it's the 45-degree line, right? By definition, it is 1. That this is a number that comes from one data set with one kind of relationship. What does that say anything about the practical world, so to speak? It's another way of saying what I've been saying all along. How does your data have anything to say about these relationships outside the data? The problem is a little clearer here maybe, but the problem exists for anything. So for example, there is a correlation of 0.28 between education and age. 0.28 means that there is a positive relationship, but not a very strong one. Where is that graph? This is age. Education was the second one, right? So this one, right? Or this one, whichever way. This shows that there is a weak positive relationship between them. When one goes up, the other does have a slight tendency of going up. Now I should warn you that there is no sense of causation here. There is no sense that if x goes up, then y goes up. Because correlation of x and y is the same as the correlation of y and x. Definition. This is a symmetric concept. It makes no attempt at causation. That's a different thing altogether. So this is a positive. This is a positive relationship. It's a weakly positive relationship. This is about usage and education is about 40.4. Income and education is about 0.62. Miles and usage is about 0.48. Miles and fitness is about 0.78. Let's see miles and fitness. This is miles and fitness. Nothing in this data set has a negative correlation, but you might have seen it if one was negatively correlated to the other, negatively related to the other. Close to 0. So you're looking for low correlations, right? So age and usage, for example, is a very low number. Age and miles. In other words, age doesn't seem to have much to do with things, shall we say, other than income. But age and income doesn't really have much to do with your product per se. It will be useful in when you do clustering later on. Variables like that are useful to try and segment. Rich old people. Always an interesting segment. Yes.
So, correlation is 0. What is it?
Correlation means 0, that there is no relationship between the variables. It could mean, for example, that a plot that looks like this. Let's pick a variable. So, closest to 0 is what? Age and usage. So age and usage is where? Usage and this one? No, this is age and miles. That also is something low probably. This one? No, there is no relationship between them in the sense that there probably is a relationship in the variability. In other words, there is more variability here than here. But if I want to draw a line through this, the line doesn't have a positive slope or a negative slope. There's no idea that says that if one of them is above average, the other is also likely to be above average. So low correlation means that there is no sense that one being above average related to the other being above average. No increasing, no decreasing. Correlations are notoriously hard numbers to interpret, but they're also very useful summaries, particularly for large data. The question that he asked is does this make any sense in the real world has two components to it. Component 1, is your relationship between the two related to a linear concept? So for example, I was talking about height and weight. What should be the relationship between height and weight? Linear? So if I plot height versus weight, I should see a straight line. Okay? Now she's going to say, not necessarily. Okay. Removing outliers. We're all outliers, aren't we? Okay. Have any of you heard of a concept called the BMI? Body mass index. In this day and age, you have all heard of body mass index. Kya hota hai? What is body mass index? Height by? No, there is no age in it. Height by weight squared. Height by weight squared. Now, so BMI is height by weight squared. Now, if BMI is height by weight squared, what does that tell you about the human body? Height by weight squared is what is called BMI. And this number, let's say, should be around 25 if you are healthy. What does that tell you? If you are taller, what will happen? How should your weight increase? No, there's a square here. Half the rate. So roughly this should mean, let's say that this is correct. Let's say roughly that this is correct. If this is correct, what does that mean? It means that height is approximately 25 into weight squared if you are healthy. That means if I see a bunch of very healthy people and I plot their height versus the weight, I should see a curve like that. Not a straight line. She's figuring this. She's saying, now why? If I'm twice as tall, I should be twice as heavy. Yes, if you want to give it a fancy name, correct. No, you're right. That is a parabola. Undoubtedly true. Now you could argue as to why is it height by weight squared? That's a slightly different question. Why isn't it, say, weight by height? So let's suppose that so weight by height means what? So let's suppose that these two, they're not the same. Well, let's suppose that so these two, so this is a certain height, this is a certain height. If I put this on top of this, what happens to the weight? If these two are exactly the same, this is going to double. Or if I take two of these, I don't see two of them, I apologize, but anyway, okay. So here's one more. So these two, so if I put this on top of this doubles. So therefore, if I look at objects such as this, then by doubling the weight and doubling the height. So height by weight remains a constant, correct? So if I'm looking at BMI for bottles this way, it should be weight by height. So if you were a bottle, your BMI would be weight by height. Okay. Now imagine that you are a football. Now if you're a football and your height doubled, how much bigger would you be? You understand the problem? Is a football, it is now twice as high. How much heavier is it? By a factor of what? So the height has doubled, volume has gone up by what? No. Pi r what? No. 4 by 3 pi r cube. It has gone up by a cubic factor. So now for a ball, the BMI should be weight by height cubed. So you're not growing like a cylinder and you're not growing like a football. You're growing like something between a cylinder and a football. We all are, not you personally. So, which is why it looks like that. Right? Babies grow like cylinders. We don't grow like cylinders, because if we grew like cylinders, we'd be a lot thinner. Think of yourself, imagine yourself when you are, 5 or 6, and now double your height. You'd be a lot thinner. Right? Similarly, you don't grow like a football as well. Imagine yourself at 5 or 6, and now imagine you grew in every dimension in the same way. You'd be a lot fatter than you are now. So therefore, this relationship depends on the empirical relationship between height and weight for the data that is available, which is of humans growing. And so empirically people have discovered that this is the object that should be invariant. This is an example of what's called dimension reduction. Two variables are being combined into one, which is carrying information for you. But it relies on a nonlinear relationship between the two that is not going to be only picked up by the correlation. So the correlation goes so far and no further. It is not one of the more analytically useful things. Very often we do test a hypothesis. Is the correlation 0 versus is the correlation not 0? To ask whether the correlation is real or what is often called spurious. And in a later class, I think about 2 or 3 residencies from now, you'll spend some time on things like spurious correlations. In other words, I'm finding a relationship between X and Y, but is it real or is it due to something else? Yes, it could start as a basis for a causation. It gives you some summary of the data. It is at best a descriptive measure of association. Sometimes people want to see it in another form. This is what's called a heat map. It is exactly the same thing as a correlation, except that in a heat map, it gives you nice colors. It gives you nice colors. And you can change those colors, so to speak. Here's the index of what the color is. -1 is pale blue, positive, etc. And positive was in the same direction. So it gives you a sense of what the color is. So sometimes when you have lots and lots of variables, this is too few a set of variables for a heat map to be useful. So for example, let's suppose that you're looking at a product catalog, a few thousand products, and you're trying to find the correlation between sales of those products across time and across geographies. And you give a display of, where, and so you do a heat map and you find those regions where the products are sort of clustering up. We often do it in medicine through what is called microarrays, where essentially we look at data from genes, and let's say there are thousands of genes, and you look at the expression levels of each of these genes, and you say these are the genes that have been expressed, and these are the genes that haven't been. So if you are doing correlations of thousands of variables or hundreds of variables, often a nicely arranged set of variables with a heat map gives you a good picture of the data. So heat map in this form is exactly the same as a correlation, except that it adds colors to the numbers. So that you're not looking at the numbers, you get a visual picture of it. So the traditional choice of it is hot is related. So red is related and white is not. But there are many ways in which you can change the coding of the heat map's colors. Okay, now comes to some extent a tool that is descriptive. However, it is the first predictive tool that you will see. I will not want to use it like a predictive tool, but I'll still show it. So let me show you what the end product is. The end product is, I want to summarize the relationship between, say, miles, usage and fitness, variables like these. Right? Now in relationships of variables such as this kind, here's an equation. Miles is equal to minus 5.75 plus 20 into usage plus 27 into fitness. This is, shall we say, a targeted equation. What is this equation? As far as I'm concerned today, this is a description of the data. But the description of the data will be used in order to predict how many miles my instrument will run. So, think of what the instrument is. The instrument is an engineer designed instrument, and I'm trying to figure out how much it will be used, how many miles it will be used. To do that, I will figure out whether people consider themselves fit or not and how frequently they use it. And using that, I want to get an equation for the number of miles this will run. Is there a descriptive way of getting at that equation? So, what this does, this kind of an equation, it's what's called a linear regression model. This is your first model. This is going from descriptive to predictive. I haven't done it yet. I'm just saying what I'm trying to do. Self-rated fitness on a 1 to 5 scale. I'll get there. Okay, so maybe I shouldn't have shown you the output. Always dangerous to show good people output. Never show output, moral of the story. So what I want to do is keep it deliciously vague. So y is equal to beta naught plus beta 1 x1 plus beta 2 x2. I want to fit an equation of that type. Why do we have multiple variables? I can't do it with one variable. Maybe life is simpler with one variable. You have given me itna sa data diya, ek hi variable ye kya hai yaar? So you can. In the code, as you'll see, you can have one variable, you can have two variables, you can have three variables, you can have any number of variables. I think they've chosen two to say that, I once had we were going from bivariate distribution to multivariate distribution. So he did all of bivariate distribution, and then at the end he said, now put 2 equal to n. And we were telling him, sir, it doesn't work that way. If you do it for n, I can put n equal to 2. But if you want me to put 2 equal to n, in which 2 do I put which n? So he's saying, I'll show you it for 2, but if I show it for 2, you can do it for 1, and then you can do it for 3, you can do it for any. But we can try it for 1 also if you want to. So let's look at that, and what am I trying to put here? I'm trying to put miles here, and I'm trying to put usage here, and I'm trying to put fitness here. I forget which was where, but anyway, these two variables. How am I using it to describe? So you might want to think of it this way. If I give you 3 variables, how do I describe the relationship between them? If I give you 3 variables, how do I describe the relationship between them? There are 3 variables. In the form of something like that is one way of doing it. Now, does that mean that in reality, as he might say, that there is a relationship between these 3 things? No. Correctly so, he's being precise. Maybe, I don't know, not necessarily. Correct. Not necessarily. So, when you do linear regression in the future, any regression for that matter, there will be 3 uses of it. Use 1, it is simply descriptive. It will simply describe the nature of the relationship to you. It will make no causal inference, no sense that this causes this. It will give you no predictive model. It simply describes, and we'll discuss how it describes. 2, it predicts. Predicts means when I put in another value of x and another value of x1 and another value of x2, I will get a different value of y, which means that I've looked at data from all of you and a new person comes into the room with a new x1 and x2 and I'll put then her number in and I will predict her y. That is the predictive use of a model. 3rd, prescriptive. In order to get a different targeted y, what changes should I make in my x1 and x2? To get different usage of the equipment, what behavioral changes do I need to make in people to get them to use more? An even more complicated use of the same thing. So the same model, the same principle can be used for different uses. I am using it simply as a description. Simply as a way to summarize not univariate, not bivariate, but trivariate or multivariate. I can do that with a 3x3 correlation matrix. But if I choose to do it this way, now what number am I looking for? Fitness is here. Average number of miles a customer expects to walk or run. Average number of times the customer plans to use. So I'm going to give it this variable and this variable and try and get an outcome for the middle one. Getting it, the way to do it is something that I won't talk about too much. So there's sklearn, which is one of the learning modules that they learn in the sense of supervised learning. Import linear model, regression linear model as a function, and the slightly irritating big function here called linear model, which is inherited from linear model. You're giving it a y. What is the y? The thing on the left hand side of the equation. What is the x? The thing on the right hand side of the equation. What is reg fit? Reg fit means regression fit. And this fits my x and y. And this outputs something. It doesn't output anything at this point in time. Now I have my regression coefficients. And my regression coefficients are 20 and 27. My regression intercept is minus 56. And my miles predicted is minus 56.54 plus 20 usage plus 27 fitness. How is this interpreted from a purely descriptive perspective? It means that, for example, if usage remains the same and my fitness goes up by 1 unit, then my miles goes up by 27 units. If my fitness remains the same and my usage goes up by say 1 hour or 1 unit, then my miles goes up by 20. What does minus 56 means? If you don't use it at all and you have 0 fitness, you have run minus 56 miles. Makes no sense, but neither does 0 fitness. So the model is not necessarily written in a way in which this intercept makes sense. Which is why in the software, the intercept is not treated as a coefficient. The intercept is a part of the equation, but is not one of the coefficients that you interpret. This is pure description. What does it do, in case you are asking, and I hope you don't? What it does is this. What it does is, it looks at the data. And what is my data? My data is, say, y1, x1, x2. And it says this. It looks at yi minus beta naught minus beta 1 x1i minus beta 2 x2i whole squared. This is my prediction or the equation, beta naught plus beta 1 x1 plus beta 2 x2. This is my actual. What prediction is the closest to my actual? In what sense? Find the difference between the prediction and the actual, square it, and then minimize it with respect to beta 1, beta naught, beta 1 and beta 2. So what are beta naught, beta 1 and beta 2? They're variables or they're parameters that are estimated in such a way that if I estimate it this way, this plane is the closest to the data. In what sense? In the sense that the difference between the predicted and the actual is the smallest. Don't worry, you will do this again. You will do this again. This is a very important thing in supervised learning. In prediction mode. In description mode, all that is necessary for this to happen is that it describes the nature of the relationship between miles, usage and fitness. Describes in what way? In addition to the interpretation of the numbers, there's also something else interesting here, the positive sign. What does the positive sign mean? It means that as fitness goes up, miles goes up. As usage goes up, miles goes. I've summarized the relationship between three variables, treating one of them as a output. This is a descriptive use of linear regression as a way to describe data. Is the description real? To be decided, to be confirmed, to be analyzed, to be understood. Right? You do not know. It is empirical. It is based on data. Why is it necessarily true? Is there a logical reason why this is to be the case? Yes. You can do it with one. You can remove it. So if I remove it, what happens? So what would you do? You guys can do it if it's there. You'd move it here. Instead of usage and fitness, just have one of them there. I have not given you any idea as to whether the description is good. I have not told you whether this model is a good model or a good equation. In the same way that I did not tell you whether the correlation was good or whether the mean was good. I have not given any quality assessment to anything. These are ways to describe the quality of the model. How accurate is my mean? How good is my prediction? These are things that are going to be inference and prediction and will come. We can't answer those questions before we get to probability. In the middle here, sense of language on it. Yes. Fitness and usage as?
1 hour and probably 1 fitness. The answer gets
That's true. So you're saying that it doesn't make sense for certain values, which is true, which may well be. As I said, I am not saying that this is a good predictive model. What will happen is you will study a model like this and you will ask certain questions. What questions might you ask? For example, here's a question that you would ask. You would ask the question that if I fit a model like that, is this coefficient that is in front of this variable actually equal to 0? Because if it is actually equal to 0, then there is no relationship between the output and that variable. So what we do is we ask for a statement of this kind. If say yi is equal to beta naught plus beta 1 x1 plus beta 2 x2, I ask for the statement, is beta 1 equal to 0? And these are called hypotheses. Because if beta 1 is 0, then this number should not be in the model, and therefore this variable has no predictive power over this variable, which is where the analytics part becomes interesting. But to answer that question, I need to have a sense of how do I know whether this is 0 or not. And to answer that question, I need to have a sense of what the error around that number is. So this number is not 20, it is 20 plus minus something. In the same way that my mean of 28, age of 28 was not 28, it was 28 plus minus something. This is also similarly not 20, it is 20 plus minus something. And if that plus minus something includes 0, then I can't say that this is not 0. If on the other hand that plus minus does not include 0, I can say it's a predictive model. That's coming. But for now, this is simply a way to describe data. And like for means, like for correlations, like for standard deviations, and for linear regression, all of these, all will now see an inferential phase to them. The mean must see a plus minus. The regression coefficient must now see a test. Is it equal to 0 or is it not equal to 0? All these models, all these estimates will now be put into an inferential test, into a predictive test. How useful is it for new data? Because just describing current data is not going to be good enough for me. I'm writing an equation like this. I want to write this equation. I want to write miles is equal to beta naught plus beta 1 into usage plus beta 2 into fitness. I want to write this. The code now tells me what these numbers are. This number is minus 56, this number is plus 20, and the third number is plus 27. That's it. You can call it intercept based on whatever your term is. Yes. Yes, yes. In X, just put in another variable, do comma another variable. It can be any number. Try it out. I mean, you can do it now. If I don't want to fiddle around with this, I won't plot it. My purpose is to, if I could plot it, I would. But remember, there are three variables. Remember, there are three variables. Why am I doing this? Because in two variables, I can plot it. I can also look at many variables at a time and see a correlation. But if I have three variables, plotting things becomes difficult. If I have four variables, plotting things becomes even more difficult. But you still do it. I think you have Tableau or in your curriculum, maybe, I'm not sure. But visualization techniques can still help you. But if you've got 10 variables, then plotting is not a way to do it. So how do I express the relationship between 10 variables? By arbitrary equations like this. What does it mean? This intercept is, if this is 0 and this is 0, what is this? But as we have said, this 0 doesn't make sense and this 0 doesn't make sense. But this is simply a line that goes through the data. If I have data that looks like this, for example, all it does is it fits this straight line. What is the intercept? Where it cuts this axis. Does it make any sense? Maybe, maybe not. This is the place where the data makes sense. But the equation is written so that it cuts the line here. Correct? If I find a relationship between height and weight, and I write the equation as y is equal to beta, or say weight, is equal to beta naught plus beta 1 into height. What is beta 1? Beta 1 is the weight of someone who has height 0. Makes no sense, right? But giving me the freedom to have a beta 1 here allows me to get a much better line, because I can move this line up and down in order to get the best fit. It allows me an extra flexibility. Don't worry. In fitting good models, you will have enough experience in doing this. My purpose is just to show you it as a way to describe three variables in one shot. I'm not building a model. So if I do it for two of them, just miles and usage, just two of them, this is an equation just of this kind. With one variable, you wouldn't do this, because there's nothing to model, right? There's no equation between one variable. Criteria for doing this, remember my purpose is not to use this to select which variables to model. When I'm calculating means and standard deviations and correlations, I'm not using them to select anything. I'm not saying that I will measure your mean because you're important, or I'll measure your standard deviation because you're low. I'm using this as a tool to summarize 3 or 4 variables. Which variables to use when in predictive mode, you can do. You can look at for high correlations, and there are many other techniques that you learn in order to figure it out. So just like a mean is a way to do analytics, correlation is a way to do analytics, standard deviation is similarly. So what we had done yesterday is we had spoken essentially about descriptive statistics, and descriptive statistics is the taking of data and to simply describe it with the later purpose of either visualizing it or writing a report or using it for inference and prediction in later courses or later applications. It is compared with predictive statistics or predictive analytics, and then prescriptive. Describing is simply a task of summarizing a given set of numbers. You'll do sessions in visualization in due course. Prediction is a task that is often in machine learning or a data mining professional's requirement to say that if something changes, then what happens. I should have made a comment that there are 2 English language words that mean more or less the same thing. One is forecasting and one is prediction. In the machine learning world, these words are used a little differently. Forecasting is usually in the context of time. So something has happened in the past, what will happen in the future? I'm giving you this week, what will happen next week? Forecasting in the future. Prediction is usually used without any sense of time. Prediction is like I'm giving you an X, you give me a Y. So I'm giving you one variable, you give me another variable. So predictive analytics doesn't necessarily forecast anything, despite the fact prediction itself is about forecasting. So the words mean slightly different things. It's a little like, price and worth mean more or less the same thing, but priceless and worthless mean different things. So the words are used in a slightly different context. So in descriptive statistics, we had looked at certain ways of doing things. For example, we had looked at what is called univariate data. Univariate means one variable. For the univariate distributions, we had seen certain kinds of descriptive statistics. Some of them were about, shall we say, location. Location meant where is the distribution, and we had seen, for example, things like means and medians, which talked about where is the distribution located. We talked about things on variation, where we had talked about standard deviation. We'll talk more about things like this today. Standard deviation, range, interquartile range. Here also we had terms, for example, like the quartiles, the upper quartile, the lower quartile. These are parameters that are used in order to convey a message to someone saying that what is the data about. So for example, a 5-point summary talks about the minimum, the 25% point, the 50% point, the 75% point, and the maximum. Irrespective of the number of data points, you could have 10 of them, you could have 100 of them, you could have 1,000,000 of them, you could have 1,000,000,000 of them, it doesn't matter, it's still 5 numbers. Sometimes those 5 numbers tell a lot. They tell about location, they tell about spread, they talk about skewness, Is the distribution sort of tilted towards one side? Is there more data on this side than on the other in terms of the data spreading out towards the tails? So there are plots associated with this as well. We'll talk a little bit about the plots later. Then we went towards the end, towards the idea of, let's say, bivariate data. Bivariate means that there are two variables in which we just didn't spend a lot of time. We talked about covariance and correlation. Covariance is a sense of variability of two variables together. Its univariate version is a variance, which is the square of the standard deviation. A scaled version of covariance is the correlation. If the correlation is close to +1, then it means that there is a strong positive relationship between the variables. Positive means if one goes up, the other also goes up. If one goes down, the other also goes down. Negative means the opposite. As one goes up, the other goes down. Correlation is not to be confused with causation. There is nothing in the descriptive world that says that this causes this. There is no science to this. This is simple description. The science to it and the logic to it and the use of it for inference, for business logic and things like that will come a little later. For now, we are simply describing. Then we have taken an even brief and perhaps even more confusing look at multivariate, our first multivariate summary, where we looked at the idea of a linear regression. A linear regression is an equation of the form y is equal to, say, beta naught plus beta 1 x1 plus beta p xp, where one variable is written as an equation of the others. This is merely done to describe the nature of the relationship between the variables. Correct? It can be used for prediction. It can be used for prescription if you wanted to, but that is not our purpose here. Our purpose is simply to describe a relationship. Why is this useful? Because let's say that you've got 3 variables, 4 variables, 10 variables. You need a mechanism to say how these variables are connected. How do you describe 10 things at a time? There are graphics out there. There are famous graphics in history where you have many variables being represented on one plot or one visualization. So visualizing things itself, so for example, we looked at a certain kinds of plots. We looked at, for example, histograms. We looked at box plots, sort of pairs, which were essentially what are called scatter plots. So these are for the human eye. These are things for the human eye to see data. And they have the limitations because we can only see data in a certain way. We can't see very high dimensional data. Visually, we can see up to 3 dimensions maybe. For those of you who are interested about such things, or any of you who are in the graphics world, etc., you spend a lot of time saying, how can I make people see things? So how many dimensions can you actually plot in? I mean, Python itself is good at it, but there are other devices. So for example, let's say that you're plotting, you can have, of course, one variable as x, one variable as y. Another dimension can be maybe the size of the plot. You know, if this is bigger, then another variable z becomes larger. It can be a color, like a heat map. A 4th variable, if it is low, can be blue, and if it is high, can be red. Another may be the shape of it. Lower values are circles, higher values are more pointy. So there are many ways in which you can get summarization to be done. So when you do visualization, if you do, you'll see other ways of summarizing it. But if you want to do it as a number, then something like an equation that looks like this is often a good representation. How one gets at these beta 1s and beta p's, I explained very briefly. What happens is you form this equation and you take those values of beta naught, beta 1 and beta p that are closest in some sense to the data. So if I draw a picture of, say, 2 of them, y on x, and I say give me a line, which line should I take? Take the distance from the line to the points and make this distance the smallest. Get a line that goes through the data with the smallest distance to the points. How is small measured? Small is measured by the square of these distances, because distance on the above the line and distance in below the line are equivalent. So if this is my beta naught plus beta 1 x and this is my y, what I do is I look at y minus or yi minus beta naught minus beta 1 x I. I is equal to 1 to n, my n point, square it. This is the squared of the distances from the line, and then I minimize this with respect to beta naught and beta 1. That is how I get the numbers. But if you're simply interested in what Python or R does, then the program will simply give you what the number is.
So what those will give? This minimizing of beta 0, beta 1.
What? Sorry?
What I will get it from those?
You will get the value of beta naught and beta 1. Find the value of beta naught and beta 1 such that this is the smallest. For different values of beta naught and beta 1, this distance will be different. For different lines, this distance from the line will be different. Which line will I take? The line such that this is the smallest. How to get the beta? So, form this yi minus beta naught minus beta 1 xi squared.
On a plot, actually, that points are where the point existed.
The point is here. The points are here.
So these line is basically which.
The line is a line I'm trying to find. Here is a point. 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 Right? Let's say I have 5 points. I want to describe the relationship between these 5 points. Therefore, what I need to do is, I need to find a line that goes through these points. I want to write an equation of the type y is equal to, say, I'll remove the b and x, y is equal to a plus bx. I want a line like a plus bx going through those points. There are many lines. This is one line, this is one line, this is one line, this is one line, they're all lines. Which line will I use to represent the relationship between y and x? I need a criteria. So what I do is, I try to say, let me find a line, let's say that this is the line, and find out how good it is at describing the data. Now, when is it good at describing the data? When it passes close to the points. Because that is its purpose, to describe the data. Because I want to say that this line, without any data points, is a description of the data.
But how to get that line position?
That's what I'm talking about. So I need the value of A and B. Correct? So how do I find the value of A and B? For every such line, A and B, I find the distance of the points to the line. So if there are, how many points do I have here? I've got 5 points. So I've got 5 distances. What are the points? This is the point x1, y1. This is the point, say, x2, y2, x3, y3, x4, y4, and x5, y5. These are my 5 points. How far is the point x1, y1 from the line? This distance. And what is this distance? This distance is how much? This distance is, this point is y1 minus what is this point? A, so A plus B x1. That's the point on the line. Correct? Okay. I can stop here, but if I stop here, what will happen is that if this is the distance, then this will become a negative distance and this will become a positive distance. And they will cancel or neutralize, as you say.
Sir, A is which point, which is from that point to the line, actually that is the A distance.
No, A is this equation. A is the equation of the line. You want to know what the term A is? A is this point. B is this slope. And I want to find A and B. So this equation is A plus BX. So this point is Y. And this length of this line is Y minus A plus BX1 squared. Plus, for the second one, what is it for the second one? Y2 minus A minus BX2 whole squared. Do this 5 times. Correct? For every line, you will get this number. If you want to, you can take a square root. For every line, you will get this number. This number is the sum of squared distances of the line from the data. It tells you how far the line is from the data. The larger this number is, the further the line is from the data. The smaller this number is, the closer it is to the data. If the data is on the line, what is the value of this? 0. So if every point is on the line, or if the data is itself a straight line, then this will be 0. So I have formed this. Now I find the value of A and B such that that is the smallest. For every A and B, I will get the value like this. If I take another line, I will get another value of this. For every choice of A and B, I will get a different distance from the data. Which A and B will I pick? That A and B such that this distance becomes the smallest.
So can we have an issue where the algorithm means computationally we don't find the value of which can kind of minimize means the kind of
okay, so let me finish this. So choose A and B to minimize this. And that is the A and B that the software gives you. This is called a linear regression. Right? Answer 2, does it have a least square? This is why Gauss was so successful and Laplace was not. You will get a unique solution. This is what's called a convex problem. And this is a convex optimization because of the squaring. If you have modulus values here, there is a possibility that you will not get a single answer. But because of this, and because of the square and because of the nice bowl-shaped curve that the square function gives you, you will find a unique solution to this.
So how many times the system tries? The number of data points?
No, the system doesn't do it that way. The way the system does it is, the system differentiates this with respect to A and B, differentiates with respect to A, sets equal to 0, differentiates with respect to B, sets equal to 0 and solves those two equations. It doesn't minimize. It doesn't minimize. When this becomes very high dimensional, this minimization, this differentiation of solving it becomes a very interesting problem in mathematics and numerical analysis. To do that, you need typically to do linear algebra, and in courses such as this and in machine learning books, you will see at the beginning of the book, you will often find chapters on optimization and linear algebra because of this or something similar to this. That to represent a problem, you often need a matrix representation, and to get a good learned solution, you need an optimization. So most machine learning algorithms are built that way. Because for example, as I was saying yesterday, that you're going to tell someone to do something. You're going to tell a car to behave itself on the road. Yesterday, while going back to today morning, I heard that, or I read that BMW and Daimler are setting up a, €1 billion R&D operation somewhere in Europe for self-driving cars, etc., etc. Two different industries are trying to go towards making cars that don't need people. The automobile industry is, as well as the ride-hailing industry. People like Uber and Lyft and Ola and these companies. So now you're going to figure out, the car is now going to have to be told when to go and when to stop. But how does the car know that it has a good rule? How does it know that it has learned? And what is good learning as opposed to bad learning? What is enough learning as opposed to not enough learning? A computer is stupid. All a computer can do is store a lot of data and do calculations quickly. Computers aren't intelligent. To make the computer intelligent, you have to give it an intelligent function. You have to say, okay, run your algorithm such that this thing becomes the highest it can be, or this thing becomes the lowest it can be, which is an optimization problem. So what machine learning algorithms almost invariably do is they say that here is an input and here is an output. Give me an algorithm such that based on the input, you can come closest to the output. For example, object recognition. If I'm teaching computer vision, or if I'm teaching text recognition, or any of these, let's say text recognition. So I'm trying to understand what the word is. So the computer is reading something, let's say in handwriting, and it's trying to identify that as an English language or a Kannada or a Hindi phrase. So it's going to write something down. You write this, and in my horrible handwriting, I'll write something, and that camera has to recognize what I wrote and transcribe it into something that you can read. Now, how does it know it's done a good job? What it needs to know is that this is what I think the word is, and this is what the correct word is. Now, tell me whether I'm close. And if I'm close, I'm good. If I'm not close, I'm not good. But this has to work not just for one word, this has to work for thousands of words. So I must be close to thousands of words at the same time. Therefore, I need to measure the distance from my prediction and my actuality over many, many data points. So all these algorithms, what they do is they take your prediction and they compare with the actuality. And they find a distance between them. And they minimize the totality of the distance between the prediction and the actual. And an algorithm that minimizes that distance is a good algorithm. It has learned well. So they all do something like this. Where this is the prediction and this is the actual. And A and B are the parameters in the prediction. In other words, find a prediction such that it is closest to the actual. So this algorithm has become very popular. It's probably the single most popular fitting algorithm out there. This is called least squares. Least squares. This is called least squares. Squares. Here's a square. Least because you are minimizing. This is called least squares. And the least squares algorithm is a very standard way of doing things. This has nothing to do with the algorithm itself. The algorithm can be anything. This itself can be a neural network. It can be a support vector machine. It can be a random forest. It can be association rule. It can be any of your logics. But the question is, if you give me the program, how do I know whether the program is good? So I give it what's called training data. Training data means I tell it what the right answer is.
So, sir,
yes.
This we can infer that this is the starting point of basically what the prediction and what actuality is that we are comparing, and
yes.
we are getting the result of that?
Yes. So this is the prediction. This line is the prediction if you want to think of it. The data points are the actuality. The problem is this. These data points are also not the actuality. The actuality is going to come in the future. It is a training set for the data. It is the data that has been given to the algorithm to train it. but it's not the algorithm, it is not the data that the data will actually run on. The car will run on the road. The car will see its data points, its people and other cars and the cows and whatever for the first time. It will not have seen that data before, but it will need to know what to do.
You're starting off learning basically.
Yes, so what do you do? So what you do is you train the algorithm. What does training the algorithm mean? Training the algorithm means you give it data for which the car is told what to do. In other words, you give it what they call ground truth. So you give it the why and you say, here is the data or here is the situation, please do the right thing. So please do it such as this. So here's a person who's crossing the road. Please stop. Here is another person crossing the road, but he's very far away. Calculate the distance, compare with your speed and decide what to do. He may be far enough for you to be able to see, but you may not stop. If you are driving a car, it's quite possible that you are seeing someone crossing the road, but maybe about close to 100 meters ahead and you're not slowing down. Because you're doing the calculation that I have a speed, the person crossing the road also has a speed, and by the time I get there, this person would have gone. Do not do this when doing a level crossing. But we all do this all the time. We do this when crossing the road. So I'm happily doing that. There is a car coming, but I'm still crossing the road. Why? Because I know that I'll be able to cross the road before I get there. So the car needs to be taught how to do these things. So this data, it's given data like this and says, for the training data, get as close as you possibly can to the training data. And then it's given what's called test data. And now the algorithm is told, oh, now I'm going to give you new data. And now you're going to tell me how well you did on new data. So suppose you were given a problem like this. I'm not supposed to talk about this. Your ML instructors are supposed to talk about this. But suppose you're given a problem like this. In other words, I've given you a data set and I'm going to tell you that your performance will be judged not by this data set, but on another data set that I am not giving you. What will you do? How will you make your program ready? Yes, so how will you make your program generalizable? So the usual way it's done is something interesting. You say that, okay, you want me to predict data that I have not seen. I will see if I can do that. So what you do is all the data that is available, you take a certain part of it and you keep it aside. You have it, but you don't use it. And now the remaining part of the data you build your algorithm on. And now you test it on the kind of data that you yourself have but have kept aside. This is called validation data. And now if your algorithm works on your own held out data, that data that your algorithm has not seen, you are more hopeful that it will work on somebody else's new data. This is called validation. And this entire cycle is often called test, validate, train, etc. Or train, validate, test, etc. And you will do this in your hackathons. But to do this, the algorithm needs to know as to how good it is. And it needs measures like this. There are other measures. So for example, if you're classifying an algorithm, good or bad, positive sentiment on tweet or negative sentiment on tweet, no numbers, then you do not need this. What you need is simply, are you correct or are you incorrect? If it is correct, let's say you give yourself 0 distance. If it is incorrect, let's say you give yourself 1 distance. In other words, you made 1 error. And you just count how many mistakes you made. But what is a mistake when it comes to estimating a number? Like say miles and things like that. There's no mistake. You're either close or you are far. So you need a measure of how close. That's a measure of how close. So this descriptive method is used as a criteria for building predictive models. This itself can be a predictive model, but very rarely is it good enough. Too few things in the world are this simple. Are there things in the world this simple? Yes. But as we said, as we discussed yesterday, even things like height and weight are not that simple. There are complexities to that. So for example, you can have theories which say, for example, you could say, let's say a savings rate. What's a savings rate? A savings rate is the proportion of money that you save. Now, if there is a savings rate, what that would mean is that if I take your income data and I take your consumption data, that should form a straight line. Because you're saving up the same proportion every month. But it's not. If you go home and month by month you figured out what your income was fairly precisely from your salary or from other sources, etc., and you also plot again fairly precisely as you can how much your household spent that month, it will have an increasing effect probably, but it's very, very unlikely to be a straight line. In certain things you may be going after a law of physics, but the law of physics may hold for gravity, may not hold for anything else. I remember trying to apply this, so one day cricket sort of became popular when I was in school or thereabouts, and one calculation was done as to how to figure out whether a team is doing well or how well is a chase going. So one possibility is to simply track the score. The other possibility is to say that if you know how many runs you're going to get, you tend to begin slow, protective wickets and you accelerate. So what you do is you build models for that. You build models for saying that let me assume that the team is going to accelerate constantly, which means that every over that comes later it's going to get better. Its run rate is going to keep increasing steadily. Now if its run rate keeps increasing steadily, then when will it reach the halfway point? That is the same thing as asking the question that if I take a ball and I drop it, how long will it take to get to the halfway point? And there's a square root term there, and the answer is about 50 divided by the square root of 2, about the 37th over or something of that sort. So effectively the logic was, if you have reached halfway point below, let's say the 37th over or so, you are on track. If not, you need to accelerate a little faster. That's using a physical law to try and predict something that is not a physical law. I mean, the laws of physics do not apply to cricket, at least not in this way that I am describing. So therefore, these laws will get you somewhere, like a straight line, etc., but they are approximations. And so what you will do is you will build better versions of this when you use it for an actual prediction. But the same argument holds for things like mean, standard deviations and many such things. If there's a specific problem you need to solve, you may or may get a better estimate for doing it. Yes, someone was asking a question.
The question is that we calculated y minus a plus
yes.
x1. That is basically the distance.
Yes.
Right? What we are talking
yes.
about on the line.
Yes.
Then what the b is actually that is what we talked about.
So there are many ways to do that. One is you just put it in, you find for different values of a and b, you find what that number is, and then you solve it. If you want to do it the hard way, you can still do it the hard way, and the hard way will end up being something like this. I'm minimizing, and I should not be talking about this. Say yi minus beta naught minus beta 1 xi whole squared. I was using a and b, right? So say a and b whole squared. I'm going to minimize this with respect to a and b. So essentially what I'm going to do is I'm going to call this, let's say, L of a and b. And I will say DDA of LA is equal to 0. DDB of LB is equal to 0. And I will solve these, and this will give me two interesting equations. And my answers will be this. I'll tell you what the answer is. Your B hat, your estimate of B will be this: summation xi minus x bar yi minus y bar divided by summation xi minus x bar whole squared. And your A will be this: y bar minus b hat x bar. So if you want formulas, these are your formulas. Because I'm minimizing something. To minimize something is the same thing as setting its derivative 0. Now that is also the same as maximizing something, but this is where convex optimization comes in. That this will have a minima, but won't have a maximum. So by setting it equal to 0, I'm going to arrive at the minimum.
So,
yes.
The minimum will come with respect to A, right? Not with respect to X and Y.
Yes, X and Y are fixed. The data is fixed. The parameter is varying.
The range is fixed.
X and Y are fixed for my data, correct? So my B is written in terms of A and. So this is a formula. If you want to close it, this can also be written as the covariance of X and Y divided by the variance of X. So if you want to calculate it for two variables, what you need to do is you need to calculate the covariance and divide by the variance. And here y bar minus bx bar, this means that the line passes through x bar y bar, the line passes through the middle of the data.
So with the derivative, the minimum will be, we are minimizing A, right?
We are minimizing with respect to A. A is a variable.
So how come this equal to 0 will minimize the distance? And
how it will do this? So for different values of A and B, the distance will look like this. There's a particular value of A and B in which the distance will be this. There's another value of A and B in which the distance will be this. There's a particular value of A and B in which the distance will be this.
That is corresponding to the axis.
This is my summation yi minus A minus B xi whole squared. This value. For different values of A and B, I will get this. So when I minimize this, now to do this, you don't need to do it. All you need to do if you want to do it is this. If you want to do it, do this. Do you have yesterday's code? Open it. You can do it. Then right now, that's it. You stop. It's like saying I get the mean, then what? One use of it is to predict. Another use of it is to prescribe. There are many uses of it. A third use is to do nothing, but simply to use it to visualize or to summarize the relationship between two variables. Correct? And we do this all the time. So for example, how do you measure how price sensitive your product is? Do you understand the question? You're trying to change the price of your product. Why would you want to change the price of your product? Profitability. Maybe you want to increase it so that you get more money. So people in marketing often want to understand how sensitive my sales are to price. Now to do that, they come up with various kinds of measures. One particular measure is what is called the elasticity of demand. Elasticity of demand means this: if my price changes by 1%, by what percentage does my sales change? Well, if my price goes down, I would expect my demand to go up. But by how much? Now there are certain assumptions to this. For example, it's assumed that the same number works if it increase price as well as you decrease price. So this is called the elasticity of demand. So therefore, to get the elasticity of demand, but what is the elasticity of demand? The elasticity of demand is essentially a slope. A slope that relates something like this, that if I have demand on this side, let's say sales on this side and price on this side, I have this negative slope. The slope of this is what the elasticity is. So very often you do equations like these in order to simply get at a number that has a certain meaning for you. So the slope of a linear regression between log sales and log price is the elasticity of demand for that product. I mentioned log sales and log price because elasticity is done in terms of percentages. A percentage increase in price and a percentage decrease in sales. If I don't do it as a percentage, there's a problem. Now my measure depends on my units. Is it 1000 units per rupee or what? It depends on what I'm selling in one currency, and that's not a good measure. So I measure it as percentages, but when I measure it as percentages, I have to measure on the log scale. So there are many models like this where the equation itself is used to simply describe a parameter, something that tells you a little bit about the market, like an elasticity of demand. You're not using it to predict anything, you're simply using it as a descriptor. So you say that this is an inelastic product. If this is an inelastic product, what does that mean? It means that if you change its price, there won't be too much of a change in its demand. Classic examples of that, for example, are salt. If you change the price of salt a little bit, at least certainly domestic salt, there won't be too much of a change in demand. There might be a little bit, but there are certain things that are highly inelastic. You change it a little bit and the demand will change a lot. And marketing people are very sensitive to this idea, saying that is my demand elastic or is it inelastic? If I want my prices to go up, then I want the demand to be inelastic, because I don't want my demand to go down. If I want my prices to go down, or if I'm pulling my prices down, then I want the demand to be elastic, because I want people to say that your prices are going down, therefore I will buy more. So marketing analytics is very concerned with things like this. So therefore, sometimes an equation of this kind is built just to describe something. Right? So what I'm going to do is, let's go down. And since we are going to do this just on 2, let's pick it just on 2. So let's change this to maybe miles, and let me remove this. So what I'm going to do is, I'm just going to do it on one of them. I suspect one parenthesis might then work. I suspect this might work.
2 parameters.
X has to be in 2 simply because of the way it's entered. Because I have not done anything on this data set now. This one is a comment. So what do I have on the coefficient here? 36 and 22. So what is my equation based on this? Miles is equal to minus 22 plus 36.29 whatever into usage. Okay? Alright. Now let's try to do this manually if you want to. If I want to do this manually, so I need to get at each of these things. So now I need to find, for example, I need to find, let's say, the covariance between miles and usage. How do I do that? Tell me. No, not a sample. The data is present in me. So now I have things like, for example, my data, miles. Correct? So I can calculate things on this. So for example, I can do this. This is the mean. I can do calculations on this. Okay. So now if I do say what is the standard deviation syntax? ST, not DV. Okay. This is standard deviation. Okay. Let's try one more. This is the variance. What is the variance? The square of the standard deviation. Okay. Now I want to find the covariance of these. How will I find the covariance? Not necessary. Remember, I have the correlation function. How did I find the correlation function here? I found the correlation function from here. So I've got a number of ways to potentially do this. One is I can do it with the correlation function or the covariance function. In other words, so for example, I can try doing this. How do I write it here? My data dot this thing here was the correlation. This gives the covariance matrix. This gives the covariance matrix. Okay. Now, what is the value of B according to my formula? So, covariance of which variables now? Which are my two variables? miles and usage. Where is that covariance? Is it this number? 42.71, right? Okay. Divided by what? Variance of what? Variance of usage. Y. Not Y as in Y, but Y as in question mark Y. So my data dot usage dot var. Is this also here in the data? It is, because what is the what is the diagonal element of this? What is this number? Usage dot, this is usage 1.17, this number here. This number here is the variance. Okay. What is the equation? Usage. This is my x. This is my y. This is my x. So covariance of xy divided by the variance of x. So based on this, what is my answer? My answer is going to be for the answer for my coefficient is going to be, where is the covariance? Here, 42 point, I can do it, manually, almost 42.71 divided by, where is the variance? 1.17, say, 6 or something of that sort. 36.318. Where is my value of B? Here. This is my slope, right? How do I get my intercept? Mean of y. So my data this is the mean of all of them. So what do I want? Which mean do I want? Mean of, what is my y here? Miles. Where is my mean miles? Let's say 103, say say 19, minus, what is my slope? Say 36.32 or something of that sort, star, what is my x? Usage, which is 3.45, so 3.45, 3.3.45 or something like that, right? Will star work that way? Minus 22. What is my coefficient? Minus 22. So if you want to, you can do this from first principles by using that formula. I am not asking you to. You can do it just by running linear regression. But what it is this. You can also check the units. What is the unit of B? The unit of B is the unit of miles divided by the unit of usage. What is unit of the covariance? Miles into usage. Divided by variance, which is miles into miles. So the ratio of this is usage by miles. What is the unit of A? Miles. This is in miles. This is in miles per usage, and this is in usage. So the units all make sense. Which one? Units. What is the unit of the covariance? The unit of x into the unit of y. Why is that? Remember the definition of covariance is the product of an x and a y. So this is in the unit of the product of x and y. This is in the unit of the square of x. So the product of x and y divided by the square of x and y cancel out, this becomes in the units of y by x, which is what B should be. B should be in miles per usage. 36 means what? It is 36 miles per usage unit. That's what B is. B is in some units. Because B is in some units, we will run into some difficulty when you use this in predictive models. Because let's suppose I want to figure out, is this number equal to 0 or not? Because if this number is equal to 0, statistically speaking, then miles doesn't depend on usage. But because this is not a dimensionless number, I can make it anything I want to by simply changing the unit. So that makes the statistics a little hard. So I cannot simply look at this number and say whether it's high or low. I can make your height anything I want to by simply changing the scale. I can make your height 1,000,000 by simply using a small enough unit. So simply taking a raw measurement tells you no idea of the value of its magnitude.
That will equally have effect on miles and usage as well.
Yes. That same argument will work for any of those parameters. So therefore, when we do testing, when we do hypothesis testing, we need to normalize all these numbers by something, and that something is typically standard deviation. So we'll do that. Okay. So let's end this. The purpose of this was just to tell you what that regression line is, and then there are similar formulas. But as the dimensions increases, it's hard to do this manually. For 2 of them, you can do it manually. For 3 of them, it's hard to show manually, which is why I changed it. Because I would not have been able to do this for 2 variables. The formula becomes a lot more complicated for 2 variables. And which is why people don't use the formula for say 10 variables. Now what I want to do is I want to talk a little bit about probability. This slide deck should also be there with you. So you have to cope with the idea of probability is to be able to cope with this uncertainty. What is the uncertainty that we're talking about here? The uncertainty is that when you observe something, you're not entirely sure what the value is. Not because of a measurement perspective, but because you do not know what the corresponding population number is, you do not know the truth of the number, another sample will give you another number. There is uncertainty. And this uncertainty is usually captured by a probability. This is an interesting question. What is the probability that a man lives for 1,000 years? So the empirical probability, what does empirical probability mean? Empirical probability means you ask the question, has anyone lived for 1,000 years? If the answer it is no, then you say that the answer is 0. If anyone has lived for 1,000 years, you'd say, tell me how many people have lived for 1,000 years. So one interpretation of probability is simply, you see it. There's a criticism to this point of view. One of our teachers, Professor D. Basu, many years ago would say that if you want to find the probability that a little girl is going to fall into the river, how many little girls do you want to walk next to the river to find out? So in other words, not all probabilities can be thought of as, let me just see how often it happened. So you need a little bit more than this. So some words, the words are often useful to know. Probability refers to the chance or likelihood of a particular event taking place. An event is an outcome of an experiment. An experiment is a process that is performed to understand and observe probable outcomes. The set of all outcomes of an experiment is called a sample space. This is correct and it's easy to understand with one problem. Who is performing this experiment? Now, when you use probability, you're in 2 modes. In one mode, you are performing the experiment. What does that mean? Let's say you are running a marketing campaign, or you are designing a portfolio, or you are manufacturing a product, or you are recruiting people, or you are testing a piece of code. You are doing the experiment. And sometimes you are not doing the experiment, somebody else is doing the experiment and you are simply observing. The customer is buying or is not buying. The product is failing in the field or it is not failing. The portfolio is making money or it is not making money. The person you've hired is staying on or is quitting. It is not your experiment. You are simply observing the outcome of it. So sometimes you get to do the experiment and sometimes you do not. We used to call these things experimental studies and observational studies. An experimental studies is something in which you begin by designing the experiment and you have a handle over how much data you will collect. An observational study is you just watch and you see what data comes in. you will in your careers mostly be working with observational studies because of the nature of data today. There's just a lot more that is simply being generated without anyone asking for it. In certain very peculiar situations, you do experimental studies. For example, nuclear explosions. Right? Why do countries want to test nuclear devices? Primarily to collect data. Primarily to figure out whether this thing works or not, or how does it work or not. So they do a little experiment to say, boom, let's see what happened. Because otherwise it's all computer simulations. And you've got no idea whether this happens or not. I remember running into trouble with my engineering friends on this, working on the design of a fairly large aircraft engine. And there was a question of saying that, what is the thrust or what is the efficiency of the engine? And I stupidly made the observation that why don't we test it out? And so they looked at me, this side, that side, etc. As if, how do we going to explain to this idiot? And then patiently one of them said to me, very kindly, he was a very courtly gentleman, older than me, and he took the responsibility of telling me, where will it go? So his point was that if this engine fires up, it's going to want to move. Where will it go? Pointing to the difficulty that I cannot easily do a full-blown test of a jet engine. Because if I do start it, I've got to give it enough room to move somewhere. So where do you want it to go? So where do you want it to go? So you will not be in a situation to do that very often. So when you say experiment, it is sometimes your experiment and sometimes it is not. In rare situations will you be in an experimental state, like in A/B testing and websites, for example. It's a common job. Marketing people are often asked to design websites, and they are asked to say, which is a good website? So you do an A/B test. What's an A/B test? You design a website of say type A or type B, maybe one is the old website, and you let them loose, and you find out how people react to the different websites. This is a little tricky, but I want you to think about this. We will not spend a lot of time on it. In manufacturing unit, 3 parts of an assembly are selected. We are observing whether they are defective or not defective. Determine the sample space and the event of getting at least 2 defective parts. What is the question that I am asking? The question that I am asking is, here's the situation. There are 3 parts. For these 3 parts, I am interested in knowing whether they are good or bad. The question is asking this: describe for me all the possibilities, which is what the sample space is. So what are the possibilities?
Defective.
Don't talk about probabilities now. Just talk about the possibilities of what could happen. We'll talk about the probabilities later.
All 3 could be good. All 3 could be good.
Okay. So all 3 could be. One way of doing it is this: all 3 are defective, 2 of them are defective, 1 of them is defective, and none of them are defective. If you do it this way, the sample space has 4 objects in it. Correct? That is one way of describing it.
1 minus.
We haven't yet gotten to probability, but yes, if you get to it, it'll be 1 minus that. And the event of getting at least 2 defective parts means 2 defective or 3 defective, which is good. So this is one way of describing the sample space. This is not the way the sample space is typically described. You are not wrong, but there is a problem, and the problem is this. So let's suppose I describe it this way. In other words, now I describe my sample space as, let's say, 0 defective, 1 defective, 2 defective, and 3 defective. Let's say these are my possibilities. If I do it this way, and this 2 defective thing is here, if I do it this way, I will eventually have to get around to calculating probabilities. And let's say I want to calculate the probability of, let's say, this event, at least 2 defectives. Now how will I do that calculation? Now what happens is, the way the probability calculations are done is that you try to split this up and say that I'm going to find the probability as the sum of the individual outcomes, as the sum of individual events. I'm going to split it into individual components and then add it up. So therefore, I will ask for you therefore what is the probability of 2 defect and what is the probability of 3 defect? And what is the probability, for example, of 2 defects? So let's say I want to find out what is the chance of 2 defects. How will I find that? How will I find the probability of there being 2 defects in this situation? Yes, and how will I do that calculation?
So among 3, 1 and 2. So among 3, 1 and 2 and 2 and 3 and 1 and 3 is the defective.
There is no, see, you have not allowed me to even think in terms of 1, 2 and 3. There is no 1, 2 and 3. There is only 0 defective, 1 defective, 2 defective or 3 defective. Your sample space has lost all identity as to which one is defective. So do you want to revise your opinion of what the sample space is? What do you want to define it now as? Correct. So what you can do is, you can define your sample space not in terms of the count of defectives, but in terms of whether each individual item is actually defective or not. Correct? In other words, what you're doing is, you're essentially saying, let's say good, bad, or good, defective or G. What does this mean? The first is good, the second is defective and the third is good. If you do it this way, how many elements are there in the sample space? 8. Because each of these can be good or bad. These are your 8 possibilities. Now from this what can happen is, using these events you can now add them up. Now what happens is, if I am looking at, let's say, 2 defectives, which ones are relevant? Say this has 2 defectives, this has 2 defectives, and so 3 of them have 2 defectives in it, correct? 1 of them has no defectives, 3 of them have 1 defective, 3 of them have 2 defectives, and 1 of them has all defectives. So this is another way of writing the sample space. What this will do is, this will allow the calculation to be a little easier, and your objective is to be able to make the calculation a little easier. So in this particular case, for example, just to get the calculation out of the way, let's suppose that the chance of a defective, let's suppose the probability of a single defect let's say is 20%. Let's say it's 20%. There's a 1 in 5 chance that my unit is this seems too high. You won't survive. Let's say 10%. 1 in 10 is defective. 1 in 10 is defective. If 1 in 10 is defective, the probability is now 10%. Then what are the chances of all of these? I'm asking for a common sense answer to the question. We'll get to the concept a little later.
1 would be defective.
So the chance, you understand, the chance that a single one of them is defective is 10%. The chance that a single one of them is defective is 10%. And let's say that I want to solve this problem. What is the problem? The event of getting at least 2 defective parts. In other words, I want to find probability of, let's say, 2 defectives. What is this? Let's work it out. It's a good example to work out. We'll understand many things as we do it. The chance of a single defect is 10%. I'm asking for the chance that I've drawn 3 of them and that I will see 2 of them being 2 defectives. This needs a little bit of work. Let's do this patiently. Let's work this out. Right. Now the chance of 2 defectives can happen in how many ways? We just saw it, right? Now let's suppose that I want to calculate the chance of 3 defectives. To calculate the chance of 3 defectives, here is what I claim I can do. I can add up the chance of these 3. Right? Equivalently, I can do it this way. Probability of 2 defectives is equal to probability of GDD or DGD or DDG. Is this correct? There are only 3 ways in which I can get 2 defectives. You're okay with this? Okay. Now I'm going to do something a little interesting. I'm going to write this as P of GDD plus P of DGD plus P of DDG. Now let me explain what allows me to do this. What allows me to do this is the fact that if this happens, these two cannot happen. They are mutually disjoint. Both cannot happen together. Which means that if I draw a picture, they are like this. So if I want to find the chance of being here or here or here, I can simply add up the chance of being here plus the chance of being here plus the chance of being here. Why can I do that? Because they are disjoint. There is no common thing. If this happens, then this does not happen. These are 2 separate things. Disjoint. Okay? Now let's look at each of this. Probability of G, D and D. This is what event? The first is good, the second is defective and the third is defective. I am going to write this as P of G multiplied by P of D multiplied by P of D. I am going to multiply.
Because they are related to each other.
I want yes, because I want to use a technical term here. And the technical term that I want to hear is independent. Independent means that whether the first is good or bad tells me nothing about whether the second is good or bad. They are independently good or bad. This is an assumption. But I think the problem allows me to make that assumption. I'm making a part, it's good or bad. I'm making another part, good or bad. And these are independent of each other. I'm trying to sell a product to him and to him. Whether he buys or not is independent of whether he buys or not. That's an assumption. It may be true, let's say they're from 2 different neighborhoods, or maybe if they're neighbors and I'm going from one house to the other, maybe it is not independent. Maybe if he buys, he's more inclined to buy. So independence is an assumption. In this case, I'm making that assumption. When events are independent, I can multiply the probabilities. What does that mean? For example, let's say that he will buy a product for me, let's say 10% of the time. In other words, for every 10 people I want to sell my product to, only 1 person buys. So there's a 10% chance that he will buy my product. And let's say there's an independent 10% chance that he will buy my product. What is the chance that they will both buy my product? 10% multiplied by another 10%. So first he has to buy, that's a 10%. And then his 10% will be like 10% of that. So 10% to 10%, there's only a 1% chance that they will both buy my product. Multiplication is allowed when things are independent. So independence means that the probability of both of them happening, or let me rephrase the question in this way. Let me write it as one more step. Let me write this as probability of G and D and D. I'm going to write this G, D, D as G and D and D, which means the first is good and the second is bad and the third is bad. This and I will now write as G into D, into probability of D. In other words, if there's an and, then I can multiply. When? If things are independent. These laws will be clearly written later. So if things are independent, I can multiply if there is an and. If things are disjoint, then I can add when there is a or. common sense rules, but they require a little bit of sort of logic in calculating. So I'm going to take this to the top now. This is going to be what? This is going to equal P of G into P of D into P of D plus P of D into P of G into P of D plus P of D into P of D into P of G. Now what is P of G? 0.9, 90%. 0.9 into 0.9 into 0.1 plus, very right, clever thinking, into 3. You guys are ahead of me here. 3 into 0.9 into 0.1 into 0.1. Even more generally, let me be even smarter than you are. I'm going to write this as 3 choose 1 into 0.1 to the power 2 into 0.9 to the power 1. It's a slightly sophisticated way of writing the same thing. Correct? Why did I write it as 3 choose 1? Because why was it 3? How many ways could there have been 2 defectives out of 3? So correctly speaking, I should actually have written this as 3 choose 1 or 3 choose 2. Because either I can choose it as 1 good or I can say it is 2 bad. So 3 choose 2 is the same as 3 choose 1, whichever way you want to write it. So maybe a slightly better way to do it would be to say this is 3 choose 2. What are these 2? The 2 bad defectives out of 3. What is this 0.1? The chance of a 1 defective. What is this 2? There were 2 of them. What is this 0.9? The chance of the good. Right? So, how many goods, how many bads were there? 2. How many goods were there? 1. In how many ways could I have chosen 2 bads out of 3? 3 of them. Okay. This is the answer. This is an example of a distribution called the binomial distribution, which we'll see. And this calculation you don't need to calculate, your Python will do for you, like all good things. Right? The look and feel for many of these classes is see it once, understand it, and then ignore it. Because someone else can do the calculation for you. We'll do it, not to worry. We'll get to it after the break. But what is the answer? 3 into say 0.1 into 0.1 into 0.9. Somebody tell me what that is. I've got no idea. 2.43%. 0.0243. This number. Someone verify on their 0.027. Okay, and about 2%, 2.7% or a little over 2%. That is the chance of seeing 2 defects. When the chance of seeing a single defect was. So now this is, as you can see, this calculation is not about defects or anything of that sort. This is just a counting argument. This is just a counting argument. So for example, I could have asked the question that I'm trying to sell a product to 3 people. My chances of success is I don't know, 10%. What's the chance that I'll be able to sell to 2 of them? Today I'm a salesperson. I know I can call upon, I'm going to 3 houses today. Let's say that I sell children's books. I've gone to schools, I've set up my stall, Dukan Khul Diya, and I've got 3 addresses of parents who have been kind enough to say, please come to my home and I'm willing to listen to you. So now I have on my cell phone 3 addresses I'm going to go to today. I know that my chances of selling this are not good, optimistically even 10%, which means that if I try to sell to 10 people, only 1 will probably buy. So my chances of success for a single person is about 10%. So now I can ask myself, what is going to happen at the end of today? How many will I sell? What is the chance that nobody will buy? What is the chance that 1 person will buy? What is the chance that 2 of them will buy? And what is the chance that all 3 of them will buy? So what is the chance that 2 of them will buy? 2.7%. There's only about a 2.5% or roughly 2 to 3% chance that I'll end up with 2 of these people buying. Not? No. For me, I define 10% as buying. So which is I'm saying that this calculation doesn't depend upon whether it's defective or is buying anything. What it depends on is the probability of an event. And you're asking the question, how many times will this happen? And that can be a defective part, that can be a sale, that can be the loss of value of a portfolio, that can be the attrition of a person, that can be a hit on a website, that can be a click-through rate, it can be a very small number. For those of you who are in digital marketing, what's a typical CTR? What's a typical click-through rate? Any of you in that industry? So what's a typical click-through rate for you? Website clicks? Email clicks, but what's a click-through rate? So what a click-through rate typically means is, of the people who pass through an application, for whom the application is an image, in other words, an impression as they say, what percentage of them actually click on it? This is very important for digital marketing. So you're showing ads. All these websites come with ads, etc. Someone's paying for those ads and they want to know what the click-through rate is. When I see the ad, what percentage of people click on the ad? And it's typically a very small number. Have you ever clicked on an ad? No, most normal people don't. But people still advertise. People still advertise. Click-through rate is very small. Let's say click-through rate is 0.3%. Let's say. That means 3 out of 1,000 people can be expected to click through. Now I can ask the question, for example, that if I want to have, let's say, so how many impressions should I have? That depends on how many clicks I expect to have, I expect to see. So if I want to have, let's say, 100 people clicking on my ad, that gives me a rough idea as to how many I should reach, how many impressions I should be having. I can also answer a question like this: what is the chance that I will have more, or let's say less than 100 people clicking? So you can ask the question, what is the chance that less than 100 people click in a month? How do I calculate that? With this, I can, because what I need is an estimate of how many impressions there are in a month. From that is, shall I say, my n. Now if that is an n, I can then calculate, yes.
Just on this, we are trying to calculate for 2 defective.
Yes.
So why we have not added that all 3 defective?
I could have, if I wanted to do at least 2, right? If I was solving this question, at least 2, then you're absolutely right. I should have added the last one. There's a question of, so I'd written it as this, probability of 2 defectives. If I'd written it as at least 2, you're absolutely right. I should have done that. I could have done that.
Sir, how do you define this impression? I'm not.
An impression is basically so on a website, if you see the ad, in other words, for a session, so someone has gone to that website and that ad is present on that website at that point in time, that's an impression. If someone has actually clicked on that ad in that session, that's a click. So the click-through rate essentially is, if I'm showing you the impression, are you clicking on it? So I can look at the number of impressions, because basically that's the number of times that website has been visualized and that ad has been on it. I can also calculate the click-through rate, how many people are looking at that. And now I can ask the question, what is the chance that I have less than this? So then what would I do? This number would be, let's say, the number of impressions. This would be, say, 100. And this would be, say, my click-through rate. And this would be my 1 minus my click-through rate. So my 0.03 to the power, say, 100, those 100 people who clicked, the number of impressions minus 100 people who did not click, and the number of ways in which I can get 100 people out of, let's say, I don't know, 1,000,000 impressions. I do a calculation like that. I wouldn't do it, I'd get someone to do it for me. So this is where we are heading. Now I'm going to slow down a little bit, take you through this conceptually, just to get these terms understood slightly. So first of all, what is a probability? A probability is a number between 0 and 1. It is often calculated as a ratio, the number of ways that is favorable divided by the total number of outcomes. This is not the only way of calculating a probability, and it very rarely works, but it is often a conceptually easy way to understand. It's a number between 0 and 1. 0 means impossible, 1 means certain. The probability is a pure number, it doesn't have units. The philosophical question of is the glass half full or half empty? Types of probability, different ways of doing it. Now here's what I was talking about as mutually exclusive events. These are two things that have nothing in common. Mutually exclusive, they exclude each other out. An example, if you are drawing from a deck of cards, you can either draw a king or you can queen or neither of them, but if you are drawing one card, you cannot draw both a king and a queen. Just like if you are drawing a part, it's either defective or it is not defective. If you are a physicist, you would think of Schrodinger's cat. And so physicists have a lot of fun with this. You know the story of Schrodinger's cat, right? So Schrodinger gave an example of a cat, saying it's like the position of an electron. So there's a cat in a box, and this is very unfortunate for the cat. And there's a vial of poison. Now that vial of poison is a little unsteady. So it could fall down, it could break open, and if it does, then the box fills up with fumes and the cat dies. So you know that there's a vial of poison in the box and there's a cat. Now the question is the cat dead or alive? It's a closed box. You know that there's poison in the box and there is a cat. Question is the cat dead or alive? And the answer is, you do not know until you open the box. Now if you open the box, you can see whether the cat is alive or dead. This is called collapse of the wave function in quantum physics, which means that the event has already happened. But until the wave function is collapsed, you do not know whether the cat is alive or dead. If you can observe an electron, the electron is here. But if you are not observing the electron, you don't know where the electron is. It could be here or there or anywhere. So the electron is buzzing around the room. In physics, this is an important idea, and a lot of probability theory has come from physical considerations. If things are mutually exclusive, you can add up the probability as we had said. This is king or a queen. What about two independent events? Two independent events are events such that if one of them happens, then it no way influences the occurrence of the other one. In other words, if he buys, then nothing about it. If one of them is a defective, it says nothing about the other thing being a defective. So let me ask you a question now. Let me go back to my previous picture of mutually disjoint events. Are these two events independent? No. Why are they not independent? Yes. If I know that the king is drawn, I know something about whether the queen has been drawn or not. I know in fact that the queen has not been drawn. These two are most certainly not independent. So please don't confuse these two concepts.
So you are talking about the next event for the next event.
No, I'm talking about the same event. I'm talking about these two events. So for example, if I talk about, let's say one particular unit being G or D, good or defective. If I'm talking about one of them, then the picture looks like this. It can either be G or it can be D. It cannot be both. This is for one of them. But if I am talking about two of them, then say this can be G1 and this can be say D2. In other words, the chance that the first is good and the second is defective. Now these two are no longer disjoint. Why? Because both these things can happen together. It is quite possible that the first is good and the second is defective. That's quite possible. But they're independent. Independent means If I know that the first is good, it tells me nothing about whether the second is defective or not. So, if your picture sort of intersects, then you know that you cannot add up the probability. In fact, you know a little bit more. You know that if you want to add up the probability, you can, but you have to somehow take out this little common part. So, disjoint, two separate things. You add it up. It's a or. This or this, not both. If such a situation happens, you can add the probability up. And you can also add up, but you need to assume independence. We will break all these assumptions soon. This is the simplest possible way to do calculations. I have to get to a little bit of a nightmare called Bayes' theorem. Rules for computing probabilities. This language here, the cup and cap language, this is from set theory. Some people find it comforting to see that language, others find it complicating. It's called the union. So, union means, so union in general means the collection of two things. So, let's say this. This is A and B, probability of A or B if there is a common part, then probability of A or B is equal to probability of A plus probability of B minus probability of A and B. The chance that both happens is the chance that one happens plus the chance that the second happens minus the chance that they both happen. If things are disjoint, then this becomes 0 because I know that both cannot happen. But in general, this term stays. This is called the intersection. They both happen simultaneously. Here's an example. What is the probability that the selected card is a king or a queen? So, this assumes that you know what a card deck is. So, 52 cards, 4 suits. So, how many kings? 4 kings. How many queens? 4 queens. So, what is the probability of a king? 4 by 52, 1 by 13. What is the probability of a queen? 13. What is the probability of a king or a queen?
1 by 13
plus probability of a queen 2 by 13. The other way to do it is, if you want to, how many ways can you get a king or a queen? 8 ways. 8 divided by 52, which is also the same number. What about the second one? What is the probability that the selected is a king or a diamond? So again, there are 2 ways of doing this. P of king or diamond is P of king plus P of diamond minus P of king and diamond. This is, let's stay on 52s, this is, so this is 4 by 52, 1 by 13 is also correct, plus probability of diamond 13 by 52 minus king and diamond, there is only one such card, 1 by 52. This is 15 by 52. Another way of doing it is, how many ways can you get a king or a diamond? 16 ways. The whole suite of diamonds, and there are 3 remaining kings. Or there are 13 diamonds, there are 4 kings, but I have double counted one of them in both, so I should subtract it once.
The second statement seems a little ambiguous.
Remind me what the second statement was, I forgot.
King or a diamond.
Oh, the question? Okay, you're saying there's a king, selected card is a king or a diamond. You're drawing one card at random from a deck of cards and you're asking, is this a king or a diamond? Let's say I'm trying to sell him something, correct? One event that I'm interested in is he going to buy my product or not? The other interesting question is, let's say for example, is he an IT professional or not? Correct? Now, is there a relationship between these two things? Not really. But I may be interested in the joint probability of them, not because of this event, but because I want to calculate another event that's interesting to me, which is, if I know that he's an IT professional, can I sell him something? In other words, suppose it is not independent. Suppose I now know that whether he buys my product or not depends on whether he's an IT professional or something else. Let's say I'm trying to sell him a computer peripheral. And I may be assuming that if he's an IT professional, he may be more interested in a computer peripheral. If he's not, he may still be interested, but if he's an IT professional, he may be more interested in this particular peripheral. In that case, what I try to do is I try to use one unrelated event as information about another one. In other words, I'm saying it is not actually unrelated. So these ands become interesting. So effectively, how will my calculation go? My calculation will go this way, that if I want to find the probability that he will buy my product, given that he is an IT professional, then my answer will be, let me find the probability that he's both will buy the product and an IT professional divided by whether he's an IT professional. Why? Let me first calculate the chance he's an IT professional. Within that, let me now find the chance that he will buy my product. A given B is equal to A and B divided by B. This trick is always used in analytics to say this, and we'll do it before. I've received an email. Is it spam or not? Which means I need to tell me the words and I will tell you whether it is spam. So now I need to relate the words to spam. So I have two unrelated concepts, but what I want to do is I want to say that if I know one of them, maybe I can get some information about the other. Similarly here, this may be about a color and this may be about a suit, but if I know about one of them, maybe it gives me a little bit of information about the other. We'll see examples later.
Just thinking, so what if there was an additional question to this, so king or a diamond or both?
It can't be both because I'm drawing one card. Oh, you're asking just about this? That's 1 on 52.
So what if the question was king or a diamond?
What is challenging is that is this an exclusive OR? He's asking is this an XOR in computer science? In other words, he's saying that when I say OR, am I excluding the case that both are allowed?
But you are being a single card.
No, that confusion still remains if he's very picky. So he could say he's making a distinction between two statements, king or a queen, king or a diamond, or king or a diamond or both. You need to specify both. And in that, yes, you are correct.
Exclusive or needs to be mentioned explicitly.
So his mind works in ways in which the default is the exclusive. Your mind works in ways in which the default is not the exclusive. But it's a valid criticism to make. That in English language, when you use it, which OR do you mean? When I say this, in probability theory, if I say A union B, and if there is an intersection, I include that intersection. Set theory is not confused about this. For set theory, A union B is just this set. And if there is a common part, that's in it. And in it only once. It's this region. So what I did was we translated this into set theory, and he's saying that maybe I should have been a little more careful, because there's a difference between this set and the following set, which is just this part and this part. Multiplication rule, when things are independent, I am allowed to multiply. An example, there are two subjects, the chance that you will do well in one of them is 70%, the chance that you will do well in the other is 5%, the chance that you will do well in both of them or A and B the corresponding grades is the multiplication of the two, which is 35%. Here comes the interesting part. What happens to events which are not independent? What happens to the what happens to the multiplication? And there are various ways in which this part is written. So currently the way the formula is written is A and B is equal to A multiplied by multiplied by probability B given A. This is the way this expression is written. Sometimes it's easy to understand this way, sometimes it's easy to understand this way. Probability of B given A is equal to probability of A and B divided by probability of A. I want to know what is the chance that B will happen when I've already been told that A will happen. So first I find what is the chance that A will happen, and within that I take the fraction of both A and B happening. This is the same as saying the top line A and B is equal to A given B. This means what? This means A and B is first A happens, then given that A has happened, B has happened. Correct? If A and B are independent, what do I know? If A and B are independent, then A and B is A into B of B. That means that if A and B are independent, probability of B given A is equal to probability of B. Stare at that for a while. If they are independent, then this will become P of B, and so P of B given A will equal P of B. But is this not exactly what independence is? If I tell you that A has happened, I have not changed the chance of B. That is almost by definition what independence is. That by knowing that one of them has happened has told me nothing about the second one. By knowing that the first unit was defective told me nothing about the second one. By knowing that the first customer bought my product told me nothing about whether the second one will buy it or not. So these statements are understood in different ways. Sometimes this is a good way to understand it, sometimes this is, sometimes this is. But this is a more general form for doing it. We'll see examples of this. This one needs a little bit of work to understand. From a pack of cards, two cards are drawn in succession, one after the other. After every draw, the selected card is not replaced. So you're drawing one, it's like a normal deal. The second one now comes after the first one. What is the probability that you get both draws, you will get spades? In other words, you will get two spades. Two draws, two spades. What is the chance of that? So here's a structuring of the problem. A is that you get a spade in the first draw. B is you get a spade in the second draw. So what is the chance of A? The chance of A is 13 by 52. Is the chance of the first one is a spade. Now, I want to find A and B, and the way I do it is this. What is the chance of A and then what is the chance of B given A? In other words, I've drawn a spade, and then what is the chance that I will draw a spade given that I've already drawn a spade the first time? And the answer to that is -1 because there are now 51 cards left in the deck and there are 12 spades remaining. So 12 by 51. So the answer is 13 by 52 multiplied by 12 by 51. Now what would the answer have been if I had replaced the first card? It would have been 13 by 52 multiplied by 13 by 52 because of independence. I put it back, right? If I put it back, when I put it back, the second draw looks exactly like the first one. So knowing that I had a spade to begin with has been lost because I've already put that spade back in. It is a situation of independent experiments. This one, however, is the case that the result of the first or the result of the second depends upon the result of the first.
But isn't it like we are assuming the second one that we have already picked the first one as a spade?
Because that is what is being asked for. What is the probability that in both the draws you will get spades? So I am drawing one and I am drawing a second one. What is the chance that they are both spades? Here's a similar-ish question. What is the chance that I will get two adjacent seats on my flight if I don't pre-book? Yeah, so it's a similar kind of calculation. Why is it a similar kind of calculation?
One is already checked. One is the same seat again.
So you want two adjacent seats, but for two adjacent seats to be picked by you, there must be two empty adjacent seats. Now, two adjacent empty seats means what? That means, can you calculate that probability? Yes, you can. But when somebody books seats, let's say that one particular seat has been booked. What happens to the probability of the seat next to it being booked? So the probability of a seat being booked, of a single seat being booked, let's say is, making up a number, let's say 50%. A single seat being booked is 50%. Now I'm telling you that one particular seat has been booked. Let's say, 15A has been booked. Now I'm asking the question, given that 15A has been booked, what is the chance that 15B will be booked? Will it be 50%? Will it be more than 50%? Will it be less than 50%? It will be more than 50%. At least if you are modeling reasonably well, it would be. Because a whole bunch of people will be booking pairs. So now, if I know that one seat has been booked, if I know that 15A has been booked, now the chance that 15B has been booked is going to be more than 50%. Which means that my chances of coming late and finding two adjacent seats is going to go down. Because I am looking for seats that are unbooked.
Chances will be more, right?
No, the chances will be less because as people book, so people book adjacent seats more than at random. So the probability of two adjacent seats being booked is not the product of the individual seats being booked. It's more than that. So the probability of me finding two empty adjacent seats is going to be less. Because I'm looking for empty seats. So here's an example of doing this conditional calculation. Marginal probability is a term I'll explain when I do the example. So here's an example. A survey of 200 families was conducted. Information regarding family income per year and whether the family buys a car are given in the following table. So the 200 data points, 200 surveys have come and they've been distributed in a cross tabulation like this. We did a cross tab like this yesterday as well. This is the cross tab. One axis is, did they buy a car or did they not buy a car? The other is an income statement. Income below 10 lakhs or income greater than 10 lakhs. Now why might I be interested in this data?
Which segment?
To figure out who buys my cars, whether cars can be sold and whether that has anything to do with income. And if it does have anything to do with income, then is high better or is low better? I don't know. So what I've done is I've arranged my data in this particular way. And now it's asking a few questions. What is the probability that a randomly selected person, or what is the probability someone is a buyer of a car? You don't even need to look at the full table. This is 80 by 200. Probability of, let's say, car. This is called a marginal probability. Why marginal? Because from the picture, it's at the margin. It's at the margin of the table, which is where the term originally came from. This is called a marginal probability. There are many things going on, but you're asking a question only about one margin. In this case, the margin of the car. You're not interested in the income. This is called a marginal probability. What is the probability that randomly selected family is both a buyer of a car and belonging to income 10 lakhs or above? Both buying a car and income 10 lakhs or above. $42 on 200. Okay. A family selected random is found to be belonging to an income of 10 lakhs and above. What is the probability that the family is a buyer of a car? If the income is more than 10 lakhs, what is the chance of a car? So, this is probability of car given greater than 10 lakhs. 42 by 80, interesting, 42 by 80. Why is this? You're right. Is 80? That's the sample size? Right. You understand the logic? But that is exactly the same as this. Probability of car and greater than 10 lakhs divided by greater than 10 lakhs. Why? Because car and greater than 10 lakhs is 42 divided by 200 and greater than 10 lakhs 80 divided by 200. 200 cancel out. This again becomes 42 by 80. But the thinking is absolutely right. This goes in the denominator because this somehow says that out of how many people am I going to select? And then on the top is how many are both. This is called a conditional probability. This is called a conditional probability. By the way, what is this number? This is, for example, less than 50%, greater than 50%. What is the chance of buying a car? Which is about 40%. That means, if I did not know your income, I would guess that your chance of buying a car is 40%. If I did know that your income was more than 10 lakhs, now your chances of buying a car went up to over 50%. Therefore, it's worth my while to find out whether your income is more than 10 lakhs. Because it, at least by the sample data, tells me that that's going to influence in a positive direction whether you will buy my product or not. So I'll try to find out. This is, in terms of words, this is called a marginal probability. Marginal. And this is a conditional. You might have a little bit of trouble with these words, but conceptually this is not very hard. And so this is the calculation that we just did. Bayes, when he originally wrote this paper, so he talked about it, nobody understood him. Only after he died did somebody find it in his papers, and I said, okay, this is going to take a long time, and then they explained it to others. Let me explain what it tries to do. Yes?
So that middleman, what is that called? Is it a no?
On the board? Car and greater than 10 lakhs.
That's fine. You said the marginal probability and there is a condition.
This one, okay. This one is a joint probability. This is a marginal, this is a joint, and this is a conditional. So a conditional is a joint by a marginal. A conditional is a joint divided by a marginal. A joint is a marginal multiplied by a conditional. So the Bayes' theorem's idea is the following. What it does is, it switches which event is being conditioned on. it switches between A given B and B given A. Now, when would you need to do this? Here's an example. You want to find out whether the email that you're receiving is spam. Do you use Gmail? Gmail often identifies things as spam and moves them somewhere. How does it do that? Partly it looks at the mails and headers and it uses a very, very complicated algorithm. But let's suppose you are building an application of this sort and you want to do it based just on the content of the email. So you want a following kind of program. You want a program that says that if I know the words of the email, I can tell you whether it is spam or not. Which means I want the following thing. I want the probability of spam given words. If I tell you the words, can you tell me whether this is spam or not? This is what I want to do. Correct? But how will I solve the problem? I'll solve the problem by finding the opposite conditional. What is the opposite conditional? The opposite conditional is what is the probability of words given spam. Now, why am I interested in this? Because this one is easier for me to do in the following sense. What I can do is, let's say in my research lab, I can collect lots and lots of documents and I can identify them as spam or not spam. In other words, I can manually go in and I can tag them. So let's suppose that I've looked at 1,000 of these and I've targeted, let's say 800 of them as spam and 200 of them as non-spam. Or maybe I go after things that are spam and find 5,000 of them and go after things that I know are not spam and find 5,000 of them. Now I can solve the opposite problem, which means that if I know that it is spam, I know the distribution of words. And if I know that it is not spam, I know the distribution of words. I can do this inside my analytics environment. So now I know that if it is spam, this is what the distribution of words looks like. If it is not spam, this is what the distribution of words look like. Using that, I will now twist the problem and say, now if you give me the words, I will tell you whether it is spam or not. Now, how do I do that? I do that doing this. Now, this is a very easy formula to understand. Why? Because this formula essentially says this, that why is this equality true? This equality is true because let me rewrite it slightly. Let me say, what is the probability of, let's say, spam and words? What is the chance of spam and words? In other words, there is an and there. Now I'm going to write this like A and B. But here's the interesting thing. When I wrote, I can write A and B in two ways. I can write it as B multiplied by A given B, but I can also write it as A multiplied by B given A. I have a choice as to which is first and which is second. So therefore, I can write this in two ways. I can write this as spam given words multiplied by words, but I can also write it as words given spam multiplied by spam. Do you understand the trick? But what does that mean? That means these two things are equal?
No.
If these two things are equal, that expression now follows. Now I know that probability of spam given words is equal to the probability of words given spam multiplied by probability of spam divided by probability of words. So to execute on this, what do I need? Words given spam, which I told you what to do. Probability of spam, which is an estimate of the proportion of emails that are spam or not spam. And probability of words that has no conditioning in it. This is what's usually called a lexicon or a dictionary. So if you give me a dictionary of the language, I can give you this denominator. If you give me, shall we say, an IT estimate or a sociological estimate as to the proportion of words or proportion of emails that end up being spam, I can give you the probability of spam. And if you give me things tagged as spam, I can find its dictionary distributions. If you give me things that are tagged as not spam, I can find it. So therefore, I know the right hand side. Therefore, I know the left hand side. And now if you give me the words, I can tell you the probability that it is spam. So it's either thought of in the way I just described it, which is sort of flipping these two probabilities. Sometimes it is described the following way. Spam given words is an update of just probability of spam. This probability of spam part is sometimes in Bayesian language called a prior. And spam given words is called a posterior. Which means that if I know the words, I have a greater idea as to whether it is spam or not. If I know his income, if I know he's an IT professional, I have a better idea whether he'll buy the product or not. If I know the income is more than 10 lakhs, I have a better idea whether he'll buy a car or not. If I know the words, I have a better idea whether it is spam or not. And to do that, I flip it this way. And because of applications like this, Bayes' theorem has become very, very central to machine learning. Because, for example, think of the autonomous car. What is the autonomous car's decision problem? Something is crossing the road. Should I stop? In other words, given cow, should I stop? Now think of the problem that has to be solved to do that. I can flip it. Now to flip it means what? To flip it means essentially flip it by saying cow then stop. Essentially I now have to tell the program, so I say stop given cow. So now I have to solve it by Bayes' theorem, cow given stop. So I need to say these are the situations in which a car has stopped and these are the situations in which a car has not stopped. So in a stopped situation, look at what that car saw, and in a not stopped situation, look at what the car saw. Like spam and not spam. And now I can flip this and say, therefore, if this is what I saw, I now know whether to stop or not. It's a neat little logic. So this is what Bayes' theorem essentially does.
So it will be a foundation to supervised learning, right?
It is one way of doing supervised learning. It is one style of doing supervised learning. And there are supervised learning algorithms that are explicitly this. For example, Bayesian belief networks or BBNs. There are some supervised learning algorithms that are this but aren't explicitly so. For example, linear discriminant analysis, where what you do is you find the posterior distribution of being in this class given the data. And so this class given the data is written as, class given data. So, and vice versa. So there are at least two of these algorithms that you will study later. Discriminant analysis is one, and I think BBNs, I don't know its curriculum, but in general, you will find it to be a very useful trick. I'll come back and I'll show you the theory behind it if you're interested, but this is actually all that needs to be remembered for its application. So the question is in autonomous cars. His question is, why don't I do the simple thing of saying that if you see something, stop? Now for a computer, following that logic, the computer now has to know what should I do when I see something. Not if I see something and stop. So he could say if I see something on the road, then stop. It will then ask what happens if I don't see something. I should keep going. So this becomes a very simple rule that says that if I see something, stop. If I sort of don't see anything, stop. Now what will this do to the car?
It won't stop in a signal.
Correct. So this is a translation of a rule. The difficulty will be the following, and you can try doing it. The difficulty will be that what precisely will the car see? And it will follow that logic explicitly. So if it sees a car that is coming quite far ahead, it will stop. Now you could say, I'm going to draw a threshold. If it is further away from this in front, the car in front, then don't stop. Because you're expected to see a car in front. And so if you're seeing a car in front, please don't stop because something is in front. But you now have to encode that. And so that way of doing things is entirely feasible. So for example, there's a whole branch of learning called case-based reasoning. Case-based reasoning, and case-based reasoning essentially lies on that. Give me all the cases and give me the reasonings for all those cases. But case-based reasoning sometimes becomes difficult if it becomes very, very difficult to enumerate all the possible cases. For example, in the spam problem, I have to solve this problem for every conceivable word that the email might see. Because the email is going to decide based on the words. And if you do a full case-based approach, if the email sees a word that it has not seen before, the email will say, what do you want me to do? So typically when Bayesian methods are used, when it sees that word, it will do precisely nothing. In other words, it will say, if certain words are there, I will update my decision. If those words are not there, I won't. It's irrelevant to it. There is no evidence that it has. So the other is a probabilistic way of thinking that Bayes' theorem or any of these relate, and this is probabilistic learning. That when you do when an autonomous system or any machine learning system decides, then what does it decide on? So you'll often find in data sets the following situation. I should have had an example, I'll pull it up. All the x's are the same, but the y's are different. All the x's are the same, but the y's are different. Two people have exactly the same characteristics, but one has bought the product and one has not bought the product. Two people applying for a loan have given you the same information. They come from the same village, they have the same income, they have the same family circumstances, they grow the same crops. One farmer has repaid the loan, the other farmer has not. Car being tested out, there's someone crossing the road, identical scene. One test driver decided to stop, the other test driver decided not to stop. Same x, different y. What should the computer do? Now think of this from a computer's perspective. What is the computer's problem? The computer's problem is, if you give me an x, I will give you a y. Now what do you want the computer to do in this particular situation? Because in your real data, the same x is leading to different y's. Now what's an ideal solution here? What would you do? How would you think through this problem? One possibility is to give it a probability. That's one approach to the problem. What that means is this, that in your data set, let's say half your people who have seen this x have given a y of 0, and half your people who have seen this data set have given it a y of 1. The computer literally tosses a coin and decides which one to predict. That's called a randomized response, and sometimes it's done.
But that could be a disaster as well, no?
I'm sorry?
That could become a disaster as well.
It could. But give me another alternative.
Safest alternative we could go for, right?
Which is safe? How does a computer know that? What condition? Is given the same x, its input is identical.
But action, what are the consequences of this action? When you stop, is there anything happen? Any problem has happened?
See, that consequence has already been worked out in nature. In nature, if that consequence was there, that would have already have been baked in. So, if there is a consequence to it, and if there was a good consequence, then the test driver would have stopped. In all cases, the test driver would have stopped.
No, the action of stopping. The
Yes.
action of stopping and going.
Yes.
You take that in discretion, which is more fatal. Going is always fatal. Stopping is fatal.
That decision would have been made by the test driver as well. Would it not have been? The raw data would also have shown that bias. Or are you teaching a computer to have a sense of value that the real human did not have? Two doctors look at the identical medical report. One doctor says cancer, the other doctor says no cancer. You are building an AI system for medicine. What should it say?
Go for another test.
Go for another test. Okay. You should see you should see a very nice video of Watson. You know what Watson is? You should see the Watson videos. If you haven't seen it and you want to be an AI ML professional or an ML professional, then you should see the Watson videos. Wonderful videos, and you can see the decisions at the bottom. You can see how Watson decides. You know what Watson? This is the Jeopardy videos. So Watson playing Jeopardy, and so Jeopardy is a quiz question in which basically the answer is given and you have to sort of say the question or something of that sort. So when you see the video, you'll see at the bottom you'll see a bar, and that bar is basically a set of probability statements as to how likely is this the answer, etc., etc. And based on those probabilities, Watson gives an answer, and sometimes Watson does not give an answer because it is unsure of even its best answer. So when you watch it, watch the bottom of the screen, the data that Watson is answering based on. This particular way of doing things, but in general, this problem is a hard problem in machine learning, because in the real world you will have this issue. If this was not the case, if it was the case that identical values of x gave identical values of y, the machine learning problem would be a mathematical function fitting problem. It would be a problem of simply saying if this is the x, map it to the y. Just find the rule that maps it to the y. It's not. And the reason it's not is because identical inputs do not lead to identical outputs. And resolution of that has many procedures and possibilities for doing that. One of them is a probabilistic way of doing things. To answer the following question, I will not tell you whether y is 0 or 1. I will tell you what is the probability that y is 1. I will not tell you whether you have cancer or not. I will tell you what is the probability that you have cancer. I will not tell you what the probability of hitting something will be if I continue. It's not a definite answer. So I'm asking for a 0 or a 1, and I'm not giving you a 0 or a 1. I'm giving you a probability. So at every time the car, when it is driving, is calculating a number. Given the scene, what is the probability that I will hit something? Continuously, based on what it is seeing. Now you decide based on that probability whether you should stop or not. Based on your risks, etc. The learning system does not do that. The learning system does not say whether you should be diagnosed with cancer. It simply says what is the chance that you have cancer. Now you decide based on your logic as to whether that's enough for me to state whether you have cancer or not. The learning system will not say what is the probability that you have defaulted on, it will not say whether you will default on your loan or not. It will say what is the probability that you will default on the loan. Now you decide how much risk you will bear. That's one solution to the problem. It doesn't even try to predict the right answer. It simply gives you a distribution on the possible answers. Now you decide. As I said, if you see the Jeopardy videos, you'll see this in action. You'll see the data on which it does.
The category is 19th century novelists.
What Watson wants to do then is preserve the lead, not take a big risk, especially with Final Jeopardy, because just like for humans, Final Jeopardy is hard for Watson.
Now we come to Watson, who is Bram Stoker, and the wager. Hello.
See the full video.
973.
It's enormous fun.
Total of 77,147.
I would have thought that technology like this was years away, but it's here now. I have the bruised.
Phenomenal.
Watson went on a tear.
Watson.
Look at that. What it's doing is it's given probabilities on the answers. These don't add up to 1. These don't add up to 1. But what is the chance that list is the right answer? what is the chance Chopin is, etc., etc. This number, if it is below this threshold, Watson will say pass, it won't answer, and is there in the video a few number of times. It doesn't know, but it says that if I am more sure than a certain threshold, and if I am uniquely sure, it will also not answer if multiple of these cross here, which means both of them are probably right and I don't know which is right. They both sound correct to me. Again, I might stop.
So for each question, Watson will check what is the probability of the...
He'll do that. Every question, based on hearing it.
So if probability is done by Python language or any of the machine language thing, then what is that we are here for? Meaning, what is our role in deciding that?
Deep philosophical questions. Why are we existing at all? Why are we here at all? So one reason you're there is to provide test data to the system, or what's called ground truth. In other words, you need to give it spam, and you need to tell it once that this is spam. Just like he's saying, I need to tell it to stop. I need to say that this is a dangerous thing. So a human needs to initiate that. But yes, people are asking that question a lot. That is that human initiation necessary? Now the trouble with that is that the value system that is necessary to decide that this is a good thing or a bad thing is something that computers do not have. And it's extremely difficult to encode that. It's a lot easier to encode in a computer in some way, this is good, or this is one decision, this is one decision, and also if you want to encode a cost to it. And if I do this, this is what cost. If reinforcement learning does this. If you take a wrong decision, there's a penalty function that hurts the computer in terms of an objective. And the computer knows that if I want to reduce, shall I say, that pain factor, I should avoid doing this, like babies learn. That's called reinforcement learning. I don't know whether you'll do much reinforcement learning in this course or not, but you will do that. So you build algorithms of that kind. There will come a time where that will not be necessary. For us, it is not necessary. But even humans, have to come with our genetically coded information. We also cannot begin from scratch. We already come coded with this. There's a school of thought that says that that's all that there is, that this information is passing along. In other words, a hen is an egg's way of making another egg. So an egg wants to make another egg, right? Now how does an egg make another egg? Through a hen. It makes a hen. And that hen makes the egg, another egg, right? So, which means that there is a basic information content. The gene is trying to say, I need to survive. So there's a sequence of A, C, Ds and Gs that has a survival instinct. And the only way it can do that is to get another organism to create a copy of it. Viruses do that brilliantly, right? The big war going on planet Earth for a few billion years and still continuing. It's a deadly war, it's got no winners and is going to continue. Is a war between bacteria and viruses. Nobody wins, right? These two are at each other for donkey's years because they have two very different ways of dealing with information. Right? A virus is a retrovirus type thing. A virus is basically just DNA with a protein around it. The way it reproduces is like certain birds we learn in mythology. That information gets into another organism, typically a bacteria. So a virus forces a bacteria to make another virus. And obviously the bacteria doesn't like it. And so the bacteria over billions of years have figured out how to prevent doing this, and viruses have consequently adapted and have repeatedly kept doing this. And so information transference has a long history in the real world. In the computing world, the challenge of saying that how do I input the information, how do I get the machine to learn is something that we are rapidly evolving in. The reason this current generation is so excited about it, and I'm not that old, but even in my career, and I've been doing this for, I don't know, about 25 years or so, roughly speaking, I've seen 3 or 4 waves of it. It goes up, it goes down, it goes up, it goes down, and different. The current version of it essentially is based on certain deep learning algorithms that have come and have made it a lot easier to feed back information. So, recurrent neural networks, all these neural networks now have the ability to feed context and feed information a lot more efficiently, which means this idea that a computer can pick up context and use it to get better algorithms is there. And that scares a few people mightily. Because what it means is that as a car keeps driving very well, it's knowing that it's driving very well and it will keep doing certain things. So there's a school of thought that says that therefore maybe the car should have a few accidents. Just like maybe there should be a few nuclear explosions. Let's suppose that you go and get an HIV test done. HIV tests are routinely done. Let's say you have surgery or anything like that, etc. HIV tests are done. So let's suppose that for whatever be the reason, an HIV test gets done. And the test turns out to be positive. I hope it never happens to you, but let's suppose the test turns out to be positive. The question is, how scared should you be? Very, that's a reasonable answer. But let's work it out. So, to do that, trying to calculate the probability of HIV given positive test. This is what I'm interested in calculating because my life may depend on it. There are many ways to do this. Here's a suggested route. Now, what I'm going to do is I'm going to write this version of the formula down. Without necessarily, and you'll see what it means here. So what I'm going to do is this, I'm going to write this as probability of HIV and plus divided by probability of positive. Correct? Conditional is joint divided by marginal. Now, I am going to write the numerator as probability of positive given HIV multiplied by probability of HIV. I am going to twist it. Here's why. These are numbers that are much more available to me. What is this number? This number means that if I have HIV, what is the chance that the test will be positive? That's called the sensitivity of a test. A test maker has to report that. This is the proportion of people who have HIV. This is the incidence rate. It has nothing to do with me. It's like my dictionary. It's just the fraction of people who have HIV. So these are numbers that I know. One from epidemiology and one from my test manufacturer. Divided by positive. And I'm going to do something very interesting on the positive. I'm going to write this positive in two ways. There are two ways in which someone can become positive. HIV and positive plus not HIV and positive. Okay? Disjoint. There are two disjoint ways in which I can end up being positive. Either I have the disease or I do not have the disease. Now I can write this as this I had already calculated. It's the same number. Probability of positive given HIV multiplied by probability HIV plus probability of positive given not HIV multiplied by probability not HIV. This is this formula just exampled out. We're going to apply this and see what happens. What are the numbers that I need? I need a number of probability of HIV. Probability of HIV is a incidence rate for HIV. What's a good number for this? 0.01? Well, okay. Let's say 0.1%. That's actually very low. The HIV rate is a lot higher. Or let's say 1%. 1% of people have HIV and 99% don't. What this also means is that probability of not HIV is 99%. Okay. I also need a few other things. I need, for example, this probability of positive given HIV. This is a measure of how good the test is. If you have HIV, what is the chance that it will report that you have HIV? What's a good number for this? 99%? 95%? What does 95% mean? That if you have HIV, there is a 95% chance that I will find it. Equivalently, for 100 people who have HIV, for 95 of them I will find it. Yes?
Can you please repeat this part?
Which one?
Positive HIV, how do you conclude that 95%?
I asked. This will come from the, this is called a sensitivity number. It comes from the test. A very good test may have this at 99%, 99.9%. A not very good test or a cheap test may have this at 90%. I am assuming that this test has 95%. Pick your own number. Its sensitivity is 90%. The other number is sometimes called specificity. So, for example, let's say I go the other way. Positive of negative given not HIV, which means if you do not have HIV, what is the chance that it will say you do not have HIV? Again 95%? Again 95%. In other words, I have a fairly simple test which is 95% accurate. Whatever your disease state is, 95% of the time it will give you the right answer. Okay? Now let me re-ask the question. I've given you a test that is 95% accurate. I'm now telling you that your test is positive. What is the chance that you are HIV positive? 95%? That's a reasonable guess. Right? Let's work it out. Negative not HIV is 95%. So what is positive given not HIV? 5%? Correct? Okay. Now I have everything that I need to calculate this. What is positive given HIV? 0.95, correct? Into what is probability HIV? 0.01 if he is given it as 1%. Downstairs again 0.95 into 0.01 plus what is this? Positive and not HIV? 0.5 multiplied by probability not HIV? 0.99. Correct? Someone please work this out on a calculator or on.
Sir, what is collectively exhausted means it is dependent on.
Means together they cover everything. Yes, which means in our particular case you have HIV or you do not have HIV. There are no other possibilities. They are exclusive. Why? Because either you have HIV or you do not have HIV.
Yeah, that is mutually.
But exhaustive events means there are no other things.
So this P given HIV positive is 95. So
yes,
because of that 95 we are not calculating this.
Which one?
The last one, 5%.
This 5%. This is I think 1 minus this. For not HIV, if negative was 95%, then positive will be 5%. What is this number? Point? I have high variance in my answers. Anyone else? 0.16? 0.16? There is 16% chance you have HIV if you test positive. Why is it that a fairly accurate test, a 95% accurate test, my wife and I have a biotech company, we are trying to release a product on molecular diagnosis for infectious diseases. If we get 95%, we'd be thrilled. Our investors would be thrilled, we'd be in business. This is not easy to attain, particularly cheap. We're trying to keep the cost of our test fairly low for things like UTI and stuff like that. But, so where is the problem?
False sample size.
False positives. 95% approx, but there is a problem of false positives here. So another way of seeing exactly this same calculation, or pretty much exactly the same calculation, is the following thing. So I'm going to rub out Bayes' theorem here, which is exactly this. I leave it to you to link this to BI, etc., etc. But sometimes it's easy to just understand it as an example, as how it's done. But I'll show it to you as a picture. I leave this here, and now let's assume that I begin with a population of maybe 100,000 people. Let's suppose that I've got 100,000 people who are being tested, let's say. Now, of these 100,000 people, some of them have the disease, some of them do not have the disease, some will, I don't, the total is 100. This is my sample space, so to speak. Now, let's say, how many of them have HIV?
1%.
1%? So that's how many? 1,000? So 1,000 of them are here. So these are HIV, and how many are not HIV? 99,000, correct? Now of these 1,000, how many of them test positive? 950. And how many test negative? 50. Okay. Of this 99,000, how many test positive and how many test negative? So these guys should test negative. So what is 95% or what is 5% of 99,500? Of 99,000? 4950 is 5%. So 5% is a wrong, which means 4950 are here. This is 5% of 99,000. And so how many are now here? Negative? 94,000? About that?
95,000.
This number won't matter much anyway. So you're okay with the situation here? Now let's look at all the people who've tested positive. Where are all the people who've tested positive? These guys have tested positive and these guys have tested positive. So how many people have tested positive in all? So 950 plus 4950. Of them, how many have the disease? 950. Calculate this. This is exactly the same calculation you did before. Arithmetically, it is the same calculation.
Sir, 4950 is the culprit here.
Here. 4950 is the culprit. What does that mean? It means that there were a lot of people who had a false positive. Now, why were there a lot of people who had false positives? Because there were a lot of people who did not have the disease. For that large number of people who did not have the disease, only a few positives will swamp the positives of the people who had the disease. Which means most of the people who are testing positive are actually healthy people who have had the misfortune of the test going wrong on them. But because there were so many of them, it affected the probability. Correct?
So if it is an epidemic, for example, which is not very rare, then I think
Correct?
the test is...
No, but what is it for you? So what is the moral of the story now? So therefore, what will happen, let's say you go and I'm pretty sure this hasn't happened. But if somebody gets a positive HIV test, what will the doctor say? Check once more. Get a retest done. Why? Because let's suppose this is my test. Let's suppose this is my test. And let's suppose now I've changed the test to saying that I will say you have HIV only if you test positive twice in a row. You test it twice and both times you show up positive. Now what happens to these numbers? What is now the positive given HIV and what is now negative given HIV? First of all, what happens to this? What happens to these? What is the chance of a false positive now? So the chance of a false positive, which was previously 5%, now becomes it must go wrong twice. So 0.05 into 0.05 and then 1 minus that. 5% of 5%. 5% of 5% is what? It's a quarter of a percent or something like that, or even less maybe. That becomes now a very large number. So this number becomes much smaller. The chance of a false positive becomes much lower. And because the chance of a false positive becomes much lower, this number becomes a lot lower. And now the number begins to approximate what you think it would. But for this to work, I must be able to multiply the two probabilities that both tests went wrong. That multiplication comes from independence, which means the second test that you should do should be from a different laboratory, which would have its own biases, it will have its own problems, but they'll be independent of the first guy, and you can multiply this out and this problem will go away. If it doesn't multiply out, if the same result happens, in other words, if the same thing shows up, then this 0.5 will not go down. So, now this difficulty with Bayes' rule, this also again, for example, this shows up in many things, even in business. So, if I'm trying to detect, let's say, fraud, I'm trying to detect fraud, and I have a fraud detection algorithm, and I now say, if I see this signal, what is the chance that it is fraud? By Bayes' theorem, that will be low. The reason that will be low is because most transactions are not fraudulent transactions. And so even if there is a small possibility of detecting a non-fraud transaction as a fraud transaction, I have messed up my algorithm.
So does it mean if we run it twice, will it give the accuracy more?
You have to do the test independently. Running the same program twice will not help you. So in the biological example, you need to run it again in a different test. In a machine learning situation, what does that mean? It means you have to give it fresh data. Different data from the same situation, shall we say. Which is a little harder, but that's fine. So this is Bayes' theorem.
Sir, that last world and spam problem, how does it kind of map to this?
How does it map to this? Okay. Well, it looks completely different, does it not? Okay. We'll do it this way. What is the proportion of spam and not spam? Let's say this is spam and not spam. What is the proportion? So I need to know this. This is the proportion of things that are spam and not spam, independent of what is in the text. What's the proportion of emails that are spam? What do you think?
5%. 5%.
30% are spam? Okay. You guys know your inbox. It also points to a healthy social life, right? So now what? Now let's suppose that we fix the problem, and I'm going to solve the problem not for words but for one word. So what's a spam like word, for example? Bye. Congratulation? Congratulation. Right? No, okay. Palm, cool. Congratulation. So now I want probability of congratulations given spam. What is probability of congratulation given spam? If congratulation is there, then if it is spam, what is the chance that the word congratulation will be there? 100%? That's a little too. 75%. Let's say this is 75%. Right? Then what else do I need? Because what is the problem I'm trying to solve? So I'm trying to solve the following problem. I'm trying to find probability of spam given congratulation. This is what I want to find. I want to say that if I see the word congratulation, what is the chance that this email is spam? That is the problem I want to solve. Now to solve that, I'm solving the opposite problem. I'm saying what is spam, what is not spam, what is congratulation given spam, and I need one more probability. Congratulations, not spam. What is this? 25%? Not necessarily 1 minus this. This is a separate calculation, but it could be 25% if you want to. Let's make it 35. Which means if it is a genuine email, if it's not spam, there's a 35% chance that the word congratulations will be there. Now, I don't need to make this up. As I said, in a laboratory, I can look at all spam things and I can count how many times congratulations shows up in it. So now let's suppose this is here. Let's suppose I know this. Now, can you do the calculation? You can do it using Bayes rule. You can do it using the diagram if you want to. Just try. What is the answer?
So what we are saying that congratulations given are not spam is 35%, that is known actually.
These 4 numbers are known to you. Well, actually, these are the same numbers. So 3 numbers are known to you. If it is spam, then the chance of congratulation is 75%. If it is not spam, the chance of congratulation is 35%. Now I want to find what is the probability of spam given that there is congratulation. Now how do I
Out of these 4, 3 are known, right?
All 4 are known. This is my, shall we say, the information that's available to me. Some of you can try using the formula, some of you can try using the picture. So if I do it using the formula, what will it look like? Spam given congratulations is equal to probability of congrats, I'm going to summarize this, spam multiplied by spam divided by probability of congrats given spam multiplied by probability of spam plus probability of congrats given not spam multiplied by probability of not spam. This. And this is what? Congrats given spam is 0.75 into probability of spam is 0.3 divided by 0.75 into 0.3 plus congrats given not spam 0.35 multiplied by not spam is 0.7. Point? No, is it? 0.47? Or you may want to draw a picture like this, like we had drawn before. Begin with another typical number, let's say 100,000. You'll do it as spam, not spam. On the spam side, this is 100,000 emails. On the spam side, how many will there be? 30,000. On this side, 70,000. On this side, how many will have congratulations? This is on the spam side. 75% of them will have congratulations. So 75% of 30,000, that's what, 22,500 or something like that. And the remaining will not have congratulations. How many here will have congratulations for not spam? 35% of 70,000. What is 35% of 70,000? 24,500. And so what is my answer? 22,500 divided by 22,500 plus 24,500, which is presumably my 47%. You can do this as well. So, without opening the email and seeing the email, the chance that it is spam is 30%. But if the word congratulations is there in the email, the chance that it is spam has gone up to 47%. Now, you would not do this just for congratulations, you do this for a whole bunch of words, which means that instead of congratulations, you did congratulations and something, etc. Which means that instead of congratulations here, it will be congratulations and something here. Which means for these probabilities, you will need to say congratulations and something else. Let's say another word. What's another word? Offer. So you would now say, what is the probability of spam given congratulation and offer? Now you would need congratulation and offer. But if you assume independence there, this can be congratulations given spam multiplied by offer given spam. So word by word the probability can be calculated and it can be put in. This approach you will see studying text mining, one of your courses, is called the bag of words approach. The words are put into a bag irrespective of their order and things like that. Yeah.
For one word, yes, it's spam and not spam.
Yes.
Here,
Yes.
So it will be like 2 cases for each word.
Yes. So each of these, the A will then be a new event and that new event would be different words. And so that those different words will be thought of as the product of each word. So the chance that the words congratulations and offer are there in the email is the chance that congratulations is there in the email multiplied by the chance that offer is there in the email. That's an assumption that is built into the bag of words model. If you don't like it, what you have to do is you have to give me the joint probability of offer and words. And those models are also there. They're called bigram models.
Offer and word plus spam and not spam.
Or no. Spam and not spam are where? Spam and not spam are in the BI.
Right, but in the formula below, for each case,
yes,
we are adding 2 times. So
these two, spam and not spam. Yes. Yes, so you're relating it to 2. Here there are key possibilities.
yes, so the number of possibility will be combination of
no. The number of possibilities in this case, no, and there could be other possibilities here. Here the things I'm deciding between are just 2, spam or not spam. In this formula, the number of things that I'm deciding between are many. For example, in your Gmail, how many categories are there? There's social, there's promotions and primary. So instead of it being spam, I can define it as primary, social and promotions. So now I need to find what is the probability of primary given congratulation, promotion given congratulation and social given congratulation. There are 3 of these now. That now you can apply here. There's B1, B2 and B3. So we've already seen an example of a distribution. I'll simply tell you what it is, the binomial distribution. What is the binomial distribution? The binomial distribution is a distribution of simply counting the number of things, the number of defective products, the number of customers that receive service, etc., exactly like the applications that we were talking about. This is the statement we have already seen. The probability of getting X successes out of N trials is P of X is equal to N choose X, P to the power X, 1 minus P to the power X, where the individual P is the probability of getting success in one trial. You remember my formula of 0.1 to the power 2? So it's that formula. What does this formula say? This formula says that if P is the probability of success of a single trial, then what is the probability of getting X successes out of N trials? N trials, P is the success probability of each trial. What is the probability of X successes? N choose X, P to the power X, 1 minus P to the power N minus X. How do I think this through? What is a trial? A trial is the total number of attempts that I am making, the total number of products that I am making. I am making 3 products. The probability of each product being defective is 0.1. What is the chance that I will get 2 defects? 3 choose 2, 0.1 to the power 2, 0.9 to the power 1. P successes, P into P into P, n minus x failures. What is not a success is a failure, whose probability is 1 minus P, and there are x ways of choosing that original n.
Sir, in this case, it's a like these trials are like with replacement.
These trials are not just with replacement. Yes, they're with replacement. It's not like it's a population, so to speak. In other words, an actual experiment is not being done. It's imagined that someone is doing this experiment repeatedly. So yes, if you want to think of it as replacement, it's a model. For example, here, a bank issues card statements to customers under the scheme of MasterCard. Based on past data, the bank has found that 60% of all accounts pay on time following the bill. If a sample of 7 accounts is selected at random from the current database, construct the binomial probability distribution of accounts paying on time. What is the question being asked? The question being asked is this, that I am looking at 7 accounts and I am trying to understand how many of those accounts are paying up. How many of those accounts are paying up? Now, what values can it take? What are the possible values that my x can take? 0, 1, 2, 3, 4, 5, 6 and 7. 6 means none pay on time. I'm sorry, 0 means none pay on time, 1 means 1 pays on time, 7 means all pay on time. The chance that every one of them individually pay on time is 60%. And I'm going to make the assumption that these people aren't talking to each other. So they're behaving independently. The 60% chance applies to everyone separately. Which means that if one person has paid, that has had no impact on whether another person has paid or not. Correct? Let's do one of these calculations. Let's say, what is the probability that, let's say, how many people? 2 people pay on time. So 2 pay on time. What is the answer to this? You can use this formula directly, but 2 people pay on time means 0.6 into 2, 0.6 into 0.6, not into 2 to the power 2, 0.4 to the power 5. These are the 5 people who have not paid on time. These are the 2 people who have paid on time. So this 0.6 into 0.6 into this 0.6 into 0.6 into 0.4 into 0.4 into 0.4 into 0.4 into 0.4, the 7 people. Now that is one arrangement. How many such arrangements are possible? 7 choose 2 arrangements are possible. Those 2 could be the first 2, they could be the next 2, they could be the first and the last. There are 7 choose 2 of those. For each of them is a pattern: paid, paid, not paid, not paid, paid. And every time you see a paid, 0.6, every time you see a do not paid, 0.4. The 0.6 you are going to see twice, and the 0.4 you are going to see 5 times. Therefore, this formula.
So, can you expand the choose one?
7 choose 2 is a formula which simply says how many ways can I pick 2 things out of 7. The formula for it is 7 factorial divided by 2 factorial into 5 factorial, which is 7, in this case 7 into 6 divided by 2, which is I think 21. The 21 ways to pick 2 out of 7.
To 5 factorial?
Because I asked for 2. I can do it, and the problem asks for all combinations. I have just solved it for one particular answer. I need to do it for 0, 1, 2, 3, 4, all of them. If I add them, what answer will I get? I'll get the answer 1, because something must happen.
Isn't the number of primes 8 and the
No. The number of trials is 7. The number of outcomes is 8. If I toss one coin, I can see 2 things. So there are 7 outcomes. There are 7 people. So 0, 1, 2, 3, 4, 5, 6, 7. That's 8. The 8 possible outcomes. Alright. So now there is a file here. It's called, I think, Binomial Distribution Example. You'd import a few things for plotting and for the stat functions. Then I'm going to set up the problem. How am I going to set up the problem? In this particular case, just by specifying an n and specifying a p. What is the n? In this case, n is the total number of trials. Why is it 7 for me? Because there are 7 customers. Correct? P is 0.6. Where do I get this 0.6? Here, right? This 60%. What am I doing here? What I'm doing here is I'm creating the sample space. I'm creating the set of numbers for which I want to calculate the probability. So this one here, the range function 0 to 8. So when I do this, it creates an array of 8 numbers 0 to 7.
Do that 0 really has a value? We don't need it.
Of course we do. There is a reasonable probability that nobody pays on time. Same place, wherever you got the other one from.
Can you repeat once more the basis of the formula, how it was?
How it was formed? This is X people have paid. So this is P, so think of it as P into P into P X times. And think of 1 minus P into 1 minus P N minus X times. Because X people have paid, and what allows me to multiply the probabilities? Because if there's 60% chance you pay, there's also a 60% chance you pay. And so when I figure out the chance that both of you pay is going to be 6.6 into 0.6. And if he doesn't pay, and I want to multiply those, so 0.6 into 0.6 into 0.4. Now how many 0.6s are there? How many successes I want? How many 0.4s are there? How many non-successes are there? And how many such possibilities are there? How many ways can I get 2 successes? That is what I'm calling 7 choose 2, which is 21. Why is it 21? You are going to pick 2 people out of 7. How many ways can you pick them? The first person you can pick in 7 ways. The first person who pays on time. The second you can pick in 6 ways. 7 into 6. But if I pick you first and you second, that's the same as picking you first and you second. So I've double counted. So by 2. So 7 into 6 by 2, which is my 21.
So one quick question: when in practical world,
now he gets it.
Look out for binomial distribution.
This application, this kind of application, or another kind of application. For example, I can change this to saying in sales, I am selling my, or I am approaching 7 leads. The chance of a conversion for a lead is 60%. What is my sales distribution? Okay, so I'll use that information, for example, to figure out, let's say that how much budget should I have for the sales team? For example, I could say, you know what? I'm going to approach 7 leads and I'm going to get sales. However, how are those sales going to be made? The sales are going to be made on the phone. But to confirm the sale, I need to be able to send a salesperson to the person's house and get their signature. This person is going to take a certain amount of time to travel through the famous city of Bangalore and get stuck in the traffic jam and get there. So I'll be able to get at most 3 signatures in a day. And if I lose it, I lose it. Or 4 signatures. Or so let's suppose that therefore I employ 1 person. Is that good enough? So now I'm asking the question, what is the probability that I'll end up making more than 3 sales in a day? Because if I end up making more than 3 sales in a day, I'll not be able to close all the sales. So this becomes a Salesforce question. It becomes a question of saying that based on my ability to sell, I should have a sales team. If my sales team is too short, too small, there's a probability that they will not be able to close out all my sales and I leave money on the table. If my sales team is too big, I'll be paying for that sales team, but they will not have enough to do. So yes, the binomial distribution is used left, right and center. In contact centers, yes, is used big, same argument. In contact centers, for example, one reason it's used is how many escalations do you expect? So in many of these. So how do I execute on this? So I've given the, I've created the array. Now here's the command that you need to know. This command calculates that formula. That n choose k, that formula is calculated. Right? By the way, you can manually do this if you want to once, which is your 21 into 0.6 to the power 2 into 0.5 to the power 4. Does anyone want to manually do it once? No one has any, just to check, otherwise you'll just trust the output, that's fine. But if I do this, binomial stats.binomial.pmf, PMF stands for probability mass function, in case you want to know what on earth that means. Probability mass function. So this thing is called a probability mass function. Probability clear? Mass means it's almost as if you're thinking of a solid material and the probability as being physical mass. How much mass is in each number? How much mass is in each number? So
what it represents, that PMF?
This number. The PMF simply is this number. It's a calculation of this number. So now if I ask for binomial, if you do it without the equal to, it will just give it directly. Alright. So it's done. It just takes a little bit of time. So binomial is an array. So what is this number here? For 0. So what is this in the business context? This is the chance that nobody pays on time. The number of people who pay on time is 0. So it's about 0.16%. What is the chance that 1% pays on time? 1.7%. 2 people pay on time? About 7.7%. 3 people pay on time? About 19%. 4 people pay on time? About 29%. 5 people pay on time? 26%. 6 people? 13%. 7 people? About 2.7%. Okay. Curiosity question. How many people would you expect to pay on time?
7.
No. Remember, there is a 60% chance that everyone will pay. Yes, 4 or 5. In fact, the right answer is 7 into 0.6, which is about 4.2%. So you would expect to see about 4 or a little more than 4 people pay on time. And the chance of 4 people paying on time is what? 0, 1, 29%. And the chance that 5 people pay on time is about 26%. If you want to plot this, there's a slightly sort of, jazzed up version of a plot here. So the first line says plot it. It says binomial. Then there's a title. There's a labels. And then finally the plot command itself. I think that's a plotting artifact. I mean, it tells you what to plot. You can remove it and see what happens. Here's an interesting thing. Someone's asked, what happens when I add up all the probabilities? Which is what I get here. I don't need it. It's a checksum. So one possibility of a business outcome is, what is the probability that say more than 6 people do not pay their bills on time? Now in a collections team in a bank certainly is interested in that, because you have to go after that. There's also a question of what is the entitlement on a specific month. So a bank is going to make money, or let's say a telephone company, whoever is going to make money on the amount of bill that's actually paid. Now the fact that a bill has been given to a person doesn't necessarily mean they'll pay it, like here. So how much money does the bank actually expect to make? It has to have an estimate of its revenue per month. How does it get that? By doing a calculation of this kind. Here's a little formula if it wants to help you. The average of a binomial distribution is given by n into p. We just discussed that. Total number of trials into the probability. 7 into 0.6. Which means, for example, that if I think that my success probability of a sale is 10% and I approach 10 people, the number of people I expect, number of sales I expect to make is 10 into 0.1, which is 1. Does that mean I will make one sale? No. The distribution goes from 0, 1, 2, 3 up to 10. But the average is at 1. Similarly, the average of this distribution is where it's at 4.2. But where is the picture? Where is the average? Where is 4.2? Somewhere here, right? Somewhere here is 4.2. This is the center of gravity of the distribution. There's a standard deviation formula, if you want to know, NP into 1 minus P. The standard deviation will make a little more sense when we talk about the normal distribution. I hope I'll get there. Now there's another distribution which is used a little less in practice. You guys are all very practical types. How is it used? How is it used?
Any examples where would we use a mean or a standard deviation on the binomial?
The kind of question he asked. So I want to make an estimate, for example, as to how many people will pay my bills. Because based on that I will decide. So I can do it two ways. I can, for example, say what is the number of people I expect to pay my bills? 4.2. What is the number of sales I expect to make? What is the number of errors I'd expect to have in my code? What is the number of defective products? What is the number of expected customer recalls that I have? Whichever industry you're in, there are events that happen in that industry. And you're trying to find out an estimate for it. One estimate for it is an expectation, like we discussed yesterday. But remember, this one is not coming from data. 7 into 0.6 is not a calculation based on data. I didn't give you any data on people paying their bills on time. I gave you a theoretical distribution. This is an assumption that I made. It's not an average computed on data. So therefore, when I make that distributional assumption and now say based on that distribution, what is the expected number I should see? Will I see that all the time? No. That's why there's a distribution.
So there was an array that you gave,
yes,
like probability of 1%, 2%.
Yes.
In reality, when you do real solution, this array is something which we have to churn with the historical data in the lab, right?
No. So this would be used, and it is often used, where what will come from the data. One thing that can come from the data is the P.
Yeah, okay.
The P, just the P, not the distribution itself.
Okay, but probability of 1% paying, 2% paying.
Yes, and so that will not. So, for example, I want to find that next month for a new customer, or next month, how many people will pay their bills on time. That's the user case. Now, here's the way I do it. I ask myself, last month, how many people paid their bills on time? But it may come from the data. So the P comes from the data, but the calculation for saying how many people will pay their bills on time comes from the next month. It is done for the next month. It makes no sense to do it for this month because I already have this month.
Exactly. But let's take a situation that the probability that we added, right? Probability of 1% paying, probability of 2%.
Yes.
The exact array that we had in the Python.
Yes.
The entire array.
Correct.
The data for the array. Will it come from the past data?
It already has because the P has come from the past data.
Yeah, that's the question I had.
Yes.
So that normally in a real situation,
yes,
that probability has to be computed in a lab based on past data, right?
Yes. Let me clarify that. Yes, it came too quickly. So there are complexities. One is you might be supposing that it changes with time. You might be in a situation that does this. That you know what? I have a collections problem. Means not enough people are paying. So I might have a problem that looks like this. That the number of people who pay their bills on time is 60% and I'm saying it's too low. Correct? Now I want to increase that. How to increase that? My manager comes and says, make it so such that the number of people, say let's say more than 5 people not paying on time, this number must be less than, let's say, 0.1%. That's the goal. Now to do that, I now need to change my P. So I'll set my P so that the answer to this question becomes less than 0.1%. That gives me a target P. Now I must reset my collection process so that that P is attained. To achieve that P. So I can create applications in various ways. Give me the P and I will tell you what happens. Or give me a situation that I want to achieve and give me a target P such that it gets there.
The constant and the variables keeps.
Yes, the constant and the variable keeps changing. What do I want to fix keeps changing. So that depends. This is a model. This is a mathematical model. How you use it is up to you. This is one particular use case, but there will be many use cases for this. You see one in logistic regression, for example. The Poisson distribution is a very similar distribution, except that for the Poisson distribution, that has a mass function that looks like this. Now, this mass function counts, but does not count relative to a maximum. The binomial goes from 0 to n. 0, 1, 2 up to n. The Poisson, there is no n. There is no total number of things. For example, I might ask the question, how many fraud cases do I expect to see? There is no sort of maximum to that. I could frame it as saying that tell me the total number of cases there are, and that is my n, and then I'll figure out based on a p how many fraud cases there are. But there are situations where this maximum is something that doesn't quite make sense. How many fraud cases are there? How many cracks are there, microfractures are there on this bottle? It's a count, right? How many eggs will the chicken lay? It's a count. It's not in some way a proportion-like thing. So if you're in a pure count-like situation, you are in the situation of the so-called Poisson distribution, whose mass function has this slightly different form called e to the power minus lambda, lambda to the power x, where lambda is the average. If on an average 6 customers arrive every 2 minutes at a bank during busy working hours, what is the probability that exactly 4 customers arrive in a given minute? What is the probability that more than 3 customers will arrive in a given minute? This is slightly different from a binomial. Why? The reason is, in the previous case, they were asking for how many customers did not pay. But there was a total universe of customers, 7 customers. There was a sample space. Here there isn't. I'm not telling you how many could have come. There is a series, and that series could go up to anything, so to speak. This is the typical situation of a Poisson distribution, where it's not a question of saying independent trials and how many were successes. It is that I'm simply counting how many there are, and I have no idea as to how many there could have been potentially. How many fraud cases I do not know. How many microfractures I do not know. How many customers could have arrived I do not know. There's no maximum to it. So there's a similar calculation here for the same thing. If you open the Poisson distribution example file. Now for the Poisson distribution, that formula, for the binomial, there were 2 numbers you needed to put in, the n and the p. For the Poisson, there is only one number. There is only one number, and that number is usually called the rate at which my customers are arriving, the rate at which I get fraud, the rate or the density of my cracks. It's a rate number. You can think of this rate number as a product of n and p, as the total number of opportunities multiplied by the product, if you want to think of it as that. So for the Poisson, I need to be able to specify the rate. And now I do exactly the same thing. I can calculate the Poisson probability, stats.poisson.pmf. Now for computational purposes, I am setting the range from 0 to 20. I can set it to be any high number. That 20 is not coming from my data. That 20 is coming for a computational reason, because I want to do the calculation for a finite number of points. And as you'll see, after 20, the numbers are very, very small. So the 20 is not there from the problem. The 20 is there for my visualization.
But how do you come to that point?
I can make it any other number. If you make it too low, you will be leaving some probability to the more than 20. If you make it too high, you will be calculating a lot of zeros. So what is my problem? Let's go here. My problem is, what is the probability that exactly 4 customers arrive in a given minute? 6 customers arrive every 2 minutes at a bank. What is the probability that exactly 4 customers arrive in a given minute? What have I put my rate as? 6. And here is my distribution. This is what? 2.4 into 10 to the power minus 3. So this is what? 0.002. Let's see what happens. So what is the probability of 0? 0.002. What is it for 1? 0.001. For 2? For 3? 0.008. For 4? No, for what? No, what is it for? What is it for? Says this 0? 1, 2, 3, 4. What is it for 4? 0.13. 13%. What is it for 5? 16%. What is it for 6? 16%. What is the average number of customers I expect to see? 6. 16%. What is it? What is it? 7? 13%. For 8? 10%. Now it will start going down. And it will go down, and by the time I have reached 20, it is already 0.00001. So if you had gone beyond 20, I would have seen even smaller numbers. But I could have stopped, for example, let's say at 15. If I had stopped at 15, where would this have stopped? 1, 2, 3, 4, 5. It would have stopped here. Which is fine. 20 is an approximation. 20 is a guess. Here is a distribution plot. The same thing. This is the plot of the distribution function whose average is at 6. By the way, what is the answer to the question? What is the probability that exactly 4 customers arrive in a given minute?
15%.
Be slightly careful. Be slightly careful. 6 customers arrive every 2 minutes. The question asks for exactly 4 customers arriving in 1 minute. Which means, if I'm putting 6 as the rate, then I have to convert this question to saying what is the probability that exactly how many customers arrive every 2 minutes? Each customers arrive every 2 minutes. Or what I can do is, I can change my rate to 3. This one is a distribution where you do most of the calculations with. This is the normal distribution, the distribution that corresponds to age, to the mean spread, all the continuous variables that we were looking at. Numbers. So if you're dealing with numbers, then you deal with a distribution that has a shape like that. This is called the normal distribution. Now the normal distribution, the reason I wanted to get to is this, because of this picture. Now this picture puts the standard deviation in context. So yesterday we talked about the standard deviation. And a question often asked is, what does the standard deviation mean? What is standard about the standard deviation? This picture tells you what is standard about the standard deviation. So this picture means that if I have a normal distribution, then the chance of being within one standard deviation is 68%. As a numerical quantity. This distribution is a distribution that has a mean and it has a standard deviation. Now the standard deviation has to be defined in such a way, and the way the standard deviation is defined implies that the chance of being within one standard deviation is 68%. The chance of being within 2 standard deviations is 95%. The chance of being within 3 standard deviations is 99.3%. So now if I tell you something like this, that I'm telling you that for a group of people, the mean height is say 5 feet 10 inches with a standard deviation of 2 inches. Mean height is 5.2 inches and a standard deviation of 2 inches, right. So mu, so let us say 5 feet 8 inches and a standard deviation of, sometimes denoted by sigma, of say 2 inches. I have told you some interesting things. If you allow me a normal distribution, I have now told you that 68% or roughly 2/3 of the people are between 5 feet 6 inches and 6 feet.
5 feet 10 inches. 5 feet 10 inches.
Oh, 10 inches. Same stuff. This is 5'8". This is one standard deviation, which is 2 and 2. So this is 5'10", and this is 5'6", and this is about 68%. Sometimes it's easy to remember it as 2/3. Close enough. 2 out of 3 are between these two heights. 95% are between what and what? 6 and 5, 4. 95% are between these two heights. 1 in 20 are outside this range. So therefore, if I tell you the mean and the standard deviation, I have actually told you a reasonable amount as to how the data is spread. So sometimes the mean and the standard deviation are reverse engineered, so to speak. So if you are a professional student, I often do this. So people often ask, where is the data? They said, nobody has any data. So I say, so you know, you're trying to figure out what work to get. So you might ask a question, when do you typically arrive? And someone says, 9 o'clock, thereabouts. What's your earliest arrival time? 8:30. What is your latest? 10 o'clock. So looking at this, you'll now say, so you can decide as to what you should assume that the whole range of the distribution is. Say from say 8:30 to 10 o'clock. And now this pattern tells you that if I go for 3 sigma covering 99.7%, this whole range is about 6 standard deviations. So to find the mean, you just take the middle of it, and to find the standard deviation, you take the whole range and divide by 6. So I can get an idea of what the average is and what the standard deviation is without even getting any data from you, but just getting a sense of the extremes. It's a nonsense way of doing things, but what it does is it allows you to cheat with essentially very minimal information. So remember these pictures, they're helpful. They give you an idea of what the distribution is like. Now by the way, these numbers are easy enough to calculate. So we'll do some calculations. The normal distribution is a bell-shaped distribution. So it's symmetrical. The tails could be extended. It depends on 2 parameters, mu and sigma. See the power of it. By giving you 2 numbers, I've given you characteristics like this. So, and I can do calculations, and this is the density function, that equation, if you want to think of it. Nobody does anything with this. And then you can do calculations on it. So here's a calculation. I'm not sure whether this is a calculation that we had worked on. This is a calculation that we actually do in some detail. Let's do it. So the mean weight of a morning breakfast cereal pack is 295 kilograms with a standard deviation of 0.25 kilograms. A random variable weight of the pack follows a normal distribution. What is the probability that the pack weighs less than 280 grams? Now why would someone be interested in this? One possibility perhaps is that maybe the target for the pack is something like 300 grams. And you're trying to understand whether you are within tolerances or more or less or something of that sort. So, what is the probability that the pack weighs less than 280 kilograms? So, what do I need to do? What is my picture like? My average is 295, standard deviation of 25 on the gram scale, and I want to find the chance of being to the left of 280. I need this area. Calculating this area is actually quite easy. So let me calculate that area. So I'm going to do it this way. Stats dot norm dot CDF. CDF stands for cumulative distribution function. I'll tell you what's cumulative about it. CDF. Now, what is the number that I'm interested in? Probability of being less than 280, or if I want to be very clear about this, 0.28. Now I'm going to do something here, comma, location equal to, location means the middle of the distribution. For me, what is the mean? 0.295, comma, scale is equal to, what is the standard deviation? Is that right? Are the numbers correct? 27%. This one here, instead of 0.28, you are saying it should be 0.27? No. I am calculating the answer to this question. What is the probability that the pack weighs less than 280 grams? This is the question. To answer this, the way I set it up was to say that what is the chance of being less than 280 when the mean is 295 and the standard deviation is 0.25. Because of certain technical aspects of other functions, the mean here is referred to as location and the standard deviation is referred to as scale. So if those terms location and scale confuse you, just ignore it. This first term is the number, but otherwise, this one here, this one here makes more sense. Okay, go ahead with this. All right. Do you understand how the code works? All right. Let's do the second problem. What is the probability that the pack weighs more than 350 grams? What do you think the answer should be? Guess.
1 minus less than 1.2.
Yes, 1 minus what?
Stats norm of
1 minus stats dot norm. Now what should I do? Sorry, norm dot CDF. 0.350, comma, same thing. About 1.39%. The chance of being more than 380. Clear? So what does CDF do? CDF, cumulative distribution function. What does it do? Calculate the area to the left of, less than. Therefore, if I want to calculate the area probability more than, I need to go 1 minus. Why? Because the whole probability is 1. What about the third one? What is the probability that the pack weighs between 260 grams and 340 grams? How to do this? Yes, 340. So I now need to be between 340 and what is it? 260. So less than 340 minus less than, so it should be again, let's say, let's get lazy. What is this number? 340 and this is 260, right? 88%. 88% of my packets are going to lie between 260 grams and 340 grams. It's an assumption we are making. Remember, there isn't any data at all here. There isn't any data at all here. What numbers am I using? Mean and standard deviation. So what I'm doing is, what is the advantage that I have? I don't need the data. All I need is this mean and standard deviation. What is the price I pay? An assumption on the distribution. No. So I could, instead of using norm, have another distribution sitting there. There's a whole range other possibilities. Binomial is one. There are other distributions if you want to.
How would you decide?
You would decide based on whichever distribution makes most sense for your application. Now, in certain cases, you know what those nature of those distributions look like. For example, if you're looking at lifetimes of things, it's an exponential distribution or a gamma distribution or something of that sort. But there's a certain advantage to the normal distribution because of something called the central limit theorem. And we'll cover that, a little bit of it will be mentioned in the next residency. Central limit theorem essentially says that if I take the averages of things or the totals of things, I end up with a normal distribution. The normal distribution is a result of averaging. So if my observation is a total of little things, then probably the normality assumption is a good assumption for that. Large data doesn't necessarily mean normal. But if the observation is the total or the accumulation of lots of things, so for example, height is often normal. Why? Because our height is in some way a random combination of many things, maybe the height of each of our cells and things of that sort. So the normal distribution is often used as an assumption based on the central limit theorem. The other part of it is that even if the data doesn't look like a normal distribution, the sort of generation for it, the sample from a normal distribution doesn't necessarily look like a sample from a normal distribution. So even like we saw yesterday, the bell-shaped curve. So it's hard to look at the data and say that it is not normal. So the normal distribution is percent to the that is often made in the absence of any other information on the data. It is obviously wrong in cases where the data has a very strong skew in one sense to another. But remember, in many cases you are not even talking about the data. The question that you're asking is not a data question. The question that you're asking is a probability question. It's a situational question. You're asking for effectively the following thing. Why is this an analysis of this kind done? What data is it going after, if anything? You're talking about the data being normal or not normal. What data is it even referring to? Why do I care about the first question? What is the probability that a pack weighs less than 280 grams? One context for it could be that if a person buys a pack, what is the chance that they're getting a light pack? In other words, something that is less than 280 grams.
The way you have to design your packaging also. Right?
True, but my question is this, where in all of that is data? Where is the data in this? How do you even think of the data? Is it a data problem at all? I'm asking the question that is my product in spec? In other words, what data are you referring to? Is this a data science issue at all? Or is it not? You're asking the question, is it normal, is it not? Is it a data question?
How you reach the customer?
Yes.
And what kind of packaging sizes?
So what data is that? So data of what? Data of my SKUs? How many data observations? Which data observations? For whom? For which customer? When? What data? So Kellogg's quality check for what? I could argue, for example, that this is about saying that if he goes in and buys that breakfast cereal, will he get something that is below 280 grams?
For the value of the price that we are paying.
Yes, but where is the data?
In the supermarkets, for example.
There is no, it's a business question. What data does it apply to? What I'm trying to say is that it's not a data problem at all. You can solve it using, you can say, I'm going to gather a lot of data to solve the problem.
But here the data we already have, right? On the basis of which we have picked up the mean, basically that what.
No, I'm telling you that this could come from the past mean. This could, so you could say that I'm going to gather the data to get this number and get this number. That's a good answer. Then in order to solve my business problem, I need a mean and a standard deviation so that I can get a handle of what is the chance that it will be underweight. Now that mean and standard deviation has to come from somewhere. And I can say I will use data to get that mean and the standard deviation. That's a good answer. That you'll now say, why do I need data? In order to calculate mean and standard deviation. Why do I need mean and standard deviation? Because that's the least data I need in order to be able to answer this question. Which is the question I'm interested in answering. Will he buy the product? Will my network go down? Will I be under product? There's a business question I'm interested in answering, or there is a tech question that I'm interested in answering. And often that is made independently of the data. So for example, the car has to stop, autonomous vehicles. Right? The data that the car is going to react to is the scene that the car sees in front of it. But that's not the data on which the algorithm is going to be based. So the data that the car sees is what it is reacting to. Similarly, this is reacting to only one number, 280 grams. I'm now solving the 280 grams problem by saying, is it this? So I'm giving you a packet and I'm asking the question, is this underweight? Does this have less water than it should? I'm interested only in that. I'm not interested in any data. So in hypothesis testing, what we'll do when we come back is to be able to close out that question and say, therefore, from data, how do we get to numbers like this? Which now means that I have to put the two pieces of this residency together. I have to put together the idea of calculating means and standard deviations from data to the idea that it is a parameter being estimated to solve a problem. So now you would say that data, this 295 comes from data. That immediately raises an issue. But if it comes from data, it comes from a sample, and if it comes from a sample, it's not accurate. And if it's not accurate, then how well does it solve my problem? And life keeps going in circles like that. So this is the probability side to it, which explains why I need to have means and standard deviations in order to do a calculation. And the descriptive part says, I have the means and the standard deviations to do the calculations.
So does that mean that when I had the sample size,
yes,
sample set,
yeah,
that if it had normal distribution, then I am more reliable?
No. If it had a normal distribution, then maybe I'd be able to get good numbers around this and the plus minuses would be symmetric. This calculation doesn't rely on the normality behind the 295 estimate. This calculation lies on the normality of the future data, which doesn't exist at all.
But what I'm asking is, will these numbers be more reliable, the mu and the sigma, if I had normal distribution?
No, not necessarily. Not necessarily. If I have normal distributions, I'll be able to use certain very specific formulas that we'll see. If it is not normal, those formulas may break down a little bit. So those formulas help me calculate. So normality helps me calculate. It helps me calculate how good these numbers are. It also helps me calculate using normality what the answers to questions such as these are. But the normality that I use right now, 10 minutes ago, had nothing to do with data. And that to some extent is the power of probability, that you're being able to answer a question like saying, do I expect that the weight is going to be less than 280 grams without having data in place for it? The simpler answer would be, give me the data and count how many are less than 280 grams. That's the simplest answer, right? What is the chance that the pack less than 250 grams? Empirical. Go collect 100 packets and find out how many of them have weight less than 280 grams. That's the answer to that question. So why are we doing all of this? Because you don't have that. Because you don't have that data. Why don't you have that data? Because that's not the question I'm asking. I'm asking the question, is it less than 280 grams? I'm looking at a computer program in front and I'm asking, what is the chance that there are more than 5 bugs in this code? I'm looking at all the computers in my office and I'm asking, what is the chance that all of the employees today, there's going to be more than 2 hacks or malicious attempts on my server? There is no data yet. There will be, but by that time the hacks happened. But I still need those numbers and I get those numbers using these distributions. To operationalize those distributions, I need certain numbers and I can guess them, I can beg them, I can borrow them, I can steal them, I can estimate them from data, I can ask for a friend, I can read a book, see a standard, I can look at market research. Yes, I can do any number of things in order to get at those numbers. I can look at an industry standard. Those two pieces will put together. Shruti is getting a little nervous.
Normal distribution will it be always 6 sigma on the mean?
This picture is definitional for the normal distribution. This picture, this is definitional for the normal distribution. So if you look at 6 sigma will cover 99.7%. 3 out of 1,000 will lie outside the plus minus 3 sigma range. Not everything, but roughly 3 out of 1,000. This is 3 sigma, 6 sigma. 3 sigma usually says 3.4 defects per million opportunities, which is actually not 3 sigma, is not 6 sigma, is 4.5 sigma. So 4.5 sigma is about 3.4 into 10 to the power minus 6. That's 4.5 sigma. So if you look at 6 sigma literature, there's a confusion there. Basically what it says is that if you have, in order to get 3.4 defects per million to the customer, you have to be within 6 sigma, which is about 1 in a billion. This is at 3 standard deviations, plus minus 3 standard deviations. If I go to plus minus 4.5 standard deviations, I'll be at around 3.4 into 10 to the power minus 6. To reach that for the customer, I need to go to 6 sigma here, which is about 1 in a billion. I must be more accurate in my factory floor for my customer. So if I reach 6 sigma, my customer will reach 4.5 sigma. And customer 4.5 sigma is the 3.4 into 10 to the power minus 6. So if you look at 3.4 into the power minus 6, it doesn't correspond to 6 sigma. Little confusing, but that's the way 6 sigma literature is written. The normal distribution is just this as a formula. Plus or minus 2 sigma is 95%. Actually plus or minus 1.96 sigma is 95%. And 3 sigma is about 99.7%. Infinity. By definition. It goes to infinity. You want to cover everything? Plus minus infinite standard deviation.